Check, mic, check. Check, mic, check. Check, mic, check. Check, mic, check. Check. All right, good morning, everyone. Welcome to the 14th GNU Radio Conference. So it's great to see a lot of familiar faces here, a lot of new faces, and welcome to everybody watching this on the live stream. So I'm very honored today to introduce Jack Dongarra. So Jack Dongarra received his Bachelor of Science in Mathematics from Chicago State University in 1972 and a Master of Science in Computer Science from the Illinois Institute of Technology in 1973. He received his PhD in Applied Mathematics from the University of New Mexico in 1980. He worked at the Argonne National Laboratory until 1989, becoming a senior scientist. He now holds an appointment as University Distinguished Professor of Computer Science in the Electrical Engineering and Computer Science Department at the University of Tennessee and holds the title of Distinguished Research Staff in Computer Science and Mathematics Division at Oak Ridge National Laboratory, Turing Fellow at Manchester University, an adjunct professor in the Computer Science Department at Rice University. He is the director of the Innovative Computing Laboratory of the University of Tennessee, and he is also the director of the Center for Information Technology Research at the University of Tennessee, which coordinates and facilitates IT research efforts at the university. So you may know Dr. Dongarra from his work in open source mathematical computing and parallel computing packages, such as BLAST, LAPACK, WinPack. So everyone welcome Dr. Dongarra to the stage as our first keynote.
Well, thank you so much for that kind introduction. So I'd like to talk about high performance computing. Sometimes it goes by the name of supercomputing. And for years, science was moved forward by theory and experimentation. So theory is a paper and pencil kind of thing where we put down some ideas. Experiments are where we take those You think about putting it into a cabinet. So we fill up a cabinet with these boards and connect things together using some interconnect. That may be gigabit Ethernet, it may be InfiniBand, it may be some proprietary mechanism that allows messages to be communicated very rapidly. And of course, we're not going to be satisfied with just one cabinet. What we'd like to do is to fill up a room with those cabinets. So at Oak Ridge National Lab, not too far from here, we have the fastest computer for doing scientific computing. And that computer is called Frontier. It has a footprint of about 2 tennis courts. So think about a room full of cabinets connected together, intended to be used to solve one problem. That's the purpose of this machine, to solve some of the most challenging problems that we have. The Department of Energy runs that computer, and that computer is used for open science, not classified work. We have other labs that do classified work. This is used for open science work. There are other supercomputers. China has a number of supercomputers as well, and I'll talk more about the Chinese capabilities and what's happening on that score. But this is the way our machines are typically built today. Back in 1993, well, actually it goes back further. Back in 1978, I was part of a software project called LINPACK, and as part of that project, I put together a benchmark. That benchmark measured the performance of a computer solving a very standard mathematical problem, a system of linear equations, AX equals B. And it solved that problem using the technique that I learned back in high school, Gaussian elimination with partial pivoting. So a very simple method implemented using the LINPACK software, and I measured the performance of a computer based on solving that problem. So we're looking at performance. So I'm talking about operations per second, and I'm talking about floating point operations, or more specifically 64-bit floating point operations. An operation in this context is an add or a multiplication. So we're looking at flops, floating point operations per second, and that's what the benchmark is trying to register. So my colleague Hans Moyer, who worked at the University of Mannheim, had a list of the 500 fastest computers in the world. They were ranked by theoretical peak performance. Theoretical peak is the paper and pencil calculation for what the manufacturer claims for their computer. I had a benchmark that actually measured something, and Hans suggested that we get together and put together a list, and we wanted to call that list the Top 500. So the Top 500 has been going on since 1993 and measures the performance of high-performance computers solving that problem, solving a matrix problem, AX equal B, using that algorithm, Gaussian elimination with partial pivoting. So we have data that goes back to 1993 for solving that problem. That list comes out twice a year. It comes out in November as well as in June, and it reflects the state of high-performance computing. The way this works is if you had a high-performance computer, you would download the benchmark, you can optimize certain components of it, you would run the benchmark on your machine and send the results to us. We, of course, check to see that you got the right answer in terms of 64-bit accuracy, and then we would register your machine as having a certain execution rate, flops, for your machine. So that's the benchmark, and that's the way it's carried out. So I want to talk about the Top 500 list. There's a lot of interesting things that come out of it. So back when we started in 1993, there were 65 systems that used Intel instruction set. And in fact, it was the Intel i860 architecture. And this graph here is, let's see, can we see that dot? Oh, there it is. So this graph is reflecting the number of machines that used Intel processors. So it goes to 500, and you see there was a modest number of machines that used Intel parts. Most of the machines on the list back then had supercomputers that came from Hitachi, NEC, Fujitsu, Thinking Machines, SGI, Cray, and IBM. So they were the manufacturers of high-performance computers. And many of those companies made their own processors. So they invested, they developed an architecture, and they put together an architecture based on that characterization. Something happened back in the turn of the century. So it was the attack of the killer micros. So the Intel processor, the x86 processor, the instruction set, and that processor was capable of doing and competing with many of the manufacturers that were making supercomputers. So as we see going forward from this period, Intel processors and the x86 architecture, including AMD, have really dominated high-performance computing. So high-performance computing is really based on commodity processors leveraging that instruction set that Intel has. And those companies that made specialized processors couldn't maintain the business, and they went out of business or went out of the high-performance computing business. They couldn't sustain the machines at the cost, given that these commodity processors were much cheaper and provided a capability which was very similar to what we had with those high-performance computers. So today, 95% of the high-performance computers on the top 500 list are based on the x86 architecture. I find that stunning. A commodity processor driving high-performance computing that way. If we take a look at the frequency of the processors on the top 500 over time, we get something that looks like this. So I'm looking at the average frequency of the processor on the top 500 list. So we see that it was rising until roughly 2004. So it was about 3 gigahertz around 2004. And then something happened. Dennard scaling ended. So Dennard scaling is this incredible situation. We always think about Moore's law, but the real secret sauce in some sense is Dennard scaling. So Dennard scaling, Robert Dennard is a scientist at IBM Watson Research, and he had a paper which said, as the dimension of the devices goes down, the power consumption will also reduce. So we can put smaller transistors that run faster on the chip that are using less power and cost less. This was an incredible situation that took place. Unfortunately, as the size or feature size of the transistors got smaller, there were some problems. And what happened was there was voltage leakage, and the result of that voltage leakage caused the chips to heat up. So they couldn't maintain the continuation of the reduction in the increase in the frequency of the processors. It would cause the chips to heat up too much. So we're stuck at basically the 3 gigahertz for our processors. And the reason goes something like this. The power consumption is proportional times the frequency. So think about, and the frequency is roughly proportional to the voltage for modern processors. So the power looks something like the frequency cubed. So if you double the frequency, make something run twice as fast, the power requirements for that chip go up by a factor of 8. So that's too much to maintain. We can't continue that rise that we saw in the early days with Dennard scaling. So that's one reason why we're capped at 3 gigahertz roughly for our processor performance. So I mentioned that our processors or our high-performance computing systems are based on commodity parts. 95% are based on the x86 instruction set. We use commodity accelerators as well to boost the performance. And NVIDIA is an example of those commodity processors. So of the supercomputers that have accelerators, 96% use NVIDIA accelerators. The other accelerators on the market come from Intel and AMD. So they also make accelerators that can be put together. The computer that we have at Oak Ridge is based on AMD parts. So they use AMD processor together with AMD accelerators, again, to boost the performance. We see that commodity interconnects are also on these systems. So 85% of the top 500 systems use gigabit Ethernet or InfiniBand as the interconnect mechanism, not special purpose things that allow for much greater bandwidth and lower latency. They're using commodity parts. And this is really to lowball the price of these machines. So the way it usually works is if you're going to go out and buy a supercomputer, you have a performance target in mind. You want the supercomputer to be at this level, and you have a certain amount of money to spend. And now you ask for bids from vendors, and the vendors go off and cobble together a machine with those commodity parts, trying to get the price as low as possible, trying to make that performance point that you're asking for. And the result is a system that looks like this, based on commodity parts. And then they throw it over the fence. And now the scientists are left scrambling, trying to figure out how to use a machine that's based on these commodity parts, which have very, I'll call it, unbalanced performance characteristics, as we'll see. And of course, 100% of the systems are based on Linux operating systems. Not a surprise, really. That's unlike the hyperscalers. So the cloud vendors are doing something quite different. They're not building their machines based on commodity parts. They're going out and they're designing their own processors. So the vendors like Google, like Amazon, like Facebook, are designing their own processors to meet the needs of their cloud-based services. And they have tremendous resources that they could put together, financial resources, to invest in hardware, invest in the design of the hardware, taping out and putting together processors that are targeted for their audience. That's quite different than what we do in the scientific community, where we don't have that unlimited set of financial resources to invest in high-performance computers. If we take a look at the number of conventional machines or vendors that produce equipment that fits into the high-performance computing space, and we look at the capital, the market capitalization, the net worth of these companies, we end up with the traditional companies like HP, Intel, IBM, and AMD. You know, if you add up all of the market capitalization of these companies, we get to about $2.6 trillion. And on the other side, the hyperscalers, we see this incredible situation where their capital worth is just dominating what we see from those conventional computer users. So even the Chinese participate in this with Baidu, Alibaba, and Tencent. They have companies that are producing these things. They also are making their own processors to use in their services. So just an incredible situation. The one outlier here is NVIDIA. So NVIDIA's capital worth today, you know, is something which dominates and sort of rivals Microsoft and Apple. You know, they're greater than Meta, they're greater than Amazon, they're greater than Google. That's a stunning achievement, and that's being driven, of course, by artificial intelligence, AI, machine learning, that need the kind of processors that NVIDIA has, and driving that market. So this is what our environment for scientific computing looks like today. It's highly parallel. It uses distributed memory. The programming model is MPI, the message passing interface, together with something called OpenMP for programming on a node. So we have nodes, and we have multiple nodes connected together. Connecting things together require us to pass messages, and we do that through MPI. We program in C, C++, even Fortran is used on these machines. The machine at Oak Ridge National Lab is the fastest machine. That machine has a theoretical peak performance of 2 exaflops. 2 times 10 to the 18 floating point operations per second. That's an incredibly large number. I have a hard time getting my hands around that number. So think about if everybody in the world did 1 operation per second, everybody in the world, it would take 4 years to achieve 1 exaflop of the world's population doing 1 operation per second, just to put that in perspective. And this machine does 2 exaflops per second. So this is a tremendous amount of computational power. It has 8.8 million cores. So if you're going to program this machine at scale, you have to coordinate, orchestrate that number of processes on your application in order to have it run efficiently. And this machine is based on an AMD CPU multi-core, a plus 4 AMD GPUs. So that's the node that's on the machine, and that node gets replicated 9,400 times to fill out those cabinets that run on that machine. But the important thing to note here is that 98% of the performance is coming from the GPUs. So the way these GPUs work is the CPU's in charge. It sends some data over to the GPU and tells the GPU to do some operation on the data. And when it's finished, you can collect the answer back and send it to the CPU. So there's this constant play between the CPU and GPU. The GPU is really the thing that's powering that peak performance, and 98% of the performance is coming from that GPU. So if you don't use the GPUs, you should really forget about using this machine, because you're only going to get 2% of that exascale performance, potential performance. So our machines are heterogeneous. They have CPUs and GPUs. That's going to change in the near future, where there's going to be a fusion between the CPU and GPU that's happening today with processors that are emerging from companies. Communication, though, is something that's very expensive. So I talked about floating point operations. In the old days, floating point operations were very expensive. Adds and multiplies were very expensive. Today, it's communication. Passing information around from various parts of the machine, from memory to the CPU, from distant memories on distant nodes of the machine, passing information is the most expensive thing that we do on our high-performance computers today. And in some sense, our computers are over-provisioned for floating point arithmetic. We can't possibly use the potential that's there because of the communication cost associated with it. And there's this conventional wisdom that said if you have two algorithms, one algorithm does fewer operations, you want to choose the one that has fewer operations because it's going to run faster. But today that's not the case because of communication costs. So communication really has to be taken into account when we look at a comparison of algorithms. And floating point computations today can be dialed in at various levels. Traditionally, we think about 64-bit floating point operations and 32-bit. That's the way science has been done. Scientific computations have been done for many years. And today, we have 16-bit floating point operations. There's hardware that has 8-bit floating point operations, and even 4-bit floating point operations. Those lower levels are there not for the scientific guys, but for the AI application. So machine learning doesn't need high precision in their computations. They can get by with much shorter length of precision with it. And the hardware is there, of course, to meet that demand because of the increase in need for those kind of processors. So we see processors today that have even 4-bit and even 2-bit operations going on because of the cost associated with it. This is a chart that gives you a sense of how supercomputing has evolved over the last 31 years. So what we're looking at here is time on the x-axis and performance on the y-axis. It's on a log scale. The red is charting the #1 machine, the fastest computer. So the fastest computer today is the machine at Oak Ridge National Lab, and it's sitting here at 1.2 exaflops. The guy at the bottom of the list, just made it on the list, is 2 petaflops. So exa to peta, there's 3 orders of magnitude difference. This guy here is 1.2 times 10 to the 18. This guy here is 2.3 times 10 to the 15 operations per second. And that's running the benchmark. So running that problem, AX equals B, using a dense matrix computation is what's being reflected here. So there's a lot of interesting things that you can make out from this graph. We see this inflection point here. If you take a look at the trend lines, what's going on there? What happened there? Well, I think it's a combination of things. There's Moore's law slowing down. There's the Nard scaling ending. There was a financial crisis that took place, slowing down the purchasing of high-performance computers. So I think a number of things contributed to that. But again, tremendous advances in really a short period of time. Back in 1993, the #1 computer was at Los Alamos National Laboratory. It was used for nuclear weapons simulation. And that computer ran at 60 gigaflops, 60 billion operations per second. My laptop, this machine here that I'm using to give this talk, I can run the benchmark on. And I get 426 gigaflops. That's stunning. This is a computer I use mainly to read email. And I get a performance that outperforms the machine used at Los Alamos National Laboratory, which had 1,000 processors, which was used to do nuclear weapon simulation. Just incredible changes over a period of time. And my laptop would have been on the top 500 list. It would have been #1 back in that into perspective in terms of how the changes have evolved over a short period of time. All right, this is the list of the top 10 machines today. And the way to read this is the #1 machine is at the Department of Energy, Oak Ridge National Laboratory. That's a open science laboratory. So the Department of Energy has two kinds of laboratories, open science and defense related. So NNSA is the defense side. Los Alamos, Livermore, and Sandia do weapons research, classified work. Oak Ridge, Argonne, and Lawrence Berkeley Lab are the open science laboratories. All have high performance computers. We have the fastest one. Again, it's based on AMD parts. It's put together by HPE. HPE does not make processors. They're an integrator. They take stuff and put it together, and then we buy it from HPE. And our machine has 8.6 million cores in it, and it achieved a performance of 1.2 exaflops, 1.2 times 10 to the 18 floating point operations. And that was 70% of the theoretical peak. So the theoretical peak is a paper and pencil calculation. How many cores do you have? How many operations can you do per second? Multiply all the stuff together, and that gives you a problem on your machine, and you get something much less. And they got 70% of their theoretical peak performance. The machine uses 22.7 megawatts. So what's a megawatt? So here in East Tennessee, at my home, if I use 1 megawatt for a year, I'm going to get a bill from the electric company, and that bill will be for $1 million. So a megawatt year is $1 million. So this machine, to turn it on, is about $22 million just to run the machine, the power needed for that machine. That machine costs $600 million. So that's a small part of the overall cost of the machine. And you can see some of the other machines down the list here. I've highlighted the machines that use accelerators. So in this column that says computer, there's in red are the machines that use accelerators. Of the top 10 machines, 9 machines use accelerators. The only one that doesn't is this machine here in Japan. It's the Fugaku system. It's an ARM processor, and they've modified the ARM processor to have vector instructions. So this machine, in some sense, gets its performance by executing these vector instructions on their machine. And you could just scroll down the list here and see the percent of peak performance, 70%, 51% of peak performance for a machine at Argonne National Laboratory. In fairness, this machine is just coming up. It's a new machine that was just put on the floor, and they're still sort of shaking it down. But look at the power consumption, 38 megawatts of power in this machine, so it's a very hot machine. Some of the other machines, you can see the US has 5 machines on the list, Japan 1, Finland, Switzerland, Italy, and Spain round out the list. There are 2 machines that are provided by cloud vendors. One's Microsoft at position number 3, and at position number 10, the machine at NVIDIA is also used for cloud-based services. So they put together a machine, ran the benchmark on their cloud, and submitted it to us. This is a list. There are 500 dots on this list here. So the x-axis is listing position number 1 through 500. and the y-axis is giving us the speed of the machines. So you see the list is very, let's call it top-heavy, a hockey stick effect. We have a lot of machines at the lower end, and just a few machines giving us this very high performance. So if I was doing this list again, I probably wouldn't have 500. I may have 50 machines, because that really reflects what's being the top machines in terms of scientific computing. Okay, this is the machine at Oak Ridge National Lab. The peak performance of 2 exaflops, 20 megawatts of power. It's based on an AMD processor plus 4 AMD accelerators, and then it's built out using 9,408 nodes. The interesting thing is if you use 16-bit arithmetic, the short precision that's there for machine learning, the peak performance is potentially 11 exaflops. So using short precision allows the machine to run a lot faster, and you could exploit that if you have applications, scientific applications, that can use it, or if you're doing some machine learning training, you could also use it for that purpose. But again, 99% of the performance is coming from the GPUs, so you better be using the GPUs on this machine, or you get very little performance overall. And again, 8.8 million cores is what we see on this machine. So again, this is the chart of the #1 machine on the top 500. It's interesting to see the effects. So we reached a teraflop. So a teraflop is 10 to the 12 operations per second, and that was back in 1997 at a machine at Sandia National Lab in Albuquerque. It was called the Sandia Red Machine. 11 years later, we reached 3 orders of magnitude greater in terms of performance, and that was a machine at Los Alamos National Lab called Roadrunner. It used the IBM Cell processor, which was used in the Sony PlayStation. So that was the real driving force for performance on that machine. And then about 14 years later, we saw the first exascale machine, 3 orders of magnitude in 14 years. So it's taking longer to get to higher levels of performance. And a question is, when do we get to the next big threshold? Zettascale computing, which would be 3 orders of magnitude greater. And the projection is it's not going to be 10 years. It's going to take a lot longer to get to that point. We can't even make the projections at this point. China is rumored to have 4 exascale machines, but they haven't submitted the results to the top 500. They've been very quiet. Back in 2022, they had the most supercomputers. So this chart here is listing the number of supercomputers on the top 500 list. So China here has, I can't quite read that number, so it has 162, and the US has 125 machines on the list. So you see the difference. So China has invested in high performance computing. In 2001, China had 0 supercomputers on the list. So they made a tremendous investment to build up high performance computing within the country. More recently, China has stopped sending results for the top 500. So the US now has become more dominant. As machines fall off the list, the US is populating more machines on the list, and China has refused to send new entries into the list. So why have they done that? Well, the US has taken action against China in terms of limiting technology, and my guess is China doesn't want to have more restrictions applied to the acquisition of parts that they might use for high performance computing, or devices that they may use for making processors. So they've stopped submitting numbers to the top 500 list. But we know that there are 4 large machines in China that are being used to do their effective high performance computing workloads. One of those machines is specific for AI machine learning technology. So we've had this benchmark for a long time, this thing called the LINPACK benchmark. And it's been around since 1979, and a lot of positive features have come out of the benchmark. It shows trends. We get to understand how these machines perform on a certain problem. The problem has been fixed over time. We have the same kind of matrix. We require a certain kind of accuracy out of it. But a lot has changed since 1979. Arithmetic back in 1979 was very expensive, and today it's been over-provisioned. The expensive part is communication today, and this benchmark really doesn't take into account the communication. It highlights floating point arithmetic. And if I could put that in perspective, this algorithm does n cubed things with floating point arithmetic and only n squared data movement. So we get this bulk of the computational time being done with floating point arithmetic. So the LINPACK benchmark is no longer strongly correlated to what I'll say we do on our high-performance computers. Maybe it was back in the 70s, today it is not. And maybe we need something that better reflects what we do on our high-performance computers. And if you design a machine for a good LINPACK number, you're probably going to be imbalanced. You're probably not going to do very well on the standard applications that are run. So today's high-performance machines are used to do modeling. That modeling involves a partial differential equation. It's a three-dimensional partial differential equation. When you do the discretization of that differential equation, you end up with a system of linear equations again. That system of linear equations, however, is not the same. So the kinds of applications I'm talking about are climate, nuclear reactors, fusion, supernova calculations, material design, digital twins, and so on. All of those computations involve a three-dimensional partial differential equation, which we discretize, and we get a system of linear equations. So we have a benchmark that tries to imitate that, and this benchmark is called HPCG. It uses an algorithm called the conjugate gradients algorithm. The previous benchmark, the LINPACK benchmark, was a direct algorithm. You went through some number of steps, n steps, and you got a solution. No issue about that. That was the way it worked. This algorithm is iterative. So you iterate until you converge to a solution. The matrix looks something like this. So it's a large sparse matrix. It has this structure associated with it. These diagonals are full. The rest of the matrix is 0. And you do an iteration on it. The thing that we try to model is this 27-point stencil that is the discretization that we're following with the partial differential equation. We allow a preconditioner to be used in this partial differential equation to speed up the computation. And this is the results for this benchmark on the high-performance computers. I'm just listing the top 10. So the way to look at this is the winner in this case is this machine from Japan. It's called the Fugaku system. It's at Riken in Kobe, and it's based on that ARM processor that I mentioned. This column here is representing what we got using the LINPACK benchmark, the old benchmark, the one that did a system of linear equations using Gauss elimination with partial pivoting, the one that was very computationally intense. The new benchmark is HPCG, and it's not computationally intense. It has a lot of data movement. It does some computation, but the bulk of the time is going to be passing information around in order to do that iteration pattern. And the result of that is we see that we end up with the percent of peak performance being much less. With the LINPACK benchmark, we were seeing numbers like 70% of peak performance. Here we're seeing the best number at 3% of the theoretical peak performance. And some machines are getting 1% or less. So 1% or less, that's almost a shocking thing. So think about a race car, and think about a race car that goes 200 miles an hour. And driving gets only 1 mile, 2 miles per hour. You would be a little bit disappointed with the performance of that race car. But that's what's happening with many of the applications that are actually run on these high-performance machines. Very low return from the potential of these machines, and basically because of communication. Basically because the machines were not designed to do the kind of workload that's needed for scientific computing. We have an imbalance between the processor and the communication network. The communication network doesn't have the appropriate bandwidth or latency to match the needs of the applications that are done there. So it's really all about data movement. And we really need to think about building machines that can effectively move data through the system much better and have greater responsibility for that. So today, machine learning and AI have taken off. And there's a lot of research that's been done on these algorithms. So why has it been so, why has it just now become so important? There's a number of reasons. Well, today we have a flood of data that can be used for training. The whole internet can be used for training these neural networks. We have increased computational power, mainly coming from the GPUs of the machines. So we can do the kinds of computations that are needed much more rapidly than we could before. And we have better algorithms in theory based on machine learning that all sort of help in driving this to the place where it is today. And we have this increased support coming from industry. So we have this ecosystem that really supports our AI capabilities today. These are the companies that are involved in developing some aspect of that ecosystem, from hardware to software to specialized devices that are being put in place to help drive machine learning and computational science. But with machine learning, it's really about linear algebra. Again, it centers on small matrix computations. So looking at small, relatively small, 3 by 3, 5 by 5 matrix multiplications, dense matrix multiplications. And those GPUs do a great job, and they can get by with short precision in doing that. So today, our systems that we use, things like ChatGPT, are built in the following way. We have a model. That model may have 2 trillion parameters. We basically take all of the internet, scrape everything from the internet, take all the images that we have and do OCR on them to take the information and pour them into this training. And the training produces a model. That training is very expensive. It costs between $10 and $200 million to do the training. So think about ChatGPT or Gemini from Google. It cost about that much money to do the training for ChatGPT 4 to get it to the point where we can use it. So that's just the training part. And that's what we call a pre-trained model. So we take that pre-trained model and now we help it along. Oh, this is the indicator here which says what it costs for various models. So what I have here is different models and looking at the cost in terms of dollars that it costs to train the model itself, and looking at the number of parameters that are in those models. And again, we have these things, $100 million just for the training of some of these models, an incredible expense. So we take the pre-trained model and we help it along. So basically the pre-trained model is based on all of the internet, and you have something which has the education maybe of an undergraduate, and now we're going to help it along. We're going to push it in the right direction. We're going to make it so it works for certain areas, maybe looking at specialized data to help push it along. So we go and we fine-tune that model with some human input. So human input is there to push along questions and push along answers into the model so it gets things correct. So that turns out to be a less expensive thing, but it's time consuming. So that part of the process takes around $100 million to $1 million, $100,000 to $1 million worth of GPU time to get to that point. And then finally we have a model which can be used and satisfy your queries. So now we have a model that is like ChatGPT, where we can ask questions and get responses and carry on a dialogue that we can. And that's very quick. So that part of the operation doesn't cost very much. We've paid for the training on the upstream, and now we can get the benefits of it. Okay, so let me conclude here. I think I've used up my 45 minutes. The software, I'll say, always follows hardware in terms of development. Every decade or so, we have to redo the hardware, redo the software to match the hardware. And the hardware is put together with commodity parts in terms of scientific computing. And that leads basically to an imbalanced system. We don't have the resources in the scientific area to build our own hardware to match the needs of the applications like the hyperscalers do. So we have this ability to use short precision today. So in the scientific area, there's a lot of work going on trying to exploit that hardware that has increased capability, trying to understand if we can use 16-bit arithmetic to solve our problems, or get away with 8-bit floating point arithmetic. And those are research questions that have to be investigated. We want to ensure the integrity and make sure we get the right answers, but we want to see if we can exploit that. And again, I mentioned the old adage of things taking, of looking at the operation count and using that to project the time to solution. That's no longer true because of the communication layer, and we should be thinking about algorithms that go beyond the box, outside of the box. Look at algorithms that are what I call recklessly responsible, that try to do things which are potentially going to get into trouble, but we can detect when they do get into trouble and then back off and do something if they did get in trouble. But if they don't get in trouble, they can get to a solution very, very rapidly. So I'll end here, and I'd be happy to answer any questions that you might have. Thanks for your attention. Are there any questions?
Do you have any comment on why the optimization of the computing capabilities are so mismatched to like the HPGL?
Sure. So the mismatch is occurring. It's very obvious. You know, we have, when we buy a computer, again, we have a certain amount of money in the scientific area. I have $600 million, and I need this performance level. I need a performance level of 2 exaflops. So the vendors go off and put together a bid with that in mind, and they bid things, they want to make it as low cost as possible. So they use the commodity parts. They use commodity processors and interconnects, and those two things are mismatched. The processors are very fast. Communication can't keep up with the processor speed, and the result is there's nowhere where it's very difficult to get at the theoretical peak performance. So it's that mismatch. If we had infinite resources, we would do something called co-design. Co-design says we're going to get the architects together in a room with the application people and the software designers, and we're going to design a machine based on the needs of the applications. Everything is about the science. We're trying to drive science forward. That's why we buy these machines, and we should be looking at what the science needs in terms of getting the job done. So we don't have an unlimited set of resources, so we're stuck in some sense with this mismatch that occurs, where our friends over at the hyperscalers, they can invest and develop architectures which match the needs specifically for their problem and get a much better return. So it's a financial situation. Basically, if we had more money, we would do it right. We don't have the money, so we get what we pay for, in the sense of a mismatch.
Hey, first of all, thanks for the talk. It was really fascinating. So you were talking about how the HPC world use commodity stuff and the cloud vendors use their own custom hardware. Where do you think that's going to go? Like, will the cloud vendors eventually, like in some future, also use commodity, or will their solutions become the new commodity, or like, what's the convergence point for that?
Right. So let me just point out that you cannot buy processors from Google. You cannot buy processors from Meta or from Amazon. They don't sell their processors, they sell the services. So you can't go out and acquire what they have and put it in place. You could just buy their services. So why don't we do that? Well, if we do a cost analysis, it's at least a factor of 2 greater to buy cloud services than to use our own computers. That's the rationale that people have put together for that. So we're going to buy our own machines. So where is this driving the industry? So you could see that NVIDIA has this incredible demand for their parts today. And that's being leveraged by machine learning. Machine learning doesn't need large accuracy. So NVIDIA is putting in place small, short precision, very short precision to meet the needs of machine learning. My concern is that NVIDIA will throw away the ability to do 64-bit floating point operations, or 32-bit, because it's not needed for machine learning, and that's where their bread and butter is. So they may abandon, I'll say, what we do in scientific computing, and that would be a mistake. Or they may have a SKU, they may have a version of it, but it's going to be very expensive to get that SKU. So that's a concern that I have in terms of how the industry is going. And I don't know what can be really done to prevent that, but research is needed in terms of trying to exploit the precision that we do have.
Thanks, great talk. Just one question. Have supercomputers ever been hacked?
Hacked? Oh gosh, of course. Yes, of course they've been hacked. Yeah, so it's like any other computer. There's protections in place, and if you're doing classified work, there's an air gap between the computer and the outside world, and things are confined in that machine. But computers can be hacked, and many accounts are on machines, and those accounts could be fall into the wrong hands, let's say, and people could use those computers for doing things they shouldn't be used for. But they have some checks on that, and they could spot it, I hope. And yeah, so hopefully people aren't to do Bitcoin or something else like that. Yeah.
Dr. Dongarra, this is an absolutely fantastic talk. My name is Adam Thompson. I'm with NVIDIA. And I think one of the interesting things about this community is we're dealing with essentially edge-based sensors which vary in size, weight, and power. So sometimes you're dealing with like massive radars or big phased arrays like radio telescopes. And so as we're trying to put this real-time, high bandwidth, low latency data and have integration with something like a supercomputer for a digital twin or simulation or just crunching numbers, how do you view that the modern supercomputer needs to change to keep up with this deluge of data that has real-time requirements coming from the edge?
Right, so edge computing is an important aspect to how we do business today. We think of a lot of data coming from the edge, and we need some way to filter that data. So we need processing that will allow us to reduce the volume of data and then push that data upstream from the edge to the computer. Intermediate computers along the way where we do processing on the data and again trying to reduce or filter the information as possible before we push it upstream to the supercomputer and do the final crunch. But yes, edge computing is an important aspect. It's another one of these important changes, revolutions that have taken place and will have and continue to have tremendous impact on computing and how we use the total ecosystem that we have to get us to a better solution. Hi. We got microphone problems.
Hi, thank you for the presentation. Of all the supercomputers you listed, almost the majority of them were like x86, based. Except for the one, I believe Japanese machine. Do you see ARM architectures being pursued in the future to any degree, either for power or efficiency's sake?
Okay, so ARM. So what do we have to choose from? We have x86 architecture. We have ARM. We have RISC-V architecture. We have perhaps some others. The Chinese, by the way, in their supercomputers, they have totally different, they design their own stuff. They were forced into it, so they're not using Western technology. They're building their own technology, which is quite different. So, you know, those are potentials. ARM, the way it's being used for high-performance computing is not low-powered. So don't think of cell phone ARM. Think of an ARM processor which has a lot of power associated, a lot of the ability to solve more challenging problems, and is being used for that. So the Japanese machine, while it uses ARM, is very it's in the mix with the others in terms of the power consumption. So you're not getting any real benefit from the stuff we have on our hip. We're getting the benefit because it's a different architecture. We could then modify it easily, and in the case of the Japanese, they put a vector extensions in it, which gives them a boost in terms of performance. But having said that, there's only a few machines today which use ARM processors, a handful or two handsful of machines on the top 500 list. There are no RISC-V machines on the list. I would expect that to change in the future, but that's the world that we live in today, where it has a dominance from Intel's x86 instruction set. AMD and Intel share that and produce machines in that space.
So looking at programming for these devices, it feels like it's getting more complicated, and I as a developer have to understand more of the CPU architecture, the GPU architecture, the data buses, the memory architecture, and it feels like maybe software isn't and the tooling isn't keeping up with the hardware. So I was curious on your take on that and where you see that going.
Right, so I'm a software guy, so I'll say that we always have to follow the hardware, and that leads to many problems. My image of this is every 5 years, a new supercomputer gets thrown over the fence, and the application people and the software developers scramble for the next 4 years trying to figure out how to use that machine. And after a 4-year period, we do a pretty good job of matching the applications, and then another machine gets thrown over the fence, and we have to start that process over again. So we're constantly in a mode where we're redoing things to match what we see in terms of the hardware that we have. We don't have that co-design. So if we had a situation where we can get the architect together with the application people and the software designers, we might be in a better position to design a machine that fits the needs of the applications more tightly. But unfortunately, we don't have that at our disposal. And you know, hardware design is expensive, so it's not a surprise that we don't have that. I like to think in the old days, we had a lot of research projects at universities that developed hardware that allowed one to have experiments. I can remember back at Illinois having the Iliac 4, or at CMU having an experimental machine, or at New York at the Courant Institute having the Ultra computer. So there were a number of these experimental machines that were paid for out of research, and we don't see that level of machine development today. Of course, there's architecture research going on, but not at the level of building a machine that's intended to experiment with an architecture that's really new. So the hardware, and we need to figure out some way of matching that. Think about 8 million cores. How are you going to program that? You can't have simple loop level programming for 8 million cores. A fork and join doesn't work in that environment. You're going to spend all your time waiting for that synchronization to occur before you carry on the computation. So we need different models that can accommodate the levels of parallelism that we have, and different ways of, our trick in computer science is to encapsulate things so we can use those encapsulated versions in our applications.
So thank you again, Dr. Dongarra. Fantastic insights here from a true pioneer in the high-performance computing space. So another round of applause, please.
Thank you so much.
And GNU Radio Project would like to give you a small token of our appreciation.
Oh, very nice. Thank you so much.
And we also have the highly coveted 2024 GRCon 24.
Oh, wear it proudly. The medal, that's right.
All right, thank you again.
Thank you. So I'll be thrown off the stage. Sorry. Let me give you back this. Still alive.
I'll just use this one. Do we have the project talk slides? All right, well, I'll take this moment. Welcome again, everyone, to GNU Radio 2024 conference. There are some open seats. We have a full house here for everyone watching on the live stream. So there are seats scattered around. Please raise your hand if there is seats nearby you, so those waiting around can see. Okay, so yeah, you just have to make your way in here. One thing I want to mention right up front, all the information about the conference is GNURadio.org/grcon24. So all the logistics, information about the ham radio exams, the CTF, things going on this week, obviously the schedule. So head over there. Couple of things I don't believe are in the slides, but I don't want to forget to mention. One is lightning talks. We have lightning talks on the schedule throughout the week, and so signups are over at the registration desk. We also have merchandise for sale over at the registration desk. With the GNU Radio 24 t-shirts came, and they are fantastic this year, so take a look. I believe they're maybe $25. All right, so just in a moment for us to get these slides set up. And yeah, thank you. Again, apologize for the technical glitches here. We'll get right to it as soon as we can. Sorry. That's good. No. All right. Apologize, everyone, for the slight delay here. So we'll get started. Welcome, everyone, again. My name's Josh Morman. I'm that laptop. Which one is that? Clicker one. Clicker one. All right. There we go. Perfect. So, my name's Josh Morman. I am the president of GNU Radio and also research scientist at Peraton Labs. So let's take a look at what's going to be going on this week and a perspective from the GNU Radio organization and project. So today, obviously, is Tuesday, start of the conference. So happy to see a full house here today. And we have an exciting lineup of events, talks, keynotes, workshops, everything on the website. So please take a look. Food and beverages will be served in the expo hall behind me here. So that is ballroom C. So we will have AM and PM breaks. AM breaks 10:45-ish, PM breaks 3:30-ish, I believe, and then lunch each day over there as well. So that gives it's been a good arrangement to have the lunches and all the food in the expo hall. Gives us a good opportunity to interact with our sponsors and our vendors. We also, let me go back, we also have social events on Wednesday night and Thursday night, so hope everyone is able to make it out. I will talk a bit more about that in just a second. So please join the chat. So everyone on the live stream, we try our best to get some questions in over the chat. There is a space, a public space, grcon24. So if you go chat.gnuradio.org and go to the grcon24 space, all the rooms of interest are listed there. And I think there's a backstage room for the presenters. There is a talks page to ask questions and interact about the ongoing talks. So please hop on over there. And our chat server goes on throughout the year. So that's the best place to kind of stay engaged with the GNU Radio community. We have an excellent lineup of keynotes, so thanks again, Jack Dongarra, for that excellent keynote this morning. And we have keynotes the rest of the week. So we have Shahar Shremian, Phil Erickson, and Christina Collins on Wednesday, Thursday, Friday. Capture the flag. So Clayton Smith is running our Capture the Flag yet again this year. So he runs an excellent competition. There is a Capture the Flag room, again, in the workshop rooms right down the hall behind me. I believe it's 301A. It's labeled Capture the Flag. And that has kicked off online. So check out the GNU Radio X feed or the GNU Radio Fostodon feed for all the information there. And he will be giving information later today about in a lightning talk about the Capture the Flag. Ham radio exams. So we have ham radio exams on Wednesday. So show of hands, who here has a ham license? All right, that's about half the room or so. So if you don't and you're interested, sign up for ham radio exam, $15 cash due to the examiner at the room on Wednesday. We have an excellent lineup of workshops this year. So there is Basics of SDR. So this is a new workshop from Paul Komitz from University of South Carolina. The RF knock workshop, which is always very popular, Neil Pandya. Getting started with GNU Radio in the classroom. This is a new workshop from Neil Rogers. We'll talk about a bit more about that in a bit. An introduction to RF processing for satellite constellations. We also have 2 invited workshops from Dan Boshin, who is very active in the online signal processing community. So he has 2 workshops this week: Fast Track to Designing FIR Filters with Python, and Quick Start on Control Loops with Python. So there's an opportunity there to get some in-depth signal processing background material. If you are joining either of those workshops, go to the schedule on GNUradio.org, and there's some setup material that you might be interested before attending the workshop. So it's attached to the item on the schedule. So tomorrow night, we have a social event at the Sun Sphere. So if, I'm guessing a lot of you before you came here, only knew of Knoxville from the Simpsons episode. So this is the Wig Sphere right here behind us. And it is 5 to 8 p.m., and we will have drinks and hors d'oeuvres. And then Thursday is our main dinner social. So that is going to be further downtown, and this is going to be dinner, drinks, and bowling. So I've heard rumors that Sam is already setting up a tournament. So hope everyone can come out to that and really beat me in bowling. I want to thank all the organizers of the conference. So Samantha Palazzolo is our lead organizer. We have Barry Duggan, who is back here at the AV booth and who's put together quite a setup. This year, I want to particularly note the live captioning is done by Maestro, and that is much more accurate than we've seen in the past in terms of captioning. So a very, very impressive setup. So if you are interested in seeing the captions, they will throughout the week be done over on this north side of the ballroom over here. So Toby Flynn, Seth Heightfield, Andre Rode, Marcus Mueller, and Neil Pandey, and myself have worked throughout the year. So I want to thank everyone who registered early for the conference. So, every year we get this big burst of participants registering at the very end. Always helps us out if you can do that earlier. But also anyone interested in being involved in the conference organization next year. On Friday, we're going to have a planning session and kind of get a jump start. Hopefully get, a few folks stepping up that want to join the organization team, some ideas where we might want to have the conference. I know we're just starting, but already looking towards next year. This conference absolutely would not happen without our sponsors. So we have a great lineup of sponsors. Most of them are set up in the expo hall. So take a look at their booths, interact with them, see what their new products, and a lot of them are recruiting. So our diamond sponsors this year, Ettus Research NI, which has been a sponsor here for many years, perhaps the entire, the conference back to 2011. And we have a new sponsor in person this year, Aronia AG, who has a very impressive booth set up in the expo hall. So please take a look at their products. Our platinum sponsors, we're fortunate to have Oak Ridge so nearby. They have been instrumental in helping plan this conference, and Analog Devices as well. Our gold sponsors, we have Epic, Paraton Labs, Deepwave Digital, and ARDC, which are all returning sponsors. And our silver sponsors, we have Redwire, Amona Thames, DeepSig, B-Cubed, Impulse Space, RFNM, and AnySignal. And then we have patron sponsors Coherent, Andro, Timtech, and Doug Forster. So we appreciate all of our sponsors. Again, this event would not happen if it was not for our sponsors. So let's get into an update from the GNU Radio community. I will try to keep it short here so that we don't eat into our break too much. But first, really, what is GNU Radio Project? I stole this slide from Derek. It was in his presentation last year, but I think it accurately represents, or it brings across the idea, GNU Radio is so much more than just the code base. GNU Radio is this community. It's all the events we're able to run. It's all the supporting code bases. So GNU Radio is all the things that help push the state of open source SDR and all the people that come together to make that happen. So GNU Radio Project is you. It's all of you. It's everyone that contributes, participates, and uses GNU Radio. And that cannot be underemphasized, or can't be overemphasized, sorry. So we're seeing more and more GNU Radio usage outside of the traditional spaces of wireless communications. You're going to hear talks throughout this week all sort of scientific domains. And I guess our most recent addition here, particle accelerators, we're definitely going to hear more about later in the week. But do a quick search on Google Scholar with GNU Radio, and you see it is used in all sorts of fields. So GNU Radio is the tool for providing innovation in scientific applications, and is becoming more so. So the actual GNU Radio software that you're able to install, we have put out periodic releases through the year. This has been very consistent the last 3 or 4 years, thanks to our maintainer, Jeff Long. Every quarter, like clockwork, this year we've gotten out the 3.10.8, 3.10.9, 10, and 11 releases. And that is due to very diligent and active maintaining. Unfortunately, Jeff is stepping back as a maintainer, so we are looking to expand the maintenance team. I have a slide on that in just a second, so I'll come back to that. 3.10.9, which came out in January, that is the release that if you have Ubuntu 24, this rolled into the Ubuntu 24 cycle, thanks to the work of our packagers, specifically in the Debian sphere, Maitland Bottom. So if you get a chance to meet Maitland this week, he is the reason you are able to type in apt install GNU Radio, and it just works. So, you know, if you've been involved with GNU Radio in the past, it used to be a much bigger deal to get GNU Radio running on your system. And now, download Ubuntu, apt install GNU Radio, and you are good to go. So a lot of work, and there's also the Radio Conda ecosystem that Ryan Voles at Haystack, and many more. There's a lot of people that we don't necessarily interact with directly, but a lot of packages that just show up in these other ecosystems. That it's just a big part of what makes GNU Radio powerful. So I mentioned before, we are looking for additional maintainers. If you're interested in this, please talk to me. Please talk to Marcus. Raise your hand, Marcus. We would like to have an info session sometime this week. We haven't put that in the schedule, but stay posted. But if you are interested in getting involved, you know, not necessarily taking on the entire thing, right? That's a heavy lift. We want to build up a team of people that are able to review the PRs, push the PRs in specific areas, have experts in, you know, say that you are the GRQT person, you know, that would be great for you to take ownership and manage all of those PRs. So please let us know if you're interested. So how is GNU Radio governed? So GNU Radio, we have, actually, I'll skip to the next slide first. Well, the next slide first. We have a General Assembly. So there's really about 17 of us involved in the, we have a couple times a month we get together and determine the status of the project, what needs to happen, and it's out of this group that we elect the board. So the board right now is Mark Lichtman, myself, Mark Lichtman, raise your hand back there, myself, and Martin Braun stepped back from the board, but we will have an upcoming election and fill that seat soon. We are also aligned with the SETI Institute. The SETI Institute manages all of our finances. They also help us with logistics, the things, you know, to get us to be able to run this conference. So Derek Kozel on the GNU Radio side is the PI for the SETI Institute, and we also have representatives from the SETI Institute here, so please chat with them this week. We try to organize ourselves in the organization around teams. So things like the GNU Radio conference, we have a group of organizers. and we'll see updates through the week. I don't want to get too deep technically into GR 4.0 because I will definitely not get that message across effectively. But there are some highlights I want to point out about GR 4.0. We're trying to set up GNU Radio in a way that it can be used more in deployed real-world applications. And for Ralph's case, and this is what we want to open up, is it can be used in critical infrastructure because it is built with these things in mind: a lean code base, modern C++ and best practices, and type safety. Things like that, enable it to pass the types of security audits that we'll need to in some of these scenarios. Also, by using modern compilers and some of the things, again, I encourage everyone to watch the EUGR Days talk and Ralph's talk, but some of these things that will boost the performance of this framework by relying on the compiler to do more. And also improved usability features, customized schedulers, a simplified block API, and another kind of ongoing conversation that has been mentioned in project videos in the past is more liberal licensing. So we are gearing the core of GNU Radio 4.0 right now to be LGPL. So we haven't finalized that, but that is the direction we're moving. So again, how do you get involved? How can we push GNU Radio forward? We need partners in the community to work with the code base, build applications on top of it, and push the lessons learned back into the core. So one example of this, so I didn't mention this in the EUGR Days overview, but we were able to fund Danny Estevez to put together a fully functional packet modem, and he knocked this out. Danny is amazing. But he put together a fully functional packet modem, and we're in the process of getting kind of apples to apples numbers of performance comparisons, but there is kind of a baseline implementation of wireless communications protocol in place that is out there. It is the GitHub link is right there. So take a look at it. Danny has interacted very closely in the architecture chat. So the second point of our vision is spreading the footprint of GNU Radio. We want more people. Obviously, we want more people using GNU Radio because the more people using it, the more people are able to contribute back. Kind of two aspects of this. One is just making things as accessible as possible, and two, we see a big opportunity in the university and community college, high school space, and education to have GNU Radio available in those types of courses. So a couple things I want to highlight going on both at the conference here and in the community. One is there is a workshop on Thursday. Neil Rogers, who's a professor at the U.S. Air Force Academy, is going to be giving his insights into how he has used GNU Radio in the classroom, the benefits of it. He's written a paper that is also going to be published in the GNU Radio conference proceedings. So look forward to this workshop. There is a talk on, I can't see it from here, but this week from Vishal and Simon Steele about an ARDC-funded GNU Radio-based community college curriculum. So this is something that's kind of packaged up and ready to go to be adopted at community colleges using GNU Radio to teach radio astronomy. So we'll hear more about this week. Also, another exciting development, Jean-Michel Friet and I can't see the name, but have published a communications textbook, an academic textbook using GNU Radio for communication system engineering. So this is available for pre-order on Amazon. So take a look. If you are in the academic world and think this could be useful, definitely reach out to Jean-Michel, but it's available for order. We also have a chat room specifically for educators, so that's something where we hope that people involved in this space can connect, share information, and help promote the use of GNU Radio in the classroom. So the last point of our vision is sustainability. So right now, GNU Radio is a fully volunteer-based organization. So everyone that you see in the leadership, in the organizers, is a volunteer. Something I should have mentioned, if you see someone with a white lanyard, that means they're part of the leadership or the organizers. So we've promised to be nice so you can ask us questions. So encourage any questions to come here or the registration organization desk. But we would like to, in the future, move towards beyond a just volunteer organization. We want to be able to pay people to develop things, have more administration so we don't burn out our volunteers. And that involves more partnerships, more avenues for funding. How is GNU Radio funded right now? Well, we run this conference, and sometimes we end up with a little bit of money at the end, so that's great. That allows us to keep the servers running. We have the ability to receive grants, so those are processed through the SETI Institute. And there's a couple things we've done in the past I'll highlight, and opportunities going forward for anyone that's interested in taking on the work for a small-scale grant. We also receive donations. Part of that is through the conference, but we also receive donations from the website. And ... we want to get to the place of sustainability in the organization. Small development grants, NumFocus is one avenue, so take a look at that. We keep a list of grant ideas on the wiki. And then ARDC is another great avenue for, they're highly supportive of folks that can do projects within GNU Radio, outside of GNU Radio, that promote their goal of amateur radio, scientific research. Education is a big component of that. So ARDC, sponsors of the conference. So if you are interested in doing work that would be grant funded, please talk to us, and we can help put you in touch with ARDC, or we can do that collaboratively. So we have, over the past couple of years, been working through an ARDC grant that has been focused on GNU Radio usability enhancements. So I've given updates on these topics before, so I won't go into detail, but some of these things, they relate to documentation, moving GRC onto Qt-based dependency rather than GTK. So that is about keeping GNU Radio healthy, or GRC healthy going forward, and also making GNU Radio more accessible through clickable installers, signed installers. That's the goal. That you can go onto Windows and double-click GNU Radio install.msi, and so that is some of the things that we're working through with this ARDC grant for improved usability. Joining us this week, tomorrow, is Frank Howley, who is the Director of Corporate Engagement at the SETI Institute. So Frank is going to help us establish a GNU Radio Industrial Advisory Board. So the goal of the Industrial Advisory Board is to help us support the continued maintenance and expansion of GNU Radio with the help of paid sponsorships and I guess it's pretty self-explanatory, an industrial advisory board, right? We want to set up something that's going to ensure the long-term financial stability of the organization. So Wednesday at 2:30 in the main ballroom, he will speak briefly, introduce the idea, and also we will have an intro session, an info session right over here in the rotunda room, which is in that back corner over there. So if you are interested in learning more, this would be a great way for your company to get involved with GNU Radio. Other ways you can support GNU Radio, we've talked about. Get involved. Tell people that you use GNU Radio. If you're able to, publish something on a blog somewhere, social post, write a letter of support, publish white paper. Also get involved more tightly with the community and the team and the chat. So we want more and more people to get involved, and we appreciate everyone being here. I think that's all I had. Are there, I think we probably have time for one question if there's any questions. We got Barry.
Hi. Can you hear me?
Yes.
Yeah. First of all, I'd like to apologize to the people watching on streaming. We have video problems, and we will work on that during this break. For the in-house people, same video problems. We're getting the captioning without the video, but we're working on that, so bear with us.
So, and I would like to give a round of applause for Barry, who has really taken on this really heavy lift. So we are very fortunate to have Barry in this community, and does a tremendous volunteer effort, like not just with the AV. He picked up so many of the pieces of the organizing of this conference overall. So we don't know what we would do without Barry for this year's conference. Yeah, Sam.
And I just wanted to say, as one of the lead conference organizers, you know, Josh, as he said, I hope you see, we're all about in GNU Radio getting participation from our community as much as possible. And for those of you attending in person or online, feedback is really helpful. Please use the email. You know, we have a bunch of our team reading them. Ways that you can, you know, help improve this conference going forward. And we're always looking for organizers. So feel free to reach out to anyone with the white lanyard. Thanks.
All right. So thank you, Sam, and we'll take a break here. Hopefully, sort out some of the issues we're seeing, and come back here at 15 minutes, 11 o'clock. All right. Thank you, everyone.
Food is in ballroom C.
Oh, yeah, ballroom C. The snacks and coffee, the room right behind me. See it pretty decently from here, and you probably know your car.
Yeah, I know. And someone's going to take them out. Or, I sent you an updated version. Okay, hi. Yeah, so my name is Greg Hellbourg. I'm Institute of Technology in California, and I'm also the spectrum manager of the Owens Valley Radio Observatory, which is a radio observatory owned by Caltech, which I'm going to present in a couple of slides. But I wanted to start off this talk showing you this image, which is an image of the center of our galaxy. This image has been produced by a radio telescope called Meerkat. It's a telescope that is in South Africa, in one of the most quiet, radio quiet areas of the world. And the reason why I'm showing you this image is not because it's beautiful. I mean, it is beautiful, and it's great to see, and to see what radio astronomy is about. But it's also to motivate the reason why we're doing radio astronomy. There's no way we would be able to produce such an image with optical astronomy, because there's just too much dust, stellar dust, in the middle of our galaxy. So pointing optical telescopes towards the center of our galaxy would not show anything. And this is what radio astronomy is all about. Now, going back on Earth, what do we do with radio astronomy? So we have those big dishes that you probably all have seen in movies and documentaries, and you've seen images of. And we turn those telescopes towards the sky, and what do we get? Well, we don't get much. Because although the emission processes, the astronomical emission processes are very energetic, right? It's high energy processes that are in place. Well, those emitters, if you will, they are really far away from us. So we get a lot of attenuation from those signals through large distance propagation, but also because the universe is not completely empty. It has lots of interstellar medium, intergalactic medium, even between galaxies. And even our own ionosphere has a tendency to absorb and filter out some signals. So we don't really look at astronomy the same way as communication people look at RF signals. In fact, we don't really even use the watt as a unit of power. We talk about astronomy energy as spectral power flux density. And we have our own unit to describe the power of a source, which is the Jansky. And the Jansky is 10 to the minus 26 watts per square meter per hertz. It's named after Carl Jansky that we see on the right of this slide, which was the kind of the first discoverer of astronomical radio emissions. And I like always to put everything in perspective with this Jansky, the unit, to tell you how weak of a unit this is. So I like to think of what if we're using a cell tower to look at a 1 Jansky source. Okay, 1 Jansky source is a pretty bright source in a radio astronomy, all things considered. So if we were to use a cell tower, so if we're observing, for instance, this 1 Jansky source with a 5 megahertz bandwidth and at a 880 megahertz frequency, then the signal that we would effectively see, assuming that the antenna is isotropic, would be of the order of minus 183 dBm. That's how much power that 1 Jansky source would produce at the output of our antenna. The typical cell tower sensitivity, how a cell tower is capable of detecting detecting a user equipment, cell phone, is roughly minus 90 dBm. So we're like 90 dB below that threshold of sensitivity. Very, very weak signals. And this is for a 1 Jansky source, and current telescopes, they observe micro Jansky to nano Jansky sources. So we're a few orders of magnitude even weaker than that. Now, how do we do for building instruments that are sufficiently sensitive to these kind of sources? Well, we do have 4 main characteristics, 4 parameters that we use to tune new generation radio telescopes depending on what kind of science we want to do with those telescopes. The 4 parameters are the noise temperature of our receivers, and to reduce that, to optimize that noise temperature it's often water or cryo-cooled receivers that go down to a few kelvins of system noise in our receivers. Another way we increase the sensitivity is by using large collecting areas. Right? We have like very large single-dish telescopes, such as maybe you're aware of Arecibo, that doesn't exist anymore, but used to be a 300-meter dish radio telescope, so that's a massive dish antenna with very large collecting areas. China built the 500-meter dish telescope called FAST. But there's also a new trend of building arrays of telescopes, which helps us producing cheaper to maintain and easier to maintain in general. Dish telescopes, but a lot of them so that the collecting area is still very much preserved. Then we have integration time. And you can think of radio astronomy observations like the exposure when you do photography, right? The more you expose, the lower the noise becomes. And we can do exactly the same in radio astronomy. But instead of having exposure times of, I don't know, like a few milliseconds, we use seconds to hours to sometimes weeks of observation. But it's okay because what we're observing, it's usually stationary signals, stationary in time, which means that whether you observe it today or last week or next week, things will not really change. So we can actually effectively observe things for weeks, even split into different time chunks. And finally, another very important parameter that we exploit is the bandwidth of our receivers. The great thing about radio astronomy is radio sources, they're wideband in nature, right? Nature doesn't produce narrowband signals. So whether we observe it over 5 megahertz, 10 megahertz at like very low frequency or very high frequency, the astronomical signal that we're trying to find, that we're trying to observe, will emit at all those frequencies. Depending on what kind of source it is, some region of the spectrum might be more appropriate for detecting some signals, some of those sources. But basically, there's never too big of a bandwidth for our receivers. That's why nowadays we're working with a few hundreds of megahertz of instantaneous bandwidth receivers to even a couple gigahertz for the widest receivers that exist. The problem, of course, is that as radio astronomy users, we have to share the spectrum with active users, right? We're completely passive, we don't transmit anything, but we have to deal with people who transmit things at other frequencies. And radio astronomy has some frequencies that are allocated to the radio astronomy service, which you can find in the ITU documentation. I'm sure the ham license will touch on that as well. But basically, less than 3% of the spectrum under 30 gigahertz is allocated to radio astronomy. It's not much. So it is common practice for us to observe outside of those bands and have to deal with what we call radio frequency interference. It's not interference from an FCC point of view, from the regulator's point of view, because those signals are allowed to transmit. But it is interference for us because it's just not a signal that we want to observe, right? So we're very used to passive spectrum sharing. So I mentioned the Owens Valley Radio Observatory, which is the radio observatory that I work for. I'm on campus at Caltech, so near Los Angeles. But our radio observatory is far away from any big metropolitan areas. It is located, it's this red star on the map of California. So very close to the border with Nevada. And we're in a valley, and valleys are great for radio astronomy. The reason for that is that the mountains, the surrounding mountains, offer a proper, natural RF protection. So, even though we are far away from metropolitan areas, we have also this protection from the mountains, surrounding mountains. It's not exactly a radio quiet zone. We have a couple towns, Bishop and Big Pine, California, that surround the observatory. But it's not that much of a concern currently. Our observatory runs many different experiments and instruments. We have some instruments that are science-ready, but our university is also a technological university, and we do a lot of research and development for new instrumentation. So this gives you a little idea of, a good idea of what experiments run at Ovro. In the lower spot of the spectrum, between 0 and 100 megahertz, we have the long wavelength array, the LWA. Then on top of that, around in L-band, so above 1 gigahertz, we have the Deep Synoptic Array 110, which we're going to talk about longer later. We have a solar array, the Expanded Owens Valley Solar Array, EOVSA, 1 to 18 gigahertz, 500 megahertz of instantaneous bandwidth. We have a large 40-meter dish, and we have a CO mapping array. And we used to have the Karma array, which doesn't exist anymore. It's been decommissioned and removed, but our observatory used to go up to 265 gigahertz in frequencies. So as I mentioned, we work a lot in research and development at Caltech. And there is a shift that we're kind of trying to investigate. We've been trying to investigate since 2013, which is, back in the days, we used to build telescopes, like perfect telescope, very clean, very pre-calibrated, and have a simple digital receiver, even analog receiver in even older times, but simple digital receivers that would produce like spectra that are great. Like no need for calibration. Everything is taken care of because the quality of the antenna is so great, but very expensive. But as we've heard previously, Moore's law just keeps increasing. The number of transistors, the amount of computational power available, and the cost of the computational power. So our concept is, what if instead of building those very expensive telescopes, we just use off-the-shelf antennas, dish antennas, like satellite dishes, and a lot of them, and all the signals plug into massive GPU servers. And we take care of the calibration and the corrections of the data just using algorithm, right? And this is what we've been working on. So in 2013, we had our first dish that was just built as a prototype to measure, noise properties of the receivers and see what are the limitations, how many antennas would we need to reach the right sensitivity to produce science. 5 years later, in 2017, we had the DSA-10, which is 10 antennas, just incoherently summing the data of all these antennas. These were like literally ordered on Alibaba.com. I think they just arrived in California. We set them out, and they wouldn't move. There's no motor, nothing. They just point at the sky, incoherently sum together. We get great spectra. We detect what's called fast radio bursts, which are transient astronomical signals. That's great. A couple of years later, 2019, we completed the DSA 110. So this time it's 110 antennas, 4.65 meters in diameter. And we're still tracking those fast radio bursts, but it's not just a matter, at this time, it was not just a matter of detecting those fast radio bursts, it was also a matter of localizing it. And if you don't know what fast radio bursts are, I'm sorry, but I will not talk about that, but it's a very important subject in astronomy. It's basically, we don't really understand those effects. It's just very bright pulses that are detectable. We just don't know where they come from. So detecting is one thing. Localizing them is something that's even more important. And then DSA 2000, which we're going to talk a little bit longer later. DSA 110, well, as I said, it's 110 antennas. That's what it looks like. Actually, that's what exactly it looks like. There's like a massive T of 95 antennas. That's the yellow T at the center of our observatory. And then we have a lot of outriggers. And basically what we do is we beamform the data from the from the 95 core antennas to get high sensitivity capability towards the sky to detect fast radio bursts. Whenever a fast radio burst is detected, then we download roughly a couple seconds of data from all the 110 antennas. We correlate them and we image the field. And from this imaging process comes localization, because we're going to detect where that blip of color, of energy comes from, basically. So that was our main driver. But then it's achieved, it works, it's operational, and now our next challenge is the Deep Synoptic Array 2000, DSA 2000. So this time, it's no longer 110 antennas, it's 2,000 antennas. And the motivation, the scientific motivation for this telescope is to be a survey instrument. So there's another paradigm shift happening in radio astronomy, which is instead of building telescopes that are what's called PI-driven, which means as an observer, as an astronomer, I can apply for time on telescope, and I say, okay, I want to do this kind of science. I'm going to be the sole user of that telescope from this time to this time, and I do whatever I want, and I own the data, and I publish them, and that's it. Now what we want to do is produce survey data, which means we survey the sky. We produce data that are useful for any kind of science, or as most science as possible. In fact, we want to maximize the amount of science achievable per bit of data, if you will. So survey instruments, they have two characteristics that are, that kind of characterize the survey instruments, which are the sensitivity and the survey speed. So the sensitivity is how weak of a source can I detect with my telescope, and the survey speed is how much time do I need to detect that source. And so this diagram shows a comparison of a few edge instruments that exist right now, and it shows the survey speed versus the sensitivity of survey instruments. And we want to be on the top right of this diagram, right? We want to be sensitive and we want to be fast at detecting sources. To do so, we're building 2,000 antennas, dish antennas. They're all 5 meters in diameter. They're in a pretty dense core formation footprint. We're covering 700 megahertz to 2 gigahertz, which is another reason why we're so sensitive. It's because we're in the most sensitive region of the spectrum from a radio astronomy standpoint. We're going to achieve 3.3 arc-second resolution, so the footprint of the array is 19 kilometers by 15 kilometers. It's huge. We've been surveying a lot of valleys in the US to put this telescope. So the telescope is not built yet. We're planning on starting building it in 2016, but this is where we're at now. So the reason why we have 2,000 antennas, it's very interesting. There's no way for us to store the data of 2,000 antennas, because what an interferometer does is it correlates the data between all the antennas together, right? So when you have 2,000 antennas, that means that effectively you have a 2,000, in fact 4,000 by 4,000 matrix per frequency channel. You might have like hundreds of thousands of frequency channels, and these correlated data, you can either produce them every second and store them and have someone years from now trying to image this, or we can try to image in real time. And this is what we're trying to do. We're trying to build a radio camera, so a camera that effectively in real time produces an image of the sky that is of scientific relevance. So 2,000, the one advantage of having 2,000 antennas is what we see on top is the very large array, 27 antennas in a Y formation. And you can imagine the VLA, the very large array, as being like a CCD matrix of a camera that has only 27 pixels and in a Y shape. Well, there's going to be an artifact which we call the point spread function. It's like the telescope response to the data, which we see. That's the second plot right to the right of the image of the very large array. And basically, when we image the sky with this telescope, what we're going to get at the output is the image of the sky convolved with the point spread function of our telescope. And it's very dirty, as you can see. That's the top right image. And to actually do science with this kind of image, what we need to do is run a heavily complex and heavily nonlinear as well algorithm that does a deconvolution. So we roughly estimate the point spread function of our telescope, and we deconvolve that point spread function from our image. When we have 2,000 antennas, this is the bottom row, our point spread function is pretty much a Dirac. It's a 1 pixel. And we produce images of scientific relevance right away without having to deconvolve anything. So we also, not only we want to be fast and sensitive, but we also want to do it cheap. So cheap as in the cost of a single antenna should not exceed $25,000. And this includes receiver, all the equipment, and also the RF over fiber drivers and everything. So we do have a structure which is roughly, sorry, not roughly, but it's commercial mostly. mostly commercial equipment. Our feed is, we call it the cake pan feed because it's actually made of an actual cake pan. It turns out cake pans are, have really good RF properties with very low loss. So we're designing that at a very low cost as well. And we have a cryogen-free wideband LNA that reaches an incredible noise temperature of dozens of Kelvin, which is very, very incredible. But that's not it. The main, the central core of this radio camera is this. How does a radio camera works? So we have a front end. The front end is, again, completely commercial, right, off the shelf. The front end is iWave RF system on module that includes ADCs. From those ADCs, which sample the data coming out of the dishes, we channelize the data, right? So we split the data into sub-frequency channel. So we have at the input roughly 2 gigahertz worth of bandwidth, and then we go down to 130 kilohertz of frequency resolution. And then we apply a massive data transpose, where at the beginning of our system, we have, for one antenna, all the frequencies. What we want after this massive data transpose is that one server will see the data from all the antennas, but just over a small chunk of frequencies, right? And those GPU servers, what they're going to do is they're going to first correlate the data together, then flag and calibrate those cross correlations. That means basically detecting cross correlations that don't really seem right. It seems like there's an issue, maybe an artifact in it, so we just remove them. Everything runs in real time, so we need to remove them because after that there's no way to get back to the data. We grid, which is it's also an algorithmic step of the imaging process, and then we image using a simple Fourier transform. And what we get at the output of that is narrowband images, images produced over 130 kilohertz channel, but we can completely sum them together to produce an actual image that scientific can use. So yeah, this all runs in real time. And we're currently demonstrating this real-time imaging with the long wavelength array, which I mentioned. It's one of our low-frequency instruments, 0 to 100 megahertz. And what you see to the right, it's slow, but it moves. It's actually an image, a video of the real-time imaging process, right? So what you see is basically the edges of the circle is the horizon. The center of the image is the local zenith. And we see the Milky Way that comes across. Occasionally we see satellites and airplanes that are those bright spots that come through. So yeah, so that helps us prototype and validate the concept of the radio camera. Now, I also mentioned that earlier. RFI, so radio frequency interference, is a major concern in radio astronomy, and especially for the DSA 2000, because we're covering 700 megahertz to 2 gigahertz, which is mostly L-band, and it's also one of the most heavily used region of the spectrum. We can dissociate from this frequency range the 300 megahertz at the bottom and the 300 megahertz at the top of the band, which are mostly site dependent. It contains allocation for cellular services, so mostly cell towers, but also point-to-point microwave and public safety systems. And that's true at the bottom and at the top of the band. And the middle of the band is mostly used for aeronautical, so ADS-B and DME signals from airplanes. We have GNSS, GPS, Galileo, and so on. Satellites, we have lots of satellite communication, geostationary satellites, downlinks, and the Department of Defense that's using this range as well. So to find a site for the DSA 2000, one of the first data that we worked on and analyzed is the distribution of cell tower across the US, and this is what you see here. So each tiny dot, your eyes will definitely not be able to resolve individual dots, but each individual black dot represents one cell tower, and it's pretty easy to see that the US is kind of split in 3 regions, right? There's like a half east with like high population density, so high cell tower density. The West Coast, which is also high population density and therefore high cell tower density. And then there's the big middle where there's not much population, so not much cell towers. And Nevada in particular is a very interesting region for us because not only it has low population density and low cell tower density, but it also has valleys. And we're very familiar with building observatories inside valleys, and we love this protection that the mountains show us, give us, RF attenuations. So we went out to many regions. There's a whole process for site selection that we ran, but I just wanted to talk about the actual survey, on-site survey. We used, it's funny because I didn't know Aeronia was here, but we worked a lot with Aeronia for this survey. So we used this Spectrum V6 spectrum analyzer, which has roughly 200 megahertz, I think a little below 200 megahertz of instantaneous bandwidth. And we plugged this on a passive active omnidirectional antenna. And we basically ran, we drove through the valleys to capture what the spectrum looks like in different spots of the valley. This shows you an example of one of our main candidate site candidate. By the way, we haven't officially announced our site yet, but this is one of our main candidate sites. In blue, you see the footprint of the telescope, where the telescope would be if we were to select this site. In red, the spectrum monitoring regions, and in green, the cell towers nearby this valley. And then you see the various spectra captured at all these different points. And the thing that's the most impressive here to see is you see the number one, the spectrum at the bottom right. It's not on the telescope footprint, but it is kind of in line of sight with that bottom cell tower that you see at the southernmost cell tower. And you see the activity at the bottom and the top of the band in the spectrum in blue, right? You see those large signals, which are just the downlinks of that cell tower, which you don't see anymore in all those other spots, the 7 other monitoring points or sites. That's just because the mountain naturally provides us with roughly 40 dB of attenuation from that cell tower, which is great. We're not only basing all our decisions on site selection on RF monitoring, but we're also using external data such as weather data. We have aeronautical data, which it's this histogram that you see on top of the slide, and we also use studies of satellites, how satellites are going to impact us, which they're a big issue. In fact, talking about satellites. One of the main threats, I don't know if you're aware of that, but earlier this year, the FCC approved the use of the direct satellite-to-cell services, right? Which means that frequencies that are currently allocated to cell towers are now potentially being used by satellites to provide you with cellular service directly from the satellite to your user equipment. Great news if you're in the desert or if you're in like a very remote place where, I don't know, AT&T doesn't want to put up a cell tower. But the problem is that all the bands that are allocated there to this service in particular, they all fall in our band. So we're working actively on trying to find mitigation solutions to these. In fact, one of our main mitigation solutions that we're working on right now is a tunable quad-stub resonator filter. So it's a notch filter that can be turned on and turned off with a varying center frequency to notch out whatever data gets in our signal chain, just to avoid saturation. We also have a full RFI mitigation and flagging pipeline that we're implementing, but I won't get into that. This is my summary slide because my time is up. But yes, the summary is we're working on DSA 2000. There's a website there, and also my email address if you're interested in talking more about this. We're covering 700 megahertz to 2 gigahertz. We're going to be in Nevada, site to be announced hopefully soon, hopefully early next year. And yeah, one of our main concern is interference and active transmissions, which is where I spent, I don't know, like 600% of my time on for the past couple of years. And construction plans in early 2026, so stay tuned. And I'm happy to take questions if we have some time, but probably not.
Probably out of time for questions, but thank you, Greg.
Yeah, thank you.
Appreciate your talk today. Very interesting. Thank you so much. Next, we have Evan Peters, who is going to introduce the Modular Cubesat program. So, podium's good.
Hi, my name is Evan Peters. I'm an undergraduate co-op working at the University of Victoria Centre for Aerospace Research up at, in British Columbia, Canada. This monitor says no signal, is that fine? Yeah, okay. So I'll be talking about our modular CubeSat radio project. These are our sponsors. In particular, I'd like to thank ARDC and the Canadian Space Agency for making this project possible. So our project is aims to be a comprehensive radio system, kind of a drop-in system for CubeSat developers that can be adapted to a wide variety of CubeSat missions. I guess for the more terrestrial enthusiasts here, CubeSat is a class of nanosatellite about the size of a shoebox, typically used in university research programs and aerospace personnel training. So they typically have an emphasis on affordability and ease of deployment. So that's our market that we're targeting, sort of, in a sense. So our scheme includes an SDR, a computer, up to 4 exchangeable RF front-end modules, and other hardware peripheral I/O. It'll be in a PC104 form factor, under 1U volume. That's about 10 by 10 by 30 centimeters. And hardware and software will all be released as open source and open access after development. For this project, we want to emphasize GNU radio compatibility, low component cost, being free of ITAR restrictions, and to flight qualify our hardware all through on SkyNSat, our upcoming CubeSat. We'll be doing this through a variety of scientific experiments, including ionospheric sounding, and some amateur experiments, such as a DVB-S2 video beacon, CW beacon, and a VHF digipeater. Some background for us: the MCR consortium is headed by the UVic Propagation Laboratory. The PI is Professor Peter Driessen, who's had a lot of experience in ionospheric research and other software-defined radio projects. The Center for Aerospace Research is a mech-eng facility headed by Professor Afzal Suleiman, which historically worked on unmanned aerial systems and drones, but due to some Canadian Space Agency initiatives, we've now been able to explore the CubeSat space and move into that project. Those projects, including the OrcaSat mission, which was launched in 2022, had a successful mission life of about 120 days and has demonstrated that we have the capabilities for full in-house CubeSat development. And also the Undergraduate UVic Satellite Design Club, which works on personnel training through satellite development and interstation development. A side note, this project will be added to our growing repertoire of open source projects, including our UHF dipole antenna, which shortly after we released was pretty quickly adopted by some other Canadian CubeSat developers, so clearly shows demand for these types of projects. Speaking of demand, our motivation, so CubeSat development obviously presents many challenges, but in particular we found that the acquisition or development of radio hardware is often either fiscally or skill-wise outside of the capabilities of many developers, also including international regulations for other countries. This can be a significant challenge. So we're hoping to create a framework that addresses many of these issues, offers full hardware and software adaptability, transparent design, low cost, no ITAR restrictions, easily procured. And the baseline is CubeSat development is typically for research programs and personnel training. So we want to offer a framework that mitigates risk by being flight tested at its core, but still having capabilities for future development and future training with those front-end modules that can be adapted by end users. So yeah, you all know software-defined radio and its capabilities, but some use cases could be repeaters, transponders, beacons, satellite telecommand, or amateur television. The main emphasis here for this slide is just that we hope to expand our representation in other satellite downlink bands. As you can see on the diagram there, there's quite a lot of UHF, S-band, and X-band satellite representation, but not so much in other bands, which we're hoping to help encourage and foster. For implementation, there'll be a computer board, SDR board, and those front-end modules, 4 of them illustrated here, but you can have as many as you want. These are typically power amplifiers or transverters to target other bands outside of the intermediate frequency that the SDR outputs at HF 10 meter. And yeah, in addition, only the computer board will actually be connected to the PC-104 SAT bus, the rest of the satellite. The rest will all be internal, so it's very much a drop-in-place system, all internal telemetry and all that. So for the computer, we only have a 2-year development timeline, so a fully custom design wasn't feasible. We decided to go for purchasing a system on module. This avoids ball grid array or custom processor sockets, which are difficult to manufacture, often require like X-rays to inspect that they're properly assembled and so on. So to avoid this and decrease that overhead, we selected a AMD Korea K24. It meets most of our criteria. And yeah, that's what we're going with there. For software, the main takeaway from this slide is that we will be developing all of the core requirements, such as command processor, telemetry interfaces, and several base flow graphs, but because it's an open source project, end users will obviously be able to create their own flow graphs and peripheral drivers and so on to suit their needs as required. For the SDR, again, 2-year development timeline, so we'll be modifying the Hermes Lite 2. We've had a good experience modifying open source hardware with Orcasat, where we modified OpenLST to suit our needs. This will be a full layout redesign to fit that PC-104 form factor and a slight BOM modifications, but for the large part should have the same operating characteristics as a Hermes Lite 2, which I imagine many of you are familiar with. For buses and interconnects, how the actual modularity is going to work. Each front-end module will have telemetry and control through a small MCU. This will be interacted with the computer through CAN bus and can both control the module and its capabilities, deactivate certain sections, control which voltage outputs and so on, as well as report telemetry to the larger satellite bus. For power and PTT, each board will be able to be disabled for power conservation. Yeah, this is all straightforward. Same with push-to-talk. If you don't want your power amplifiers running all the time, they're very power hungry, it's good to push-to-talk to only turn them on when required. For TXIF distribution, since it's our frequencies, this was a little more engaged than the digital buses that we've been going over. Typically, so these will all be done through UFL and coax cables connecting the boards. There are other options, such as PNC and so on, but this targets the right frequency range for us and is, again, very affordable, very practical. I will pass through all the modules in the stack by default, but if one module, say, wants to use TX, it will divert the signal into itself, cutting off lower down modules in the stack. This just prevents multiple from receiving or transmitting and any overlap there. Similarly with the LO, since we want duplex communications, we want the LO to be able to go through all front-end modules simultaneously, and we'll just be using an RF splitter with a set 3 dB attenuation per board. Fairly straightforward, again, UFL connectors, but if you wanted like a very high frequency LO, there are more expensive alternatives that are fairly easy to swap in there. For flight demonstration, the MCR will be going on Skynosat, 3 Cubesat being built by students at UVic. It's UVIC submission to the CSA Cubix program and should be launched in SSO orbit in Q1 2026. As I mentioned earlier, we'll have several scientific and amateur research payloads for ionospheric sounding, DVB-S2 video, digipeater, as well as the CW telemetry that I mentioned earlier. But we will be doing TT&C communication, telemetry tracking and command for elaboration, communications through our UHF radio that we've already used on Orcasat, just so in case there are any issues, we aren't just dead in the water, as goes with Cubesat development. And we aim for Skynasat to be Canada's first Oscar-designated satellite, should we be successful with our amateur research payloads. For the trans-ionospheric sounding, this will be accomplished through power delay profile measurements down at the Long Wavelength Array in New Mexico, as mentioned in the previous presentation, actually. So we've worked with them before and had success working with them. They'll be gathering our data, and that should offer a 3D map, in a sense, over time of the structure and composition of the ionosphere, which we could correlate to climate change activity over time as well. That said, you don't need a highly complicated long wavelength array for this. For 2D power delay profile, we will be doing a citizen science element, where hopefully the ham radio community will be receiving these signals and submitting them to our web-based database and adding to our data gathering. This will be using an HF power amplifier module as one of the front ends modular front ends that I was talking about. There's a plethora of open source designs and so on that we will be drawing from to implement this. The DVB-S2 video beacon on HF 10 meter is an adaptation of the DVB-S2 protocol for use on shortwave frequencies. We've adapted this to use smaller bandwidth than conventional, and has been demonstrated by Robert Swinbank and our investigation to be feasible. This should pose a very rare and interesting experiment for amateur radio operators to investigate. We'll be using just a Raspberry Pi camera too for this. Again, it meets our bandwidth capabilities and is pretty well proven. We'll be using a Greenscube style digipeater to repeat VHF packets on VHF. Since this uses a transverter, it'll demonstrate the frequency conversion of the MCR scheme. And we chose Greencube because it has much better power efficiency and higher bit rate than typical conventional digipeater approaches. So again, but since Greencube was fairly successful, we're encouraged that it will be successful as well. And operators have the capability to receive these signals. That'll be using a VHF transverter based on N5 VVT's Hermes Light 2 VHF transverter. Fairly loosely, it'll have the same general block diagram and components, but well, different components, different BOM, but same flow in a sense. And yeah, so again, for these states, we'll only be operating in one state at a time, only one payload active, just to prevent interference. We'll be releasing a schedule for when TT&C will be happening, when the digipeater will be active, when the science payload and so on will be operating. Yeah, so to summarize, we have a repository link there if anyone is interested. It'll also be posted on skynasat.ca shortly. And yeah, we will be fully flight testing and releasing an SDR board, the system on module mounting board, an HFPA, a VHF transverter, the standardized module template, all the enclosures and mounting hardware. And for software, this will also all be flight qualified except for the AX.25 stuff mentioned in the middle there. Computer and command processor, module telemetry gathering, 30 kilohertz linear transponder, 15 words per minute CW telemetry beacon, the AX.25 telemetry beacon, and a telecommand module, MIPI camera interface, narrowband DVB-S2 beacon, and linear frequency modulated radar beacon that we will be using for our ionospheric sounding. Yeah, that's a fairly quick presentation, but if anyone has any questions.
We also don't have questions from online, so short reminder to the stream. You can ask questions online. We try to weave them in if there's nothing happening in the hall. But with that, I think we should give the speaker another warm round of applause.
That way. Yeah, lunch is served, everyone. So we'll be back here, have everything ready to go at 1 o'clock for the next set of talks.
All right, we're coming back from lunch, and right now we're going to have one of our sponsor talks, and this is David Cotton from Oak Ridge. He's going to tell us a little bit about what they do.
All right. Thank you. As mentioned, I'm David Cotton. For those of you that don't know where Oak Ridge is, it's about 15 minutes to the northwest of here. So we're really close. It's pretty much a suburb of Knoxville. And what I'm going to do today is talk about not only national security sciences at Oak Ridge, but also the lab as a whole and how the national labs fit into a lot of the work that people are trying to do here and fit into the general research goals of our community. So some of the stuff I'm going to go over are a lot of things that I learned because I came from the University of Georgia and didn't know much about the national lab space. But at universities, there's a lot more of the basic science. You're trying to just understand these hard problems to the fundamental level that may not have a lot of reward, but you just want to see, will something work? You know, is it feasible? Let's work at that. Then you have the industry side, and there's a lot of industry partners here that want to, you know, make the most highly engineered product available, that it works as much of the time as it can, and then that it can be moved to serial production. While the national lab, we're kind of in that middle ground that we want to do basic science, but we do not manufacture. Right when I started, they said you're never going to build more than 5 or 10 of one of the devices you make. If you get it to that level, it needs to go off to a project partner. So some of the things and focus areas that Oak Ridge focuses on, I'm going to go now from a really large scale view of what Oak Ridge does. Number one, it started in the 1940s with the Manhattan Project of enriching uranium, and that's where a lot of the research still lies with neutron sciences. We have the spallation neutron source is one of the best neutron sources that you can get in the world, and that's where a lot of the research that we still have. And you'll see all these focus areas. The lab is about a little over 7,000 staff members, so it's pretty large. The keynote speaker talked about exascale computing, the national lab. Oak Ridge has 2 of the top 5 supercomputers in the world right now. We have Summit and Frontier. We have a lot of material science that people don't know as much. We have an additive manufacturing facility that is gigantic and just off. It's not at the main campus of Oak Ridge, but in Hardin Valley. Still do a lot of fusion energy, going back to the roots of the national lab. And then since we are a DOE lab, there's a lot of energy systems research that we're doing, from battery technology to clean energy. There's also bio and environmental research. We have people that actually are doing a lot of phenology for plants, or even biometrics, or even biomedical work. And then isotope R&D production, and then tied to what we do, and I'm going to do a deeper dive into this, which is national security. And the big thing with national security, remember, is that it's not just physical threats. That's one of the number one things, but also we're doing a lot of work to better understand cyber attacks. Like, what are some vulnerabilities that may be known throughout the United States that could cause issues? How can we help identify those vulnerabilities, help resolve them, and, you know, help keep our nation secure, as to say it. Natural disasters. A lot of people don't think of that when you're thinking of national security, but if you have a large hurricane or wildfires, they could knock out the power grid, they could affect hospitals, they're affecting the nation as a whole and the security of the nation. So we focus on that. Non-proliferation, I'll go into that a little more specifically later, but we lead the world in understanding how to create and transport nuclear material safely and to understand where it's going. And then infrastructure vulnerabilities of making sure things that we connect to the grid or the grid itself are secure and working properly, because if you have a power outage in one spot, a lot of times it can cascade and affect numerous other areas and can take a long time to come up. So diving deeper into the sections of national security, where we have reducing nuclear risk. I already touched on a lot of this, but one of the big parts of this is the international safeguards and policy that not only do we help make sure that nuclear material is being transported safely, we are setting the guidelines for the world of if a European country wants to move some material, They follow a lot of the safeguards that we laid out. We also have a mobile uranium facility that if there is a spot that you found nuclear material somewhere, it could be deployed and help solve the problem very efficiently, make sure that it's cleaned up and runs smoothly. Securing critical assets, that's another area that we focus on a lot. I've touched on this a little bit, but a lot of this that I want to focus on for this part is cyber-physical security. So understanding, what are in the chips that we are using, whether it be in the manufacturing sector or even at home, what's in those chips and how can we understand what are they capable of and what vulnerabilities they may have. So a lot of the stuff you'll see, I keep saying vulnerabilities, a lot of it is, we do a lot of work to see, is this piece of equipment that people are using, a lot, is it working the way it should, and are there the correct safeguards on it to ensure that national security is kept in mind. Manufacturing, the additive manufacturing facility that I talked about is one of the world leaders in various composites, but also building materials for extreme environments. And a lot of companies come into the lab and they work with Oak Ridge at this additive manufacturing facility to better understand how they can solve these difficult problems, because it's usually high heat, high stress, very complicated pieces of equipment, and then we pass that technology on to the company and they go off and they can manufacture it and keep moving forward. We do a lot of, and tied to that, we have to do a lot of modeling with that, and that's tied to a lot of the HPCs, because you have to understand how these different compounds are going to work together and the different stress factors that can occur, and then you model it, and then they build it and put it through stress tests and repeat the cycle. Advancing human security, that's where I sit in, where I lead the Resilient Communications group. And a lot of the work that we're doing is we're working with the autonomous systems team to be able to just understand the RF environment, use machine learning to help solve some of these problems and help ensure that, there's efficient spectrum sharing going on. Diving into a little more of the core capabilities that we have here, we work with probably almost every vendor here, at least at some point, if not directly right now, we have in the past with their software-defined radios. We do a lot of protocol development and protocol and waveform development and trying to better understand what protocols are out there, what are the vulnerabilities around those, and how we can work together with different vendors. The resilient adaptive communications, that's some of the work we do with a lot of GPUs and neural networks to actually be able to adapt and effectively share the spectrum, and that ties into learning from signals. We have a small satellite ground station on site that we can downlink UHF, VHF, S-band, or X-band frequencies, and that's tied to our high-performance computing platforms. We don't utilize that as much as I'd like to right now, but we're looking for ways to expand that possibility. And then we also do a lot of work with commercial partners of pushing technology to where the commercial partners can use them and advance them to the greater sector. Let me make sure, check my time, all right. Some of the thrust areas we had for the small satellite ground station was we want to work with these small sat companies that are developing new sensors, all these image products, but they don't have in mind a lot of the security or or onboard processing that could be done, or geo and assurance is one of the words, which is making sure if they collect an image that it goes down to the end user and it is still the same image, that nothing has occurred to it. So we're trying to work with them to be able to strengthen those areas using the systems that I've already described here. What's nice about the ground station is, besides the bands that I've already described, is it's been built in a secure location that, as in on top of a building, that's directly connected to high performance computing, but it can be expanded. We've looked into expanding to optical communications, working with a quantum team on site, possible KA configurations, or even phased arrays. I touched on both of these a little bit. It looks like, okay, well, one of the image figures did not come up for software-defined radio, oops. But for the geo and assurance part, a lot of it is we're looking at using software-defined radios with neural networks and GPUs to just quickly and adaptively learn from the signals that we're receiving. I'll just leave it at that. And then for the emergency response tied to the ground station is we're working with synthetic aperture radar, small sat companies to actually build data products. A lot of this is focused on emergency response, say from flooding or hurricanes or wildfires, and to quickly be able to get their data, produce some sort of usable product and get it out to emergency responders a lot more quickly, because right now it's just reliant on the small set companies, and as a whole they just want to put down an image, and if you see the gray images over there, that's what synthetic aperture radar looks like, and if you're a radar expert, you can read that, but a typical person cannot understand what you see in that figure. So we're helping to produce products that are a lot more easily used and disseminated. One of the last focus areas I'm going to talk about is we've been moving into IoT devices and looking into those a lot more in our lab, in our group, and just it's proliferated. You know, you can go into your house and maybe your refrigerator or your washing machine is hooked up and connected to your network, and how do you know what is secure about them, how are they accessed, and what can we do to better understand the vulnerabilities of these systems? And this actually ties directly into UAS. So a lot of UAS platforms are becoming more prevalent, and they use many of the same protocols as well. So we're investigating those areas to better learn their vulnerabilities. And the last thing I'm going to cover, because I think I'm over time, is we have started this NSSD Academy at the lab, which is to try to bring in more graduate, undergraduate students, and even K through 12 students to start to experience what it's like to be in a national lab, do some of the national lab research. But I put up this specific figure because when I was getting hired in the lab, I thought it was all PhDs, that's what you did at the national lab. But you can see it's almost a third in each category of people with just undergraduate degrees, masters, or PhDs, which I found to be very interesting and very helpful because we have very intelligent people at the lab. And the last part is what I was already introducing to, which was the academy path. And we're trying to create different pathways to get people into the lab, whether it's we go to high schools and just do demos and talk to them about it, understand what something like GNU radio can offer to them and get them just to play around with SDRs. Does that lead to a path of national security? Maybe, maybe not, it doesn't matter. They're learning those skill sets. And then we're also working with community colleges, different undergraduates, retired military personnel, and even other government partners if people want to come and work at the lab. Thank you.
Two things. There's time for questions, I guess, and the next speaker, Mr. Joachim Tapparel, might want to get mixed up. Are there any questions? Come on, you can do better. Okay, then give another warm round of applause to the speaker.
Okay. Hello everyone, I'm Joachim Tapparel. I'm a PhD student at EPFL in Switzerland, and I'm working with the Telecommunications Circuit Laboratory. Today I will talk about the physical layer of LoRa, and hopefully at the end of this talk you will all have a good understanding of what makes a LoRa transceiver. Maybe not. Okay. So for those of you who don't know, LoRa is a low-power wide area network technology that uses the ISM, so unlicensed frequency band, to deliver a low data rate to many IoT devices. We are particularly interested in using GNU radio for research purposes for us, because it enables the use of convenient software-defined radios. We can easily share what we do with other labs or other people, such that it doesn't get lost forever when we are done with the research we do. And LoRa is very well suited to be implemented in software-defined radio, as it uses a small bandwidth and has no real timing constraint, or not stringent timing constraint. So it can run on a very inexpensive inexpensive hardware. So as an overview of what I will talk about, we can have a look at a block diagram of a transmitter. So some of you might recognize a lot of those words. It's a very simple bit interleaved coded modulation. So it's nothing too fancy, as it needs to run on low power IoT device. So the algorithm stays simple. Now, if we want to look at the receiver, it's basically exactly the same block diagram, but in the reverse order, where each of the receiver parts will undo what the transmitter did. And in today's talk, we will follow the trip of 1 byte of data, that will be all one, for the example, that go through the transmitter and receiver chain, and we'll see what happened to it. So the first operation we want to do is to remove any pattern of the binary values that is specific to what the user wants to transmit. And this can be easily done with whitening, so you can XOR your input data with a pseudo-random sequence, and you get a new sequence that looks much more random. Out of each byte of input data, you can create 2 nibbles, and we will use that to create a code word later. So you repeat that process or you continue that process for the full payload, and you get a bunch of data bits. You can prepend a header in front of it that will give useful information for the decoding, and append a cyclic redundancy check, which is some kind of hash to verify the data integrity at the receiver. Now we have all the contents, all the information bits that we want to transmit, and we will add some redundancy to it. LoRa uses a simple Hamming code to add redundancy, and you can see here the expression of the simple matrix multiplication that you can do with all your nibbles, and you get the code words you want to send. So that's the whole data we want to transmit in our frame. But instead of transmitting it sequentially, we want to distribute the bits of a code word into different symbols, such that if one is lost, then other symbols can help recover it. And LoRa is using a diagonal block interleaver, and it's given by either this equation that you can see on the slide, or intuitively you take the code block or the interleaver block, you rotate it by -90 degrees, and then each row has you do a circularly shift of each row, and now you have your interleave block. So now each bit of a code word lies in a different row. And each of those rows will give you decimal value or a symbol value you want to transmit, and it's using a simple gray code such that every decimal value will have only 1 bit difference with the next value and the previous one. And now we have value we want to transmit, but we need to have waveform to be able to send it over the air. And one of the particularity of LoRa is that it's use chirp spread spectrum modulation. So you start at a low frequency, and during the time of a symbol, you will have the frequency that increases linearly. You can use that expression here that to modulate a waveform with a value, and more intuitively, you change the starting frequency of the chirp, and that's where the information about your symbol lies. So here you can see a spectrogram of what we transmit over the air. Obviously here it's with a very high SNR, but that's what you will transmit. And now we can look at the receiver, how you deal with it to get back your information. For people that are attentive, you might have noticed I've swapped the block diagram on the top with a flow graph, because flow graphs are better, they compute something, so I just replace it here. Let's look how we demodulate the information now. So you have your chirp, so your received signal. If you do element-wise multiplication with a specific waveform, you will concentrate all the energy of a symbol into a single frequency. Then it's quite intuitive. You take the discrete Fourier of that new symbol, and it gives you a spectrum that you can see on the bottom right, where you have all the energy that is in one frequency bin. And luckily for us, the frequency bin in which it lies is the symbol that is encoded the value that is encoded in the symbol. And that's one of the key aspects of LoRa, is that you can get the maximum likelihood detection, but only with a complexity of n log n, because you can use the fast Fourier transform to perform all the correlation necessary. Now I was a bit optimistic because real life is not as kind. So instead of demodulating a symbol that looks like a Dirac, you will suffer from carrier frequency offset or sampling time offset, every hardware impairment. And now it's more difficult to know which value of the output of the FFT is our symbol. So if you add on top of that, that you account for noise, that is also added by your receiver chain, it becomes difficult to find where your symbol value is, and it's here, so it's not even the maximum now. So what you need to do is to estimate all those offsets and compensate them, which I won't give the detail now. But in short, you can have 4 different steps that you can follow to first remove some subsample offsets that will have the effect to gather back all the signal energy into one bin, and then you have integer offsets that you can compensate that will shift back the bin in its correct position. So now you get your sample value back. You can do that for your full signal, and you get all the value of all symbols. So you undo the gray mapping, you get back your interleave matrix, you de-interleave it by doing just the reverse as a transmitter, and you are back to having code words. And now it's the decoding, so it needs to be a bit more interesting, or it needs to do something, because we add redundancy for a purpose. And LoRa uses a simple Hamming code, so you can view it as a Venn diagram, where you get parity bit and data bit. You feed the bits in one code word in this Venn diagram, and you can XOR all the elements in a circle. If they give you a 1, it means there is a problem. If they give you a 0, it means it's fine. And now we can see that there is a problem in your receiver. And one can notice that if you would flip this bit here, everyone would be happy. So it's very probable that this bit was flipped due to the wrong demodulation. So you can correct it in your data. And since we are decoding the first interleave block, we get back our header value. And in GNU Radio, you need that information to decode the rest of the payload. So you can feed it back with an asynchronous message to the beginning of the receiver chain, and then it gets propagated to each block that needs it via a synchronous tag. So for the payload, it needs to be dewhitened, which is exactly the same operation as the whitening. You XOR it with the same pseudo-random sequence, and now we can see our sequence of our original bytes being back. You compute the cyclic redundancy check on it, and you can compare it with what you received from the packets. And if it's correct, it means you have successfully decoded your packets. Now, I've talked about many blocks, and they are all available and implemented on our Git. We could evaluate if it was working not only in simulation but also in real world, so with USRPs in our testbed to suffer from CFO and STO and observe the performance. And it has also successfully been used in many papers that deal with a lot of different topics. And I think that the presenter next to me also uses it, so I'm eager to see what he will say about it. Now we are working on what next for our implementation. We are working on a centralized radio access network architecture, so having a distributed antenna array and then processing jointly the IQ sample received by the different locations. So we've built a prototype of gateway that is based on USRP and a Raspberry Pi. We've put a few of them on the roofs of the campus at EPFL, and you can see here a plot of the received SNR based on the position of the transmitter. So thank you for your attention, and if you have any question, I will also be around the rest of the week.
All right, thanks. I always like the practical talks, and that you've got the code available on GitHub, so anyone who wants to try it out can easily do so. We have time for a few questions. Do we have any? Is that you? Okay. All right, so our next speaker is Josh or Joshua? Okay, Josh or Joshua. Conway is going to be speaking also on LoRa. Is this going to turn into LoRaCon? Maybe? Okay. So Thanks again, Joachim. Let's give him one more round of applause. And then Josh, the time is yours.
Good afternoon. I am Josh Conway. Some people would know me as Cranky Linux user, and I'm bringing the talk here, Meshtastic-SDR. That's an SDR approach for a full Meshtastic receiver. And thanks to Mr. Tapparel, who just gave this wonderful talk. His work is instrumental in what I was able to continue working with. That looks like the wrong controller. There. So what is Meshtastic? So according to the Meshtastic devs, it's an open source, off-grid, decentralized mesh network to run on affordable low-power devices. Now, what kind of low power are we talking about? We're talking about ESP32s, we're talking about NRF low-power boards. It even runs on Raspberry Pis with a Wave Shield, which is an SDR, or not SDR, it's a LoRa shield for that. And all the devices I've seen so far use Semtech's LoRa transceivers. I believe it's like the SX 1272, 1276. It's around those, that line of product. And all of these use, it's a single transceiver type. And these devices are usually around $25 starting into getting into this platform. And as before we got into SDR and LoRa SDR, this was a proprietary, you had to buy their chip, and now with the SDR solutions available, that's no longer the case. So how does this actually work? So these little mesh devices will communicate back and forth between each other. They do use a peer-to-peer communication strategy. They do abide by different amounts of hops, so they will redirect and they will forward your messages to other nodes on the chain. Earlier today, I was communicating with somebody around 60 kilometers away through 3 hops of this network. And from here, you can see that normally your interface would be a phone, connect to your LoRa node. There are also LoRa nodes that are self-contained keyboards, if you see in the bottom corner there. So you can have it completely enclosed without any phone attached at all. They also have a lot of computer capabilities over Bluetooth or Wi-Fi. And then the one I added was the GNU radio to be able to communicate to the LoRa network and the Meshtastic network directly through a computer and SDR. So why an SDR solution? Well, Meshtastic and the Semtech hardware only supports, I call it a geometry, but it only supports one spread factor, one code rate, one frequency, and one center at a time. You can't really hop, and it takes time to hop those frequencies. With an SDR solution, instead, you can monitor multiple channels within the bandwidth that your SDR supports. What's really nice about this is even an RTL SDR, the inexpensive $20 solution, can monitor 5 of the 8 presets in Meshtastic. So a preset is those predefined LoRa geometries. And this device, just a $20 device, can get you listening in on Meshtastic's network for 5 of the 8, including the most common one, the long fast network. And then this potentially, so an SDR potentially allows receiving multiple channels at the same time, and then having, if you were to pair it with another SDR that can transmit, or with real hardware, you could listen and watch up to 5 channels at once, and then communicate out like you'd see in a traditional amateur radio repeater. This can bring Meshtastic and LoRa modulation to other frequencies. I did a test on the ARRL field day earlier this year on the 2 meter band, which is 144 to 148 amateur radio band. And that was an exceptional test to be able to bring that modulation and Meshtastic down to the amateur band. And along with this, having an SDR receiver and transmitter also allows for very rapid testing of bugs. So for example, the SDR flow that I use uses 0MQ. And because of that, it's just a byte stream. So you just shove byte stream into it and you can test whatever you'd like. And I've tested a few things of different bugs in the Meshtastic system that you can inject a random byte stream and test and see if things are acting as the way they should. Now, I have a YouTube video, if you go ahead and play that without audio, and I'll be glad to walk through how, yeah. Okay, so to run this, you first mirror the repository. It's over on GitLab. this time around. You do have to install Mr. Tapparel's GR LoRa SDR as it's a dependency. Once you mirror it, there's a few directories in here. The first one we're looking at is going to be the GNU radio directory. And that's where the script is for the receive and the transmit flows. They are different flows right now. Now, along with this, we also separate these out into the different frequencies. And then also European is 868 megahertz, US is 902 to 928 megahertz. So I also separate that out for ease of use for the people who want to use this platform. Okay, so here, there's 5 different flows here that are potentially running. The bottom one is the long fast. That's the default that people normally get put into with running Meshtastic to begin with. And it's the most common communication. Normally, real hardware can only run one of those flows. Whereas this, once we execute this flow, we can actually watch all 5 of these flows at the same time. I'm using a hack RF in this case, but there's no reason for that. If I had an RTL SDR, we could run that. If you have a Blade RF, any front end would be perfectly acceptable to run in this situation. And we go ahead and run it, and we'll see in the bottom corner. Now, I did make one small modification to Mr. Tapparel's code, and that was the debug switch to turn on SNR and the SFO and the CTO. And that provides all the extra details of how the signal is and if it's good or not. Along with this, I'm using 0MQ, and we have the ports 20,000 through 20,004. Each of their own ZMQ, so we know which port goes to which preset. From here, you see in the bottom corner there that we're seeing LoRa data right now. We're decoding it directly. And we now have to have another accompanying program in order to decode that data further. Because Meshtastic also has its own data format. And this will parse the format to get the data out and actually give you the real messages, like the text messages. You can see from here the debug modes. Basically, because it's all 0MQ, you just give it an IP address and a port, and it runs. And we'll go ahead and see that, and we can see some messages come up on the screen after we go ahead and run that. And this time I was actually going on my real device and then making some code, or maybe making some messages back and forth. Now on my current code, I actually had to implement an extra check. So this is a message for this ecosystem for text messages. If you're not running the 2.5, the newest version, direct messages are not secret. They're not encrypted any more than the normal communications are. So I found some messages that were being communicated, and it did not feel appropriate to allow sniffing of direct messages, because that's just not fair. But that's also now part of the code base to exclude that out of privacy. And as we see here, we have messages coming through, and we can see some messages don't decode properly. Part of that is because I do have CRC errors passing through turned on. So I do get some errors in there. There's also some protobufs, which is further down the data pipeline that I haven't implemented all the way, so some of those aren't being parsed correctly. But again, we have a full stream of all the different messages that we see on the network right now. Now this is, like I said, this is just the receive flow. There's a node announce message right there. And then we also have the transmit code as well. And the transmit code is the same flow, except it's another GNU radio flow. We're going to go to that here on the video. And in the transmit, and I'm looking at adding these two together to not have to switch back and forth. But at this moment, they're separate. In this case, what we're implementing is the long fast, which I believe is SF12CR4, frequency 906.875, bandwidth of 250 kilohertz. And again, this opens up a port for 0MQ, except it's not 20,004, it's 30,004. So again, it's a simple, you send bytes into it, and it transmits it out only. And we can demonstrate that. And what I'll demonstrate here is I injected a node announce message. A node announce message in this Meshtastic ecosystem is to announce what your node's name is to the public. How do they call you? What name do they call your node? And all I'm doing is I'm sending out what's the clue server, which is currently running over in Bloomington, Indiana at my house. And I wanted to replicate that signal here, and that's what I did. And so it made it temporarily look like that my node was actually here instead of where it really is right now. And we can use a GNU radio, the transmit script here, as we see here, and we can just send the raw data directly into it, and it will transmit out over the air, over the HAC RF. And again, this works for any front end, so HAC RF, Blade RF, USRP, any other transmit compatible is perfectly acceptable. And I think this is the end of the video here. Awesome. And if you keep it on the screen, so this is actually what it was shown here just a moment ago, but this is what a LoRa transmission looks like as well, with all of the symbols like that. And again, this talk would not have been possible without Mr. Tapparel's wonderful input and with GR LoRa SDR. I would not have been able to be here and be able to do this talk without his exceptional work. And of course, is also a dependency. And again, I'm Josh Conway. I do have code credit for the source code that was provided with Meshtastic-SDR as listed, and my email. And then there's the QR code to go to the repo. Thank you.
All right, thank you. While our next speakers get ready, we have time for a few questions. All right, I've got one for you. So did you interact with GR LoRa SDR? Did you put up issues or have any issues with that, or did you just take it as is?
Actually, no. There was only one thing I looked for, and that was how do I get like an RSSI or an SNR? How do I get more debug? And I found a ticket already that he answered. Is like, yeah, just go into line 5 of this one file and comment it out to open the debug, and then it emits all the debug that I really needed.
Okay. All right, thank you. Any other questions? All right, let's give him one more round of applause. All right, so we're sadly going to take a break from LoRa for a few minutes and talk about education. And are you Dr. Steele or Dr. Gujan?
Yes, you have to guess. That's the quiz at the end.
Okay, so we've got Dr. Steele who's going to be presenting.
Okay, thank you. Very nice to be here. My name is Simon Steele. I'm at the SETI Institute, which is in Mountain View, California. And I'm also the principal investigator, the PI for the NASA Community College Network. I'm going to say a little bit about NCCN, as we call it, and then I'm going to hand over to my colleague Vishal, who's going to talk a little bit about the ARDC-funded program to bring radio astronomy into community college classrooms. I have 2 clickers. There we go. I thought we'd just start with a lovely view of the Milky Way galaxy. This is an optical image looking towards the constellation Sagittarius, which is the center of our Milky Way. What you'll notice in a visible image is it is a very dusty place. It's very difficult to see through these dust clouds using visible wavelength light. And that's one of the reasons why radio astronomy, radio waves, is so essential in looking deep into our galaxy, because the extinction is much less at radio wavelengths. So that's one of the motivations for using radio astronomy in studying our galaxy. Now, we are inside our galaxy. It's 300 billion stars, including our sun. How can you tell the structure or the layout of our Milky Way if we're just looking from the inside out? One of the thoughts is that it probably looks like a lovely spiral. This is another galaxy. This isn't our own. This is NGC 16 or 1566. Maybe this is what our galaxy looks like, but we can't tell because we can't get outside. We can barely get outside our solar system, let alone getting outside our galaxy. And that's where radio astronomy comes in, because you can probe the depths of our galaxy, you can look at the dynamics of our galaxy, and from that you can get an understanding of the structure. And that's what was done back in the 50s initially. This is an early map of the structure of our Milky Way. It was made by Jan Oort in 1958, using the 21 centimeter line, which is the spin flip transition of neutral hydrogen. The parallel and anti-parallel spins and the transition between them at the hydrogen and electron that gives an emission at 21 centimeters or 1420 megahertz. Now, by looking at this spectral emission at different locations in our Milky Way galaxy, looking at the Doppler shift of that 21 centimeter line and its location in different galactic longitudes and latitudes, you can develop a picture of the spiral structure of our Milky Way. And that was first done in the 1950s. This is an experiment that could be done very nicely if you're in a 4-year research university. You have access to your own radio telescope, you have nice labs, but it's not the case if you are taking astronomy or taking physics at a college that does not have those resources. And that's where the NASA Community College Network comes into play. NCCN is a NASA-funded 5-year program to try and support the teaching of astronomy at 2-year and community colleges throughout the US. And the motivation, for those of you who know the structure of community colleges, is quite clear. About half, almost half of students taking introductory astronomy do so at community college. So this is a very, very large population. That makes about 700 colleges throughout the US are teaching introductory astronomy. What's important, though, is that the resources for most of these colleges, not all, but most of them, are very, very limited. And yet they're reaching an incredibly important demographic in the United States. If you look at some of the stats here, 26% of the students are Hispanic, 13% black, 29% are first-generation college goers, and 15% are single parents, and a lot of them are mature students who are coming back to get some sort of formative education and will need to take a STEM course, and that's where the astronomy course comes into play. So helping these students in an underfunded environment are instructors of whom only 23% actually have astronomy degrees. So this is the motivation for NCCN as a program to support these instructors to reach this incredibly important part of our community in providing a very, very authentic and powerful STEM education to create a science literate workforce and population. NCCN works in 4 main ways. It provides a set of ready-to-go resources that these instructors can use for their classrooms. And one of those, of course, is what Vishal is going to talk about in a little bit. The second one is to provide professional development, actually get modern cutting-edge astronomy and space science developed by NASA into the hands of these instructors, so they're not just working from 20-year-old textbooks. The third one is we actually bring one-to-one contact between NASA subject matter experts and those community college instructors, either for the subject matter experts to give presentations to the students, or simply a one-to-one interaction and conversation between the scientist and the teacher to help them through some of the more complex, perhaps, topics that they have to cover in these astronomy courses. And the last one is providing a community of practice. Some of these colleges only have one astronomy lecturer. They have no community, they've got nobody to bounce their ideas off of. And NCCN provides that community for them. This is a map of the reach of NCCN. We are currently working with 206 community college instructors in 38 states around the United States. This is from our website. You can get information on our website from our booth, the SETI Institute booth. All of these are clickable, and you can find if there's a community college near you. The little blue rocket ships are the subject matter experts, the scientists, such as Vishal, who are helping us provide these instructors with very, very important resources. And these SMEs come from all of the NASA centers, most major universities and observatories. That's NCCN. This is a way to reach an incredibly important audience. And when Vishal approached the NCCN team, saying, I would like to develop radio astronomy to put that into the hands of these community college instructors. My first thought was, that is amazing. I love the idea, but we don't know if the instructors will be interested in this. They tend to be very overworked. As we said, only 23% of them actually are comfortable teaching astronomy. And generally, the courses that they're doing are packed with a lot of material. Will there actually be availability of time to learn about radio astronomy and teach radio astronomy? And to our wonderful joy, there was a huge response from the community college community to take part in this pilot program. It was selected up down to 44 community college instructors, of whom 6 were given the opportunity to come to the Allen Telescope Array in Northern California to actually do a hands-on workshop on the development of this curriculum. I'd like to call that Joel Zack at the back there, who's also part of the program. And Vishal will say a little bit more about his work as well, moving forward. That's just the background of who we're working with and why it's important. And I'm going to hand it over now to Vishal to actually talk a little bit about the program that we offered them.
Okay, thanks, Simon, and thanks for the organizer to also giving us this opportunity to talk to you all about this thing that we are very excited about, is bringing radio astronomy to community colleges. So before I begin, maybe because I'm slightly an outsider, I also like to introduce myself. So I'm an astronomer. I work on various different subtopics, mainly involving compact objects like pulsars, fast radio burst, but I also am quite interested in machine learning techniques and large data and real-time signal processing. But apart from all, my main area of research is SETI. So I am one of the alien hunters. So you're going to talk about how do we find aliens, talk to me. I'm going to tell you a little bit about it today as well, but yes, that's one of my primary area of research. So, as Simon mentioned, in a STEM education, there are a couple of challenges, and these challenges are sort of further amplified in community colleges. So what are these? So first of all, motivating student and increasing their participation in your teaching is a challenge. You want to also bring theory and practice together is also a challenge. How do you utilize cutting-edge technology like what we are talking about here in this platform, right? How do we bring that to colleges? Are there there need to be an interdisciplinary approaches, because many colleges are teaching subjects that are not sort of overly common across all of them. So how do you design something that's applicable to large different areas of research? Also, the curriculum needs to be updated, because if you go to a community college and look at their curriculum, the content in there is like a decade old. It hasn't been kept up with time. So you also need some mechanism through which you can update the curriculum so that it can also increase students' engagement. So I'd just like to highlight a very simple thing. This is what I think historically people who have worked on the education, they all know about this thing. It's called Edgarsdale's sort of learning curve cone. What it shows you is that going from top to bottom is the sort of level of retention among students or among anybody. Like what level of retention, if something new is taught to you, at what level will you be able to retain that information? And as you go down at the bottom, that's the highest level of retention, and that's when you actually able to do stuff by hand. So if you are able to engage students of doing things by their hand, it increases their participation, it increases the retention. So you can increase, basically, if you want to convey certain ideas, you want to teach something, it's always better to let them do these things by their hand. So since we are talking about GN radio, my entire talk will be building this particular blocks. So I'm going to talk about various different problems that I just mentioned. This is my problem statement. Like there are these challenges in STEM. How do we solve it? So this is our source block. Let's move ahead. So so in order to solve the problem, this is not something that is new. People knew about it. There has been studies done among students. So there was this study done in a couple of years ago where they surveyed students and they asked this question: what excites you the most? What question in STEM education basically can create largest amount of sort of interaction? And undoubtedly the answer came: searching for life. If you talk about searching for life outside the Earth, searching for extraterrestrial intelligence, that increases the participation. Don't have time to go into the detail, but the x-axis here is showing the amount of interest, and the y-axis is showing you different countries. And you can see almost all countries, so across different geographical background, with socio-economical background, everybody is interested in sort of talking about searching for life in the universe. So if you can tie a complicated idea that you want to teach students with sort of searching for life, it always going to help you get that idea across pretty easily. So that was our sort of concept, and we pitch it to ARDC, and I'm very thankful for them to kind of support us for this pilot grant, where we were able to basically build a curriculum for community colleges with the SETI as a backdrop using GNU radio module. So this potential solution is SETI. Let's move ahead. Let's try and see what SETI is. Obviously, I don't have time to go into all the details, but what I can tell you a little bit about it, because this is going to be an only talk about it, so I do want to give you some background, because I'm not sure all of you might be familiar with what SETI is and what we exactly do in the field of SETI. So let me take a slight diversion and talk about SETI. So what is SETI? I'm sure all of you have wondered about our place in the universe, like are we alone? When you look up in this night sky, remember this: all the stars that you see have planets around it. Now we know that. If you have asked this question maybe a decade ago, we had no answer. But now, based on what we have found, the number of extrasolar planets we have found, it is almost certain that any star you see in the night sky have planets around it. So obviously the question is that whether life is unique to our Earth is unlikely. There has to be other life there. And once you have life, evolution is pretty common. Like on Earth, life finds a way. It got destroyed multiple times. There has been a multiple sort of large extinction event, at least 6 that people can able to figure out. And in all cases, life survived and it evolved. So once you have life, it will evolve, it will become intelligent, and eventually you should have highly technologically advanced life, most like in at least a large fraction of them. So how do you find them? So this is our Milky Way galaxy. Let's say you have a planet on it which has life. Over time, that life develops intelligent, that becomes technology, and technology also produces radio waves. Radio waves is one of the signature of technology. So when you have life, they're producing radio waves. These radio waves are not bound to a planet. Even if they have been used for communication, they are also traveling in space. So you have multiple of these civilizations living in our Milky Way, all producing radio waves. These radio waves are traveling in Milky Way, and here is Earth. We are sitting here, we are also producing our own radio waves. It's possible for us to encounter these radio waves and capture it, and basically find if there is any technologically advanced life there in the universe. So we use powerful radio telescope. This is a telescope called Green Bank in West Virginia. It's 100 meters in diameter, it's massive. As I think what Greg talked in the morning, the amount of radiation we require for us to basically do any meaningful science is extremely low. So for that, you need a big, big antenna. So that's how we try to solve the problem. Are we alone? What kind of signal we are searching for? Very briefly, we are searching for different kinds of signals, whether it could be like a deliberate transmission or any kind of leakage radiation. You may ask this question, like what radio waves we are generating, is it possible for those radio waves to be detected by ETI? And the answer is yes. If you talk about the planetary radar signal that we produce, they are so powerful that they can be detected by the same size telescope that transmitted it. For example, Arecibo used to transmit very powerful radio waves. You can detect that kind of radio waves all the way to the other end of the galaxy. Imagine that. We sitting on this tiny dot here on Earth, we are able to produce radio waves that is possible to be detected all the way across the galaxy. Now, the same argument applies for ETI as well. They can also have powerful transmitter for detecting asteroids in their own solar system. That radio waves are traveling in space, and so you can detect them. Not just with that kind of powerful radio waves, even the leakage radiation from mobile phones. So if you take, as Greg also talked about in the morning, if you take the collective transmission of all the mobile phone towers on our planet, it's not as high as the planetary radar, but it is high. It's like 10 to the power 9 volts it reaches. So it is possible for a highly advanced civilization to detect that kind of leakage radiation. So that's what we are trying to do. Just an example, one of the kind of signal we are searching for is narrowband signal, where you put a lot of energy into only few frequency. This is, as far as we know, there are no natural sources that produces signals like that. So if you detect a narrowband signal, which is sort of coming from an extraterrestrial source, you certainly know that it's been produced by technology. And if it is not our technology, then it's extraterrestrial technology. And we are searching across all different parts of the sky. We are looking at all nearby million star, our Milky Way galaxy, as well as other galaxies as well. And this search is currently being carried out across almost every telescope that you can possibly imagine. Large number of them are currently collaborating with this program that I work with called Breakthrough Listen. And Breakthrough Listen basically conducts SETI research on all of these observatory. The other program that I also work with is SETI Institute called the Allen Telescope Array and the Very Large Array in New Mexico, which are also at the forefront of this research. And not just that, we are also in a process of basically doing a design study of establishing a radio telescope on the far side of the moon. Because no matter what you do, you cannot escape satellites. They are going to produce interference for us. They are going to produce signal that we are searching for. So the best place for them to set up an instrument to do proper SETI is the far side of the moon. So there is a funded research right now where we are doing a design study of a radio telescope on the far side of the moon. Okay, so that's all about SETI. I hope you got the very quick overview of what exactly SETI is, how we are basically trying to search for extraterrestrial intelligence. All right, so next comes the AGI SETI, or what it's a short form call for the project that I'm going to talk about, in which we are designing a curriculum for community colleges. And there are 3 different aspects of this curriculum. We are designing lecture notes, we are designing workshop, and then we are also designing GNU radio-based labs. So I'm going to go with each of this module. So let's talk about, so this is our website. I hope all of you will be able to kind of visit that. All our modules that we have basically designed are on there. You can look at different, basically our goal is to design different modules and not design one particular course. So we have a course on like basic introduction to electromagnetics. What exactly are electromagnetic waves? And this is a very popular course in a lot of community colleges. So introduction to astronomy is there. Different kinds of radio waves that we are searching in the field of SETI. We have designed GNU radio-based labs, and you can actually download the GRC files from our website, and you can play with in the classroom. Also, introduction to radio astronomy, SETI efforts around the world. The most important thing that we are really proud of is that we are able to also give access to these community colleges for our telescope. So we have these Allen Telescope Array, so we are also able to provide direct access to a lot of these community colleges to come out at the site and basically conduct observations. So this is, as Simon mentioned, one of the workshops that we conducted earlier this year, where we invited 5 or 6 community college instructors to come out at the site and carry out observation using the antenna, using the array itself, and then they could basically teach their student. So students get very excited if they actually get a hands on a real radio telescope. So that's our primary goal. I'm not going to talk too much about it, but the telescope that we have used for this is the Allen Telescope Array. It's a fantastic instrument, but Luigi Cruz, who is also in the audience, is going to talk more about the ATA tomorrow. So kind of keep that in mind and do come out for that, where he will go at length about what ATA is. But it's basically an array of antenna. It's a 42-meter antenna. 42 sort of antennas, 6 meter in size. It goes from 1 to 10 gigahertz in frequency coverage, and it's the primary sort of the purpose of the telescope is to search for life. It is in the Northern California, and it is actively searching for all kind of extraterrestrial signal that we could possibly think about. So what are the different labs? I'm just going to give you a couple of examples, obviously not with the limit amount of time. One of the labs we have designed is detecting Voyager. So Voyager, as you know, is a space probe that was launched way in the 70s, and it is at the furthest man-made object, as you know, right? It has already crossed the boundary of what we call the solar system, and it's reaching into the sort of interstellar space. You can detect it using powerful antenna. So we have basically recorded data from Voyager, and we basically can play it back. So this is a lab that we have designed for community colleges, where they can actually get the data from our website, and with a very simple GNU data toolbox, they can build, they can play back the signal that we have received from Voyager. And they can look at the carrier wave, they can look at the sort of the sidebands, play with it. We have also added something else extra, like you can demonstrate to students, like as the signal, as the sort of the source travel further out, the signal strength decreases by basically R square, right? So you want to, if you want to explain that concept, you can do that. So in a GNU radio, you can move and you can basically simulate different distance of Voyager, and you can actually simulate how the signal strength actually decreases as the Voyager move further and further away. So if you want to explain something this like to your student, it's very helpful. So again, going back to the live observation with the Allen Telescope, so that was what we did with the recorded data. But as I said, we have also designed specialized graphical user interface just for the community colleges. Because as a radio astronomer, I know how to operate a radio telescope. But it's a long, lengthy process. There's a lot of, one needs to have a little bit of expertise in order to go through everything in order to operate a radio telescope. We don't want to make instructor go through that. We want to make it as simple as possible. And for that, again, credit goes to Joel, who is also in the audience, who has designed this graphical user interface to actually control the telescope with just 3 clicks. So you can configure the telescope, give a command, and you can just let it go. And the telescope basically conducts and takes the data for you. So it gets very easy. And we actually did this trial run in our workshop. And I think all the instructors enjoyed playing with it, and they were able to kind of collect data. And the most important thing is that the data that they collect are in a format that can be played back with GNU radio. Like typically the radio telescope data we collect is a slightly different format. It's called filter bank, but those are not very difficult to play with the GNU radio. But here we are actually collecting data that can be played with GNU radio, so they can do anything they want with the data. They can do any kind of fast Fourier transform. They can extract any kind of information they want within the GRC blocks. Another example, as Simon mentioned, about detecting natural hydrogen from Milky Way. So this is an experiment we did, and it also brought a lot of interest among students, because when students actually clicks on the telescope and they can see the telescope move, if they are at the site, it's even better. But even if they are not at the site, we have a camera set up there so they can actually see telescope move. And most importantly, when the telescope moves on the part of the galaxy, what you see, you start seeing the natural hydrogen from the Milky Way. And that's fascinating for students to really see that for the first time, that it's like as if you're looking through a telescope through your eye. This is a radio telescope. It's actually letting you see the universe, letting you see the distribution of hydrogen in our Milky Way. So this lab also kind of was very popular, and we were able to conduct this with our community colleges. So that's, I think, about final what I had to speak. Just in summary, as I mentioned, we had a couple of challenges. We had a problem of like how do you motivate students, how do you basically bridge theory and practice, and we hope that by providing all of these different topics, we were able to at least solve a couple of these challenges. And I thank you for your attention. I'd take any question.
Thanks. What questions do we have for SETI? We're just full of questions. Oh, go ahead.
I don't know who to direct this question to, but do you have collaborators outside of the US as well? Or is there an option for collaborators outside of the US to collaborate in the college, the NASA college network?
I think so.
Not directly, because through NCCN, being a NASA-funded program, it has to stay in the US. We do have some of the subject matter experts internationally. There's no limitation on that, as long as you're working with NASA data of some form, and that's just about every astronomer on the planet. We very much welcome those subject matter experts joining us, but at the moment we are limited to the US.
Yeah, hi, thank you. I see you're collecting data from Parkes telescope, which is in Australia. Is that, so surely there must be some access to collect some of that data from an Australian perspective?
Yeah, so Breakthrough Listen program that I mentioned earlier, when it was launched in 2016, we actually use Parkes quite a lot. In fact, 20% of the telescope time was used for SETI from Parkes. So it is one of our primary, what we call, observing facilities till today. So yes, we do use it a lot.
Do we have any other questions? All right, well, thank you guys.
Thank you.
All right, our next talk is going to be our NI sponsor talk, and we'll have Martin Braun presenting.
All right. Which clicker do I use? 1, 2? 1, okay, thanks. Okay, yeah, I'm very happy to be back here at GRCon. So we as the manufacturers of USRPs have been sponsoring this conference since the first conference. So I'm very proud that we have this continued tradition and we're back here. So this slide says Ettus Research /NI, and it also says Emerson. So I quickly want to talk about that because I've gotten so many questions on, so what's the state of your company? What do you, how do you operate these days? And is SDR still a thing? And the question is, justified, because if you have, been following anything about NI, so there was 5 years ago, we had the blue logo NI, and we had the green logo Ettus Research, and then a million things happened, and company got sold to Emerson, so we have another new blue logo, and it was new leadership, and everything got reevaluated. And so as a consequence, many of you guys have approached me directly at this conference and have asked, so what's the state of SDR at NI? Is it still a thing? Are we going to keep doing that? And the answer is yes. So it was, scrutinized, of course, and it turns out SDR is still a great product, and it makes total sense to keep doing that. And in fact, we're going to be doing even more of that. So there's been an increased reinvestment in the SDR product line. We're putting more people on it. And also just the concept of having this open source based SDR itself was considered sensible and worth continuing. So we're back. There's plenty of people here at the back. Maybe you can raise your hands real quick. Yeah, so if you have questions about products, you can approach any one of those or myself. But yeah, that's enough going on about our company. I want to talk about stuff that we've been doing. I don't have a new product, like hardware product, to present this year, but we already have a lot of really cool hardware products, so I'm going to quickly go through them one more time, because I think one thing that we do really well with our SDR, the USRP product line, is sort of cover this huge space of possible applications that you might care about. So at the top left on this slide, we have the low swap devices, USB-based, like smaller channel width, but also like really easy to set up. The bottom right, we have the USRP X440, which can capture 1600 megahertz of analog bandwidth instantaneously with 2000 megasamples. And in between, we have everything else. So like the USRP X310, still a really good device, RF NOC capable, can do Ethernet, has like different daughter boards, so it can cover different frequency ranges. The top right, we have the deployable devices. They're either small, like the E310, or ruggedized, so you can deploy them in all sorts of environments. And then at the bottom, of course, are high-end devices. They all come with an embedded processor, so they run Linux natively, and give you different frequency ranges up to 8 gigahertz. Directly, you can use additional up and down converters and really high bandwidths. And on the software side, we also provide all sorts of options. So I guess most of you would be using the open source workflow with the USRP, so using our UHD driver, and then using the C, C++, or Python APIs to call into UHD. That's what most people do. It's also really powerful. But you can use GNU Radio, of course, so that's still front and center for us. We make sure that GNU Radio support is always a given with any USRP that we release, really on day one. But if you don't mind going into proprietary software, we have that as well. So we have support for MATLAB and LabVIEW, of course. The only case where you really do need to, buy some piece of software is if you want to do FPGA development, because we do have our RF NOC framework, which allows you to deploy all sorts of IP onto the FPGAs of the USRPs, making them even more sort of useful in different environments. And that's where you're going to have to get Vivado. But other than that, really, the choice is yours, and whatever workflow is most relevant to your kind of work, that's what you should be choosing. Now, if there's anything that you think you should be able to do with an SDR, but you can't, I challenge you to go to either Marcus or Ben Coffin, the guy who looks like he plays in a heavy metal band, and Marcus, the tall guy on the left. See if you can challenge them, poke them questions like, why can't I do X? Because I think we have a pretty good array of devices available. All right, now there's really two things I want to actually go on into in this talk. And I'm going to start with things that are happening outside of the USRP product development team. So of course, like NI is a big company, and I'm on the team that develops UHD and builds USERPs, but there are also plenty of other teams doing research or other kinds of work. And I do want to talk about that, because there's some really interesting things coming out of those teams. So first of all, we really like enabling researchers to do their, to solve their RF-based research problems. So, in particular, if you are into 5G, 6G, future G type of research, then one of the products that we have available for you is like a bundle of USRP and OAI. So OAI is a open source 5G software stack. It provides G-Node B and UA implementations, and it's modifiable, so you can look at the source code and instrument it at all, various layers. And that's really, really key and important if you're a researcher and you want to poke around in the 5G stack and see what's going on, maybe make some changes, see if you can improve something, or see if you can break something, right? Why not? You can do some security research at this point. And we've officially bundled OAI with USRPs, because you always need some kind of hardware to make it go over the air, and become a member of the OAI Alliance. And we try and make an effort to make it easy to integrate those. So it's a really good starting point if you're into 5G, 6G research. And we've actually made use of that ourselves, which I'll get into in a bit. But if you're not so much in the telecommunications research, maybe you're doing EW or radar work, we also have something for you. So I've linked a white paper here. At the bottom right, you can see a screenshot of Hayden Nelson, who's usually at this conference. It's the first year he couldn't make it in a long time. showing off the USRP X440 wideband capabilities. So like I said earlier, you have 16 megahertz of analog bandwidth that you can play around with. So what can you do with that? And that's what we talk about in this white paper. And it's definitely, it's definitely a solution that we'd like to provide. Okay. A huge hype that you've all been in touch with somehow, at least you must have heard of it, anything that's AI, ML related. And now NI is a test and measurement company. So a big question that we've been mulling around in our heads is how can we get involved in test and measurement when NI, ML systems are involved? So imagine you're a manufacturer of telecommunication devices that use machine learning. Like maybe this leads to unintended consequences of how the device works. Maybe you want to be really certain that despite there being these neural networks inside your device, they work in the way you've intended. How can you verify that that's true? Like what kind of validation do you have? And that's something we've been thinking about. And some of our colleagues have been working on that specific question in the domain of wireless systems. Now there was a cool little sort of side project that came out of that, which is the RF data recording API. This is something that came out of a collaboration with Northeastern University. It's a set of utilities that you can use if you need to create large data sets for training AI models. So you have a bunch of USRPs and you want to sort of capture or generate signals. This RF data recording API is a tool that allows you to capture a whole bunch of RF signals, store them as SIGMF data sets, and then use them as inputs to your AI training model. So you can use this for all sorts of applications. But the main work that this team did was thinking about how to test DUTs that are themselves ML-based. So here's an example of what we call a neural receiver. Neural receiver is really just a fancy word for saying we're going to take a modem, in this case 5G uplink, replace the existing classical receiver with its MMSE equalizer and whatever with a neural-based receiver. So the specific implementation is called DeepRx. It's not something that we created ourselves, but we integrated it and started to do some analysis and capture some data. On the right-hand side, you can see some BER curves and see how the neural receiver behaves differently compared to the classical receiver. That's the kind of result that you would get out of such a setup, so really useful. But how did they do that? And this is the setup, and I think it's a really cool setup. I just really love this slide because it has like so many components in there that are all really interesting by themselves, and then you put them all together to create this really cool product. So in the middle, bottom middle, there is a real-time channel emulator. It's based on PXI hardware from NI, and it can be used to generate RF channels. So when you're doing your test and measurement setup, then you don't have to rely on over-the-air transmission or anything like that. You can actually control the RF environment by having this channel emulator. And then we have a UE and a G-Node B based on the combination of OAI, open air interface, and USRPs. Put it all together, you have this end-to-end uplink that you can fully control. And on top of that is orchestration software that we also created. So, and this is the kind of test and measurement setup that you could use for testing ML-based DUTs. So in this case, what it did was, first of all, switch out the classical receiver with the ML-based one, the DeepRx-based one, so you can go back and forth between those. Also, modify the channel emulator to generate different environments, so you can actually have more realistic results. And then, play back the whole thing. So start an uplink signal, start a data transmission, and then on the other side, figure out what your data error rates were, like your block error rates or bit error rates, or whatever your metric is, and then see how they behave over time, over frequency, over varying channels, and so on. Yeah, so this is a really, really nifty, real-time capable testing setup of ML-based DUTs using everything that we have to offer. Like we have UHD, USRPs, OAI, and of course NI-based testing software on top of that. Yeah, this is a really nice project. There's also been papers and other conference articles published on that, so I can provide links to those. But for the rest of the time that I have, I actually want to go into things that we did build around USRPs and UHD in the last year. So, new features. Like I said, we didn't have any hardware, but that doesn't mean we've been sitting on our hands for the last year. We've been pretty busy improving UHD and also RF NOC. Quick raise of hands, like, is anyone familiar with RF NOC? Does that ring a bell? Have you heard of that? I see about half the hands, so that's great. That's really good coverage. So RF NOC, I don't have like an intro slide on that, is the architecture or the framework that we use to deploy IP on the FPGAs of our USRPs. So if you buy a USRP just off the shelf, turn it on, what you can do is you can receive and transmit data. You can pick the center frequency, you can pick the data rate, gain and like stuff like that. With RF NOC, you can also modify the data signal processing, like the data paths. So you can, if you need an FFT or an FIR filter or anything else like that, you can put that on the FPGA yourself. Now, in most cases, if it's custom signal processing and not something very standard, you might have to do some development by yourself on the FPGA, but we provide all sorts of tooling for that, which I'm going to talk about in a sec. But if you are just using standard DSP components like FFTs and filters, or other things that we might provide, then you don't have to do any FPGA development. You basically run a tool that says, hey, I would like to reconfigure my USRP to have an FFT in the data path, and push a button, and that's what we've been working towards. Okay, since last GRCon, we've had 2 UHD releases, and as you know, since we do open source development, every feature that we finish gets pushed public onto Git until the next release, so you can get a sneak preview of what's coming by following our Git branches. I'm going to highlight most of these bullets on the following slides. A couple of really small things, but things that I personally find really useful, I'm just going to talk about right now. So for example, really, really small thing, but I just love it. It's like just better release notes. So the last couple of UHD releases, I don't want to say I'm too proud of those, but if you go to GitHub right now, you look at the latest UHD release, 4.7, you get like a really nice description of what's going on. It's much easier to understand of what we changed, in some cases even why we changed it. And something else we've been asked a lot about, but I'm not going to talk about in the following slides, it's just finally updating the embedded Linux on our USRPs. So now they all run Kirkstone. I don't know the version number, we just use the code names. So, but that's a more recent version, and also, we have plans for keeping that up to date. All right, so I'm going to pick out a couple of these features for the rest of the remaining time that I have and go into some details. So first of all is the dual rate feature, which we released with UHD 4.6. So that was actually not too long after last GRCon. So last GRCon we introduced the USRP X440. I mentioned earlier the device with the huge bandwidth. One common request that we had was the ability to capture the L band in one go. So if you can digitize at 1600 megahertz of instantaneous analog bandwidth, that shouldn't be too hard, right? Because the L band goes from 1 to 2 gigahertz, so we have 1 gigahertz of bandwidth that we need to capture. Should be easy, except the USRP X440 has a pretty raw interface at the front. It has no mixers. You have to bring your own up and down conversion in many cases. It has many channels, but it does not have any filtering or analog front end like the other USRPs do. So capturing the L band is actually not as simple as it sounds, because what rate do you set your analog to digital converter to? The maximum rate that this device can do is around 4,000 megahertz. But if you set it to 4,000 megahertz, you get a Nyquist gap right at 2 gigahertz, and that sort of limits the visibility into your L band that you can capture. I gave a full talk about all of that last year. But what's the answer? Because you can't, you can't tune in an analog sense, and if you reduce the converter rate, then it gets even worse, because your Nyquist zone boundary will be moving right through your L band. And the hardware had the capability, and now the software does too, of using different sampling rates within the same USRP. It's something we haven't been able to do in previous devices. So in this case, you can run one channel at 1,024 megasamples and the other one at 1,280 megasamples. Gives you a different viewpoint onto the L-band, stitch that together, and there you go. That's your L-band coverage right there. And of course, that feature can be used for different applications than just covering the whole L-band. Like you could have a receiver at telecom rates running on one channel, but then a different rate receiver on the other channel. That's another option that you can do. And we've had to do all sorts of changes to the underlying framework. RF-NOC was previously unhappy about supporting multiple clock rates. Now it's fine. And that was sort of the main feature that came with UHD 4.6. And then with the recently released UHD 4.7, we've been making it much more accessible to use the FPGA capabilities of the USRP by making the RF-NOC tooling just much more easy to use, less error-prone, and more helpful. So we have a tool called RF-NOC Image Builder. Who's used RF-NOC Image Builder in the past? Not a few. Like 1, 2, I see 3 hands. And you know what? I don't blame you. Like the tool was not great. We've used it internally, but we also wrote it. So whenever it threw a random bug, we kind of knew what it meant. But we hadn't really sort of focused on the usability aspect of that tool. And that's something that's changing now. So with UHD 4.7, we've completely redone that. So a big problem that you might have is you could build configurations that were not actually that useful. So to sort of give you like the background, this image builder needs an input file where you describe what you want it to have. So I mentioned earlier you might want to have an FFT or an FIR filter. That's exactly what that file says. So you say something like, I need 2 channels, radios, I need resamplers, and I want an FFT on this channel and an FIR filter on that channel. Please go build that. And if you were lucky, it built you the right bit file. If you were unlucky, it built you a bit file, but that didn't work. If you were somewhere in the middle, it gave you an error message, but it might not be super helpful. And we've changed that by making error messages much better. And not only are they more useful error messages, they also give you an answer, like a solution. It says, hey, this doesn't make sense, but maybe try doing this. So I think you were trying to achieve that, but looks like you didn't do it correctly. What about this? One thing that we did to achieve that is to add all sorts of checks. I don't know if you can actually read that from back. I can't read this from here. So, but like the configuration files that describe the individual components can now be amended by checks. And these are really simple lines where it says, I want the number of channels to be less than 4 or something like that. And so basically at the very first glance at the configuration files, our tool can tell immediately if the configuration makes any sense. And this is also a feature that is available to anyone who wants to write their own blocks and put them into RF-NOC. GNU radio integration is getting better and better. So something that will be coming back in the future, and this is a preview, this is not completely done yet, is the ability to build bit files for FPGAs out of the GNU Radio Companion. So you have a graphical overview. And that is really nifty because, I like writing sort of text-based descriptions. I don't mind doing that, but they're not intuitive. They don't provide you like the right sort of haptical intuition of what's going on the FPGA, because like in the text file you say, oh, I want an FFT, you write that at the top, and then further down you say, oh, by the way, I need to connect the FFT with, I don't know, this other block. In the graphical representation, you can immediately see what's connected to what. So I kind of like that. And something that we've been asked about for many, many times is RF-NOC mod tool. Oh, I thought it was on that slide. Okay, that's fine. I have more on RF-NOC mod tool later. So I mentioned earlier, with RF-NOC, you can choose what's going on the FPGA. So you can say, I want an FFT, I want an FIR, and I want my radios, and I want to connect them in this way. However, that wasn't all the features that the USRP has to offer. So we've expanded the capabilities of RF-NOC towards people building their custom bit files as well. And one thing that we've added is the capability, at least for the X400 series devices, to also choose the transports that are available. So the transport is what puts data in and out of a device. So in case of the USRP X440, that would be either 10 gigabit or 100 gigabit Ethernet. So within the same configuration file where you choose the blocks that you want to have, you can now also choose which kind of transports you want to have. And you can connect pins in more configurations. So you could say, well, I'm not going to have any 100 gigabit Ethernet at all. I'm going to take these pins that are connected to the SFP at the front, pull them straight into my own block where I'm going to implement an LoRa protocol or something like that. So it gives you much more options. One thing that we've also added is make it easier to put in proprietary IP. So so everything in UHD is open source, and it's going to stay that way. That's not going to change. But we've gotten requests for people to drop in, closed source IP as well. And just to make that mesh more easily, we've also improved the infrastructure around that. Okay, so if you want to simply take existing filters, then simple math, splitters, combiners, those kind of blocks, you're fine. Like really that's all you need, but you might also want to write your own RF blocks and then include them in the design. That's also something that we've supported for a long time, but we also made that a lot easier now. So in the GNU radio world, you're probably familiar with the concept of out-of-tree modules. So you want to have GNU radio processing blocks that are not part of GNU radio, but you still want to include them in your GRC flow graph and whatever. The same concept applies with RF-NOC. So you can have your own RF-NOC blocks. And if you want to do that, you're going to have to write, Verilog or VHDL or something. So this is not for the faint of heart, but it's something that we've also made a lot easier. So in UHD, we used to have an example for an out-of-tree module called RF-NOC-example. And we've completely cleaned that up, redid that. It's now called RF-NOC-gain because it has a gain block in there. And it comes with a whole bunch of new features, including GNU radio examples. So, you just much better README file, explains what's going on, like what you put into each individual directory and how to use this. The GNU radio examples come in different flavors, and they're also just like part of the package. So this is also something we've just gotten a lot of questions, like, oh, how do I integrate RF-NOC applications in GNU radio? It's right there now. There's no more mysteries, or people have been sort of sharing secret tips on the mailing list. Like, that's nice, but really that's not what we want. We want it to be immediately accessible to everyone. And of course, RF-NOC mod tool is the utility that you use to generate the boilerplate if you want to create your own blocks, like a modem or whatever it is that you want to integrate on the FPGA. It's also come back with a 4.7 UHD release, and we'll continue to get more improvements. Just a small thing, but like a lot of people have asked about this, and I think it'll, it's one of those tiny things that will make some people's lives a lot easier. Like we've always had an FFT block. In fact, it was probably the first RF-NOC block we ever wrote, and it really didn't get a lot of attention. But we've, been redoing that, so this will be released soon. Increased size limit for FFTs. Now I know people have asked about million-point FFTs. We can't do those yet, but we can max out the available size of the Xilinx FFT IP core that we're using under the hood. So that 64K is now the new size limit for FFTs. But more usefully, we can insert and remove cyclic prefixes now automatically within the same block. So you want to build a, OFDM-based modem, do some pre-processing on the FPGA, boom, there you are. It's right there, part of UHD. Okay, that's the last feature I had. So I just wanted to encourage everyone to come by the booth. It's, where all the other booths are. Talk to everyone wearing an eye gear. Right now they're standing at the back of the hall, but usually they're standing by the booth. Also, we have an RF-NOC workshop led by Neil Pandya, whom most of you know. I think it's tomorrow. Yes, it's definitely tomorrow. Come on to us, talk to us, and like I said, if you have any challenges, something that we should be able to solve with USRPs, and you think we can, talk to us as well. All right, thank you very much, and I'm really glad to see you all again here at GRCon.
Thanks, Martin. Do we have any questions? Okay. I'm going to throw out the question, the obligatory. There are cases where maybe I have a FPGA board that's not part of the SDR. I'm not working with an SDR, but I want to be able to offload to an FPGA. Are there any plans to make RF NOC available to, say, a standalone FPGA or outside of using an NI?
I mean, we're not gonna go out of our way to do that, but it's also, it's open source. I know people have cloned it and put it on like CCU 1, 2, I don't know, like whatever the signing ports are called. So that people have done that, so it seems to work. But if you do that and find a bug in RF NOC and tell us about it, we're probably still going to fix it. But yeah, it's not a plan to sort of make that into its own standalone thing.
Okay, thank you. All right, let's do one more round of applause.
Okay, thank you.
All right, next up before the break, we have a few lightning talks, and a reminder as well that we have, not for today, but later in the week, we have more lightning talk slots available. So if you have an idea that you'd like to talk about, find someone with a white lanyard or go to the back of the room and let someone know. Oh. Sign-ups at the registration desk, I'm sorry. So our first lightning talk is going to be Clayton talking about the CTF.
All right, let's talk about capture the flag. First of all, who am I? My name is Clayton Smith. Online, I go by the handle Argilo. I'm also an amateur radio operator, call sign VE3IRR. And I am an SDR hobbyist. I love to play around reverse engineering protocols and building decoders and encoders for things, experimenting with hardware. So, what's capture the flag? This is not the type of capture the flag we're doing. We're going to do one that looks more like this. Capture the Flag is a game that became popular in the cybersecurity world. And the idea of a Capture the Flag competition in cybersecurity is that you have a bunch of servers, networks, computers, things that need to be hacked. And once you get in, you find little text strings called flags, and you submit those flags into the scoreboard and you get points by breaking into computer systems, reverse engineering, file formats, that kind of thing. Here at GRCon, we do a version of Capture the Flag where those hidden messages are embedded in radio signals. And so we have all kinds of weird and wild radio signals for you to analyze in our competition. Here's an example of one of the signals from a couple of years ago. These are a pair of narrowband FM signals. Normally they'd be at a constant frequency, but these ones are wandering up and down, and so you'd have to make a special receiver to be able to follow that frequency drift and track these signals. Here's another example of a signal painted into the waterfall and gradually fading away into the noise. So it's easy to see the first few letters there, flag, and they're kind of written upside down there. And then the letters of the flag itself are kind of fading away, and you had to figure out a way to pull that signal out of the noise. Here's another example of a signal you might find. This was a signal from a hidden transmitter that we had set up around the venue. And we have some like this again this year. And in fact, if you look between 432 and 434 megahertz, you'll hear one of these hidden transmitters broadcasting right now. And you can, if you can decode what it's saying to you, you'll already have your first flag. And just to give a feel for the sorts of weird and wild things we have, a couple of years ago we had a signal that was an analog NTSC signal, and had a bunch of flags embedded into it. You can see there was a QR code on the screen that contained one of the flags, and another flag was embedded in the closed captioning that you can see down at the bottom. So these are just some of the different ways that these messages can be embedded for you to find. We have all kinds of things ranging from beginner to expert, so there's really something for everybody. We even have trivia problems and other things. So even if you have no experience working with GNU Radio yet, drop by and you'll be able to learn and hopefully recover some flags and earn some points. If you want to join in, we have a chat channel on the Matrix server. Join the Capture the Flag channel in the GRCon 24 space. And we are on site in room 301, which is just down the hall. There's a map of the venue. We're in the ballrooms A and B right now. And over there in room 301A is where Capture the Flag is. There's a nice big banner right in front of the room that says Capture the Flag on it. So drop by and join us. The competition started today at 1 p.m. Eastern, 1700 UTC, and runs all the way until Thursday at 4 p.m. local time, 2000 UTC, and we're going to have a demo session on Friday at 2 p.m. where people will show off the cool solutions that they came up with for the CTF challenges. So that can be a really fun thing to look at, see how people solved the challenges that you didn't figure out, or see how somebody solved it differently from how you solved one of the challenges. If you'd like to get started, you can visit ctf.gnuradio.org or scan the QR code. It's all available online. You can play remotely, don't have to be here in person, and about 90% of all the challenges are available remotely. They're IQ recordings that you download, and so you can do that from anywhere. You don't need to be here. We do have a small amount of challenges like the hidden transmitters that I mentioned where you have to be here in Knoxville. So if you're watching remotely and want to join in and participate in those challenges, team up with somebody here on site and you can attack those together. So hope you have some fun in the Capture the Flag. Come see us in the room.
Thanks, Clayton. Do we have any questions for him real quick? No, that's kind of the theme today. Next up, we've got a lightning talk from Deep Wave Digital.
Awesome. So hi, everybody. My name is John Ferguson, and I am CEO of Deep Wave Digital. Today, I will be talking to you about our company, a little bit about our engineering philosophy, and then our latest product that just came out. Let's see. There we go. So if you've never heard of Deep Wave Digital, we build GPU-enabled software-defined radios. So our software stack, our driver set, seeks to abstract away the complexities of memory movement and data movement around in a heterogeneous computing software-defined radio so that you can focus on developing your application rather than those types of nuances. So our customers typically use our platform to deploy machine learning algorithms in a software-defined radio at the edge. So when I talk about machine learning and software-defined radio, what am I talking about? Machine learning on what? So we typically break apart the types of data that you can do machine learning on into two categories. There are the internals of the signal and the externals of the signal. So as far as the internals of the signal, we're talking about the actual data that you're trying to transmit from point A to point B over RF. So this could be audio, video, text, anything like that. So when you're doing machine learning in this regime, This is what's more familiar to the rest of the world, right? So doing things like automatic speech recognition, natural language processing. When you're talking about the externals of a signal, outside of this room, it's pretty nuanced, right? So we're talking about applying machine learning actually to the complex valued baseband RF data. So in this world, applications are typically things like spectrum survey, geolocation, modulation recognition, or even adaptive communications. So I bring this up because what we try to do at DeepWave is make it so that it's the same workflow whether you're doing the internals of the signal or the externals of the signal. So our platforms don't care if you're using GNU radio to demodulate a FM broadcast and sending that to an NLP algorithm to get context. It's the exact same workflow if you were to be down converting an RF signal to complex baseband and sending that to an application to do spectrum survey. So this is our latest hardware. This is the AirT Embedded series. It comes in 3 different variants, ranging in capability, and it's completely, or it's powered by the NVIDIA Orin NX modules. So talk about a few specifics of this. So like I said, there are 3 different variants. On the left, we have the Air 7311, which is the most capable higher end variant, and then down to the Air 7301, which is the lower cost, more scalable variant of the new AirT Embedded series. So I'll talk about a few specific feature highlights. So in terms of the software-defined radio, I really like the 7311 because it has 2 transceiver daughter cards. These can be synchronized or they can operate independently. So you can operate in a 4x4 MIMO or direction-finding applications, or you can separate them out and tune them to completely different frequency bands and bring all of that data synchronously down to the same GPU or same machine learning algorithm that you're trying to deploy. All of them have heterogeneous computing, AMD FPGA, ARM CPU, and then of course the NVIDIA GPU modules. And we have put a large amount of data storage on this. So one of the problems that we typically run into is the inability to just store data when you have an edge deployed system. So we put 2 terabytes of data storage on this, or up to 2 terabytes of data storage, which is great for recording baseband data in order to build machine learning data sets for training purposes. And then the feature that I am most excited about is the fact that this is powered by PoE++. So no longer carrying around a power brick to provide 12 volts or 18 volts to your radio. Just plug it into a PoE capable switch and it significantly improves how deployable the system is. So no hardware is complete without a good software stack. So our software stack is called AirStack. You can think of AirStack as the framework that allows the communication between the RF subsystem, the NVIDIA GPU module, and whatever API you want to use to build your application, whether it be PyTorch, TensorFlow, or GNU Radio. So we're managing under the hood the movement of data and the intercommunications between all the different devices on the radio. And then finally, I'll leave you with this. So we like to think of our hardware platforms as a desktop environment in an embedded form factor. That means that we strive really hard to make sure anything that you use on your desktop to do research or to deploy your applications should work on our radios. So if you want to use pip, conda, Docker, any of that stuff, just works out of the box on our platform, and that's to enable you to do the data reduction at the edge. So our hardware is not going to be a platform where you're streaming 16 kilobits per second over an SFP plus or multiple SFP plus ports to a sidecar computer. We put the computing on the radio itself so that you're streaming those data rates directly to the compute module on board, so that what you get off is the answer to whatever your algorithm is doing. So we have a booth over here at the convention hall, and come see us if you want to chat about our hardware. And thank you for your time.
Thanks. Do we have any quick questions? I knew the answer to that. All right, we have one final lightning talk before the break. Okay. We need to find the final lightning talk. So if anyone wants to think of a question, you're welcome to do that now. Would you like to ask yourself a question? Make it a nice softball.
Yeah, so this we're going to have to defer till tomorrow. I wanted to make an announcement. Anyone that's interested in learning more about SETI Breakthrough Listen, they're getting a group tonight together. If you want to learn more about that, find out at the SETI booth in the expo hall. So we'll meet back here in 25 minutes at 3:20. All right, thanks everyone.
So, welcome back after the break. We're hitting it right off with Zachary Hicks talking about Pluto-PYNQ, how to use and enable FPGA accelerators in a low-cost SDR. Give a warm hand of applause for Zachary.
Hello, everyone. My name is Zack Hicks. I work as a communications engineer at the Johns Hopkins University Applied Physics Lab. I'll be presenting Pluto-PYNQ, enabling FPGA accelerators in low-cost SDRs. That's specifically the Pluto-SDR and derivative platforms. This research was completed as a part of my master's thesis at the Johns Hopkins University Engineering for Professionals program. So I'd just like to thank the EP program for sponsoring my presentation at GRCon this year. One, two. Here's a quick agenda. I'll talk through some of the motivation here, a quick background on what PYNQ is, if anybody's unfamiliar, talk about the details of building a PYNQ Linux image for SDR. I'll show a DSP overlay example for the ANT SDR, and then wrap up with some conclusions. So bottom line up front here, PYNQ is an embedded Linux image that provides a Python environment for designing, loading, and using FPGA accelerators on Xilinx Zynq SoCs. So what I accomplished in this research, I was able to boot a PYNQ image for the Pluto-SDR using an external USB root file system. This included the integration of the analog device's Yocto layer to include those RF transceiver kernel drivers. Unfortunately, during the course of my research, I encountered an unrecoverable kernel boot failure after attempting to integrate a kernel patch for those ADI drivers. So I pivoted under the time constraint of my thesis research to use the ANT SDR E200 to implement a demonstration hardware accelerated FM radio receiver. So the motivation for this research was really how to isolate the FPGA in software-defined radio for beginners. So as everybody here knows, SDRs are very complex and multidisciplinary devices, but learning DSP hardware should not require the implementation of a full embedded Linux system. So my research question was, how to isolate the FPGA to make implementing signal processing as simple and low cost as possible. Quick overview of PYNQ. So PYNQ is an open source Python framework for Zynq SoCs. The block diagram on the slide here kind of shows the different layers that make up PYNQ. At the very bottom layer, you have FPGA accelerators that are bit streams. They're called overlays. PYNQ provides some Linux kernel drivers and a Python API for controlling your bit stream from an interactive Jupyter notebook that runs on the embedded system, and you can connect from your host computer. PYNQ is made up of two primary components. There's the PetaLinux kernel. PetaLinux is the Xilinx tool for creating Linux images for their SoCs. And then PYNQ uses a full Ubuntu root file system. The fundamental trade-off of PYNQ is a simplified path to hardware-software co-design at the cost of efficiency. So because this is a Python interface and it's kind of all done for you, this is not a very high-performance system, but it is very easy to integrate. Xilinx sells an RF system-on-chip development kit to academic customers called the RFSoC PYNQ. There is first-party support for a PYNQ image that includes a Python API for the RF data converters and some demonstration Jupyter notebooks that show DSP overlays and visualizations of like transmit and receive chains. However, this kit costs over $2,000, which is not really accessible for like students or hobbyists. So I was trying to emulate some of this capability at a much lower cost. So the right SDR platform has to be affordable for students and hobbyists. It has to have FPGA DSP resources and has to be compatible with PYNQ. So the radios that kind of meet all these requirements are the Pluto-SDR and derivative platforms. Some issues with the Pluto-SDR when it comes to PYNQ. There's not enough flash memory to store that full PYNQ image. So the Pluto only has 32 megabytes of onboard flash memory. And like I mentioned before, PYNQ uses a full 8 gigabyte Ubuntu root file system. There's also no existing PYNQ support for any analog devices IP, specifically their fork of the Linux kernel that includes all the RF transceiver drivers. The ANT SDR is a Pluto-SDR derivative platform. It's basically the same hardware plus an SD card slot and gigabit Ethernet. The SD card slot kind of solves that flash memory limitation. But some issues with the E200 are, it has a long lead time, and there's less support and documentation in the Pluto-SDR. That's kind of one of the great benefits that the Pluto provides. Here's a photo of the Pluto-PYNQ hardware setup. It's kind of Frankenstein together. You can see the Pluto-SDR on the far left, connected through a USB on-the-go adapter to a USB hub. The external USB storage is used to store the Linux image and the root file system. And then the USB JTAG bridge is used to interact with the U-boot console to actually boot the PYNQ image. The total cost of all these components comes out to $320. Here's a photo of the ANT-SDR E200 hardware setup. You can see it's a much simpler setup, primarily because of the addition of the SD card slot. The total cost here comes out to $329, only $9 more than the Pluto, plus all the added accessories. Here's a quick flow chart of the Linux boot process on the Zinc 7000 SoC. The two pieces that are really relevant for PYNQ are the second stage bootloader and the kernel. So in the analog devices Pluto-SDR firmware, they already support booting FIT images. This is a Linux kernel image format that kind of combines all of those three components into one binary file. And they also already enable the USB subsystem. So in order to boot your own Linux image on the Pluto-SDR, all you have to do is load it onto a USB storage drive and then load that image into RAM from the U-boot console, and then you can just boot into Linux from there. So the Pluto-PYNQ system actually did not require any modification of the Pluto-SDR firmware in the flash memory. You can see on the slide there just some outputs showing the USB storage detected. The PYNQ system uses the Petalinux tool, which is, like I said, the Xilinx tool for creating Linux images on their SoCs. Petalinux allows you to configure kernel features through a menu config, and then all that configuration can be exported as a board support package. Petalinux is built on top of Yocto, which is an open source collection of recipes and tools for creating embedded Linux images. This contrasts with Buildroot, which is kind of the other tool for creating embedded Linux images. That's what ADI used to build the Pluto-SDR firmware. So basically, I just had to take all of the Buildroot kernel config and map that into Petalinux and Yocto. Once that was done, I had to add the analog devices meta ADI Yocto layer that allows the integration of their fork of the Linux kernel and all of the device drivers required to control the RF transceiver. As you can see, a couple screenshots from the Petalinux menu config on the slide that showed the integration and enabling of the 809361 kernel driver. On the user space side of the Pluto-PYNQ image, all of the IAO software is required to actually enable control of the transceiver from software. So you can see all of these software packages were included in that Ubuntu root file system that allows software running on the Pluto-SDR to control the RF transceiver. And also IAOD was included to allow control from remote contexts. So this enables the Pluto-PYNQ system to kind of become transparent to a host computer. So when the system boots up, you can still stream samples into GNU Radio on a host computer totally transparently. It the system doesn't know that it's running PYNQ. Microphase is the manufacturer of the ANT-SDR E200. They provide a PYNQ image for their radio. However, they include the ADI kernel drivers using a 900,000 line kernel patch, not the meta ADI Yocto layer. And then they build their device tree overlays using the PYNQ PRIO project from a research group at BYU. Their microphase PYNQ image did not include any of the user space transceiver control software. They required on-platform installation of all the IAO and Python bindings software. So I created a repository fork of their repo to add in all of the missing IAO packages and automate their build process. Like I mentioned earlier, I encountered a boot failure on my Pluto-SDR during the course of this research. So I attempted to integrate the ANT-SDR kernel patch into my Pluto-SDR image. The Pluto failed to boot using this kernel patch, and strangely, all future boot attempts also failed. This included using Linux images that did previously work, and this failure persisted across a full restore of the U-boot firmware. So I'm not really sure what went wrong there. Under the time constraint of my thesis, I had to pivot, so I used the ANT-SDR PYNQ image that I modified to assure that I could create a demonstration overlay. ADI provides a great HDL reference design for like the Pluto-SDR, FMComs2, kind of all those derivative platforms. You can see the data path shown on the slide there. So I broke the received data path between the AXI interface that actually controls the RF transceiver and the receive FIFO. I inserted an empty overlay block diagram in the Vivado project to serve as a wrapper for user signal processing logic. Within this overlay template, basically I provide the user with only the signals that they need to implement signal processing IP. So there's a sample clock that's generated from the transceiver and buffered into the Zinc FPGA fabric as L clock. The frequency is derived from the requested sample rate on the transceiver. All the signal processing is done on L clock to avoid crossing clock domains, so keeping it simple. And then there's an asynchronous reset provided from a PYNQ GPIO signal from the PS on the Zinc. So basically all the user needs is the data signals, the valid signal, clock, and reset. Along with my overlay template, I provide a test bench. So this allows you to instantiate an HDL wrapper for your PYNQ overlay, just for verification of whatever signal processing IP you've implemented. So this allows you to load your own IQ file and set your sample clock rate, etc. So FM radio receivers are kind of the hello world for wireless communications, so that's what I chose as my demonstrator overlay. So you can see this is just a stock GNU radio, all software FM receiver flow graph. And what I did was I took the rational resampler that performs an initial decimation by 5 and pushed that into the FPGA. So here's the Vivado block diagram for those decimation FIR filters. I implemented this somewhat trivially using the Xilinx FIR compiler IP, and then I generated the impulse response using Python. So this produces kind of a heterogeneous DSP system where the FPGA overlay provides the initial decimation by 5. That reduces the sample rate required to be transferred over that Ethernet or USB interface. You then stream the samples to the host computer at a lower sample rate, and you can perform the FMD mod in software. So here's a demo video of how this works. So you can see in the lower left, there's the Linux kernel boot logs from the ANT SDR. Once we get into user space, you'll see the device tree overlay nodes that are added when the base image is loaded. So then in GNU Radio, you can just run a FM radio receiver flow graph like PYNQ is in there. So then I'll go to the Jupyter Notebook interface, and I'll open up the decimation FIR filter Jupyter Notebook. Here in this notebook, you can see the Python code used to load the overlay. So first import the PYNQ Python packages that are required, and then load the overlay bitstream from the Jupyter Notebook. And then I will assert and deassert the asynchronous reset signal. You can see in the lower left, the device tree nodes being reinserted. And then back in GNU Radio, you can see the same FM receiver flow graph.
Running down a hill can lead to that pain.
Demodulating an FM radio station, but the initial decimation by 5 is now being performed in the FPGA, totally transparently. So some takeaways in future work here. PYNQ might not be the best choice for some of these resource-constrained platforms. So although this did work, what I was hoping to be able to do was stream samples through the IO interface on the platform, do some initial software processing on the Zinc CPU, and then transfer them via ZMQ to a host computer. That turned out to run pretty slowly. I think there's opportunity to improve that using like the C++ bindings that are being developed for PYNQ, or maybe just a lighter weight framework that doesn't use PYNQ. Some future work, obviously repairing the Pluto-SDR PYNQ image would be the first thing that I'd like to do. And I think it would be also nice to pursue some tighter integration into GNU Radio. Right now, all of the signal processing that's happening inside the FPGA is not really obvious from the GNU Radio flow graph. So I think it'd be great to allow overlay loading directly from the flow graph and provide some indication that processing is being done on the samples before they arrive into GNU Radio. That's all I have, so take any questions.
Are there any questions? Yes.
Yeah, good work. How long did it take you?
I started this work in January of this year, so it was January to August.
Yeah. Oh, so I might have missed this, but what was the benefit of running the DSP and the FPGA over running it on the companion computer and software like you would normally do?
Right. The idea behind this research was really more for like an educational application of like, how do you make it a lot easier for somebody to start learning about FPGA DSP? And like I said, I think providing a sandbox like the overlay template that I have where the user is just presented with a data signal and a valid signal and a clock kind of makes it as easy as can be. You don't have to fight with any Linux components. You don't have to fight with anything else on the FPGA. You can just implement signal processing algorithms.
Okay, we're running out of time, so give a warm round of applause to Zack.
Thank you.
So, up next we have Neil Rogers, who's going to tell us a bit about a course, a two-course part course. So, please welcome our next speaker.
All right. Thank you very much. As he said, my name is Neil Rogers, and I'm a professor of electrical and computer engineering at the Air Force Academy in Colorado Springs. And I really wanted to get up and talk about how we've taken some of the applied software-defined radio concepts and moved them into our theoretical class, which I think is providing a great benefit to the students. And I have to say from the get-go, like, just being at these conferences has really kind of inspired this work. Being a part of the Capture the Flag challenges, meeting people like Mark Lichtman and Marcus and all the people that have to do, that do. Can I dive right in? Let's see, am I number 2? Or am I number 1? Thank you. Okay, so I have to give this slide. You have to know that even though I work for the government, I don't represent the government. There we go. Okay, so I'm sorry. I like to wander when I talk, and I don't have a lapel mic. So what we're trying to do here, jokingly, right, is make undergrad comms great again. We all kind of took an undergrad comms class away, and we said, okay, I know how to calculate this power spectral density. I know Parsifal's theorem. I know the Wiener-Khinchin theorem, right? And I know how to do that math. But so what? Right? And then we walked away and we thought, well, I don't really have time to study this again. So what I'm trying to do is really accomplish 5 objectives. The first is to generate renewed interest, right? Communications, especially from a military perspective, is going to be something that we have to think about a lot. We have to be able to provide communications while hopefully denying it to our enemies. So this is something that I want my cadets to be interested in, but they're not when they walk away from this, from the old version of this class. So how can I generate that renewed interest? How can I take the curriculum and modernize it so that we incorporate some of the topics that, especially the things that we talk about, like the research that's happening at the graduate level, right? If we want to generate interest and generate kind of a pipeline where we're motivating students, we need to have modern topics. Of course, I want to be the best possible teacher that I can be, and so I want to implement the best practices of pedagogy as I go. And then I want to maintain a strong theoretical foundation while I do that. So I don't really want to get rid of that theoretical foundation because that's important stuff to know, but I want them to be able to tie that to the real world. And the way to do that is by implementing hands-on learning, just like we heard from our SETI friends earlier today who talked about that, right? And the compelling questions that we can get them to ask in the presence of software-defined radios, I think, are the things that are going to help us accomplish all of these things. And really, in the end, I want to build spectrum-aware technical leaders for the next generation of my Air Force and of our military, and then of our commercial sector, who are going to continue to help do things like develop SATCOM radios. Right? I just heard that the new iOS has a SOS feature that uses SATCOM radio, which is super awesome, that you can phone home from your iPhone. Even though I don't have an iPhone. Okay, but a caveat first, right? So I feel very much like an imposter. I inherited this course sequence because we had a professor who retired, like 2 weeks notice over Christmas break, and they called me and they said, Neil, you're up. You can spell RF, so you've got all his classes. So I got EMAG, I got the comms class, both the comms classes, and away we go, right? So, so in some ways I feel like an imposter, but I also feel like that helps me think a little bit outside of the box, like, hey, I know we've done this way in the past, but what are some new things that we can do to get away from that to help students be more engaged, right? And so those are the questions that I'm asking. And so when I ask myself, like, how did I find myself here? Really just kind of by coincidence and by the fact that I was there when nobody else was. Okay, so I thought I'd take maybe a little bit of a break here and tell you about USAFA, right? It's not your typical four-year school. The cadets show up, and within, like, the day they show up, they look like this, right? They go through an intense physical and leadership training program, starting with a 6-week basic training before they even see me, right? And this is, they don't see me till their junior or senior year when I start to teach this course, but it certainly shapes their framework, and it shapes their mental model about how to learn. In addition to that kind of that introduction to the military, then they take on a really rigorous academic program that consists of probably a more extensive core sequence than any other university that I've been at. So they take something like 90 credits of core classes, and that includes everything from English to basic electrical engineering to computer science, right, philosophy. They have a ton of core classes that they have to do, so they're always crunched for time, always crunched for time. They also, while they're going through that rigorous academic sequence, they have some, military training that they're doing on the weekends and in the evenings. And by the way, all these pictures I just pulled from the USAFA Flickr, right? So these are all like public domain things. Really cool to go in there and look, and you can see what me and my cadets kind of go through on a daily basis. So in addition to academics and military training, as if that wasn't enough, they have athletic requirements that they have to meet. So this is a picture of my CrossFit team that are competing against Army at the time, and Army won, unfortunately. All of that goes to say this is kind of what their day looks like. You can't see this, right? But they have a block schedule, so we have M&T days or A and B days, and they're scheduled from 05:30 in the morning or 06 in the morning until 2300 at night. So they are busy, busy, busy. So while I'm asking these questions about the comms classes, I have to think about what they're doing that have nothing to do with my class, because if I make this class too intensive or too hard, then I'm certainly affecting other parts of their lives. But that's not to say I'm making it easy, right? That's not to say I'm making it easy at all. In fact, the thing that I want to do is keep the difficulty while raising the level of engagement, because when they care, that's when they're going to put forth the best effort on it. Okay, so we're really talking about two comms classes here. The sequence is our Introduction to Communication Systems, which is going to be, which is going to be our ECE 447. So I'm going to continue to reference these by class number because that's easier for me. And this is the first in the sequence that they would take as a senior during this semester, their fall semester. So I've actually got cadets that are in class right now taking that class. And here we're trying to give them just the theoretical foundation. And this is the class that I think probably benefits the most from our reorganization that we've accomplished. And then the second class was really kind of divorced from that. And the second class was an application of software-defined radios, where we start to look at GNU radio and how can we use GNU radio to teach them about real-world signals? And really what we end up doing is just kind of teaching them an introduction to software-defined radios as a whole, because we couldn't get too deep into it. And I'll explain that here coming up. So if we just take a top-level look at the two syllabi, right? So these are kind of the main topics that we hit as we go through the courses, and this is before we did the reorganization of the class, right? So this is kind of what I walked into. I walked into the situation where we've got, on the left, 447 has a bunch of topics that look familiar, and probably to you, you go, yeah, you need to know that, right? And it's true, you do need to know that. We need to understand Fourier. We need to understand amplitude and angle modulation, right? But the two kind of pinkish red topics, that's the only place where they actually put their hands on equipment. Two labs, maybe three if we got lucky. And those were like an AM lab where we measure the modulation depth, and an FM lab where we do the same thing and we measure the power in the sidebands, right? So, and then the digital modulation lab where we might take into account the effect of noise on your probability of error, right? So those are cool topics, right? But you're looking at a key site you're looking at a function generator, you're looking at a signal generator that's doing the modulation, right? You've got this, $50,000 worth of equipment on the table, and that's certainly a different situation than maybe if you're sitting overseas somewhere worried about electronic warfare or looking at the spectrum, which are the kind of things that I'm trying to prepare my cadets for. So the right-hand course, the one 448, looks pretty good, right? Lots of hands-on activities. We're doing lots of things with GNU Radio. They're engaged. And so I'm pretty happy with that. But there are some challenges. And so I'm going to kind of talk about the challenges with each course right now. So again, with 447, just really 2 or 3 hands-on activities. And that gives very few lessons where we're able to give them concrete applications of communication systems. And minimal connection with the next course, right? So in fact, the first course wasn't even a prerequisite for the second course. And so if I'm going to make a course sequence, I should probably try to tie those together as well as I can. And then what that resulted in, right, was just an over-reliance on theory and cadets that ended up having, as much interest as getting off the couch as my dogs do. So, which is to say not very much. And the result is, right, we have graduates that are kind of lacking. They have gaps in their experience and their education. So now if we switch over to the other side and we take a look at 448, all right, again, I'm pretty happy with this sequence of things that we're teaching them. We're starting to look at some representative modulation types that we're maybe more interested in, more relevant. But I ended up teaching a lot of lessons just troubleshooting the hardware and the software. Like, what's the buttonology of GNU Radio? How do I create a flow graph, right? What are the data types that we have flow through it? And what are the implications of using complex data versus real data, right? We have to kind of teach all of that stuff, and that can get in the way sometimes of the cadets, backing up and looking at the modulation. Hey, what is this signal actually trying to tell me? And so again, I have really little room to give them experience in real-world signals. And they struggle with their final project, which is supposed to be an applied project that they get to pick and they get to define and they get to build whatever they want to build. But they don't have the tools to do it. They don't have the kind of intermediate skill set that I need them to have in order to do that. So again, the end result is I've got graduates who have gaps in their education and their experience with regards to real-world signals. Okay, so going back to my goals here of addressing the issues, if I want to generate renewed interest, right, how can I do that? Well, I can bring software-defined radios in earlier. I can bring them in earlier to the sequence. Okay, well, how do I modernize it? Well, we want to look at real-world signals. Okay, if I want to improve my pedagogy, I want to give them a hands-on experience. I want to have them, putting their hands on equipment and really receiving signals and doing the demodulation themselves, rather than just learning theoretically about how to do it. And at the same time, I want to keep that strong theoretical foundation. And so I need to identify the core material. Here's the stuff I absolutely need to keep and teach them, and then try to make some room for that applied stuff, so that they can make every class interactive and apply that hands-on learning. Okay, so we're gonna do that. We're gonna make the classes great again. So here's again a view of what I walked into, the previous situation, and when we make it better, we kind of look at how we can reorganize that. Here's what the situation looks like. So you can tell right off the bat that there are many more applied lessons in our early class, right? So I've taken some of the introductory software-defined radio material from the second class and pulled it into the first. In fact, we're on lesson, I think, 14 today, 14 out of 40, and our cadets have already installed GNU Radio and built their first flow graph, right? And so, as opposed to not having done that until late signals, right? And so now the lights start to come on, and we can listen to AM radio, and we're lucky. We have an AM and FM radio station that broadcasts right down the hallway from us. You actually can't hear it from my classroom, but we can get plenty of radio stations in there. After we do that, we're going to go back into some theory for angle modulation, so we're talking specifically about FM here. And we're going to do another lab where we, again, put them on the benchtop, traditional lab equipment, and then we're going to turn around and we're going to do it in GNU radio, right? So you see this theme of like, teach the theory, do the lab, then do it in GNU radio. And what I'm trying to do is tie those three threads together so that they really trust what GNU radio is doing behind the scenes, so that when I give them a flow graph and say, no, this is really going to help you demodulate this thing, they actually trust that it's going to work, and they have some idea of what's happening behind the scenes. So we do GNU radio, FM, and then we have to talk about noise. This is kind of an ABET thing, but it's also important, right? Noise is everywhere. It can cause interference, pass interference. I guess I ought to laugh at my jokes. I know it's the afternoon, but it's funny. All right, we talk about probability error of error, talk about bit rate errors and things like that. And then we move on to digital modulation, things like ASK, FSK, PSK, and they do a lab where they kind of measure the bit rate error from a pseudo-random sequence. And then they're going to take that and, yep, we're going to do it in GNU radio, right? And I haven't even really called out where all the curriculum that I do the GNU radio stuff comes from, but like Barry has done a tremendous job of building up the GNU radio tutorials, and there is no reason for me to rewrite that stuff when there's excellent resources available. So I literally pull up the GNU radio wiki, and I say, away we go. And I start to kind of fill in the gaps and help them walk around and help them build these flow graphs so that by the end of the class, they actually all have it kind of up and running. So we build the FSK tutorial, and then I say, okay, the FSK tutorial kind of stops at like, we've recovered the original bit stream. But then I don't want to take it a step further and say, okay, now I want you to develop a decoder to take that bit stream and turn it back into ASCII. So we start with ASCII, we do the modulation, the filtering, we do the transmission, we have a noise source, all of that, and then we do the demodulation. I want to have them do the decoding, and usually they'll do it with the ZMQ sync off board. And that teaches them a whole lot about what GNU radio does with its data flow, right? You get these lists of arrays, and they're ones and zeros, and what the heck do I do with them, right? So we teach them how to process the data that's coming out of GNU radio and how to interpret that. Right, how to take a look at that data and say, okay, this is what that actually means in the real world. And that ends up being a really great project. Well, then I have to do a final exam because the Air Force Academy says I have to do a final exam. So it's comprehensive. And oftentimes what I'll do here in the final exam is I will, I'll put in some flow graphs and I'll have common errors, right? Sample rate mismatches between blocks that aren't connected, right? Things that they should kind of pick up along the way. And that's my way of testing to make sure that they have GNU radio literacy, because when they all decide that they want to take the next class, we're going to pick up right where they left off. In fact, we're going to start right with that, one of the modulation techniques that we talked about in detail in the previous class, and that's how they get their syllabus. So they actually have to demodulate and decode their syllabus, otherwise they can't start the class. And this is a whole lot of fun, right? In fact, I had some cadets that were like, okay, this is really cool, but I don't get it. And I was like, okay, well, you weren't, I guess they lose everything over Christmas break, right? It's what students do. But a really cool way, I think, to kick off the class and say, no, we're going to be all about applied communications in this class. And we have to do some things like talk about signal space and talk about different kinds of, antipodal signals and things like that. So we do that kind of at the get-go, talk about noise figure and link budgets, because those become important when like, hey, why can't I talk all the way across the room, right? It's because of the link budget. And then we're going to jump into the excellent paper that Dr. Mathis from UC Boulder wrote. I think it was like 8 years ago at this conference, and I still go through it in detail because he gives such a great treatment of how you can kind of unpack things in GNU radio and use them in terms of match filters, in terms of how to create, serial to parallel or parallel to serial conversion and things like that. So I walked through his paper, and every single one of these projects that we're going to do has a homework assignment tied to it. And the homework assignment isn't tell me why. No, it's take what we've done and extend it further, right? Make it better or do something else with it, because that's the starting point. And inevitably, I found that the cadets respond really, really well to that type of teaching. So after we do the PAM, we're going to talk a little bit about out-of-tree modules and how you build them and how you use them and why you might care. Turns out this is kind of hard to do in Windows, right? As great as Radio Conda is, VS Code is worse. And so we have a hard time getting things sometimes set up in the environment. And all my cadets come by default with Windows, so I have no way to kind of get away from that. And then we'll start to dive into some custom signals. Some things like CW, where we're gonna take Barry's CW generator, and we're gonna have them build a decoder. How do we decode CW? And then we actually I put up my phone, which has a CW app on it, and I start to send messages, and hopefully they can receive those through their GNU radio decoder. And then we're going to take a look at things like HD radio. So Vlad, I think Vlad was in the room. He created a great challenge last year as a part of the CTF that had wideband FM. And so we take a look at that and what you can do with digital sidebands as opposed to the analog, main band. We take a look at ADSB and AIS, because these are real-world signals that make use of incredibly simple modulation technology and are really effective, right? If you look at the low power of ADSB, blows my mind that we can actually transmit that, and we rely on planes to not fly into each other because of that, right? That's pretty impressive for me, so I like to dig into that a little bit. And what I'll do here is I'll actually give them some exposure to the standards, right? We'll pull up the standards document, we'll look through it, and we'll pull out the relevant information about what the modulation type is, what the pulse length is, right? What the power needs to be, all these things. And then they start to hopefully tie these concepts together, that they're not just blocks on a page, right? But they're real-world components that are creating signals that we need. Okay, we'll do DTMF because it's fun, and it's always fun to have 8675309 pop up as the answer. And then we'll take a look again at the excellent MPSK tutorial on GNU Radio's webpage, and this is great to talk about pulse sampling and timing and synchronization and multipath and how you use equalization, right? All of those blocks. This is a fantastic opportunity to do that. Move on to FHSS, where I'm using, I think the user is Solomon on Medium, wrote an excellent kind of write-up on how you would build an FHS frequency hopping generator. And my friend Sandia in the back have a lot of good things to say about de-hopping, so we can think about that for the cadets and their final projects. We'll do some reverse engineering of an on-off keying fan remote that you can buy from Lowe's. It's really neat to take a look at this and see what we can find out about the waveform and whether we can recreate it. And their project is actually to turn the lights on with a hack RF. And most of them end up doing it, which is really kind of neat to see. And then we do fun things, right? Like take a look at the SIG-ID challenge from a couple years ago. This has a lot of great signals buried in it. It is a great opportunity for them to practice those topics. And kind of the last thing that I want to talk about is their final project, right? So in this final project, they have the opportunity to define what they want to do. So they give me a proposal around midterm that says, here's what I want to do. And I come back and say, whoa, that's going to be way too hard, right? That's going to be way out of your range. Let's not do that, so let's scope it back. Or I say, no, you can't build an AM generator, right? That's way too easy. So I try to get them to scope it appropriately, and then I have them give me a little bit of background research, and then they have to come back a few lessons later with a prototype description or a design description, and then they have to finally present their work at the end of the semester in a presentation and a final report. And so what I'm getting them to do with these milestones is build up almost a publishable paper that they could say, okay, now I know how to write a paper. I know how to do research. I know how to scope a project. I know how to describe a design. And I know how to test and verify that things work. And so by the end of this, it's a whole lot of fun. So a couple of cool examples. I had a cadet last year that took GR-NTSC and actually fixed it to work with PAL. So we can do PAL. I got 5 minutes or I'm done. Okay, cool, thanks. So we can decode and demodulate PAL and NTSC with the same blocks. And in my world, there's a whole lot of use for this kind of technology. So I was really excited when he was able to pull off the PAL demodulation on the bottom. I had a cadet that recreated a PPM-based RC controller. And he was able to take an Xbox controller, link it into his computer, have GNU Radio take the input of that, and then broadcast the proper PPM signal to make the thing move left, right, up, and down, which was really cool. And then I had a student last semester that kind of did the NOAA imagery, right? And yes, this is built into a lot of software packages, and he used that. But the hard part of this was he built his own antenna. So he built his own antenna, and he realized that the antenna didn't work so well on our terrazzo, which has a bunch of rebar underneath it, right? So he took it out of our environment and took it to basically a forest in the middle of nowhere, and was able to get a clear line of sight for the satellite overpass, and was actually able to decode the signal. I told him at the beginning of the class that I didn't think he was going to be able to do this, and he pulled it off. And so it's a lot of fun to see cadets kind of take those tools and say, okay, now I believe what I'm getting out of them, and I kind of know how to work with them, right? These are the kind of cadets that I want to be sending into the Air Force that understand what the spectrum is, especially when we start thinking about drones and we start thinking about communications being denied or GPS going away, right? Those are the kinds of things that really keep me up at night, and the things that I want my cadets to recognize what's happening when it happens. Okay. So how did I do, right? I don't have any formal feedback because I've really only done this for one semester, but the feedback has been great, right? Our students say, yeah, that was one of the best classes we took. In fact, after I gave the CTF challenge for their midterm exam, I gave it to them over a weekend and said, do as many flags as you can. They came back and they said, that was one of the best assignments that I've ever done, right, at the academy. So wherever Clayton is, thank you very much for writing that challenge. And my perception is that the students are really enjoying it. The engagement has gone up, the grades are really good, and the students are putting in a ton of effort, right? And so this is, and the level of achievement that I'm seeing on their final projects is very much in line with what I would want to see for cadets who are doing no-kidding research and able to publish. So we have a couple of comments here. Oh, I actually got an email from a cadet who graduated and said, hey, my boss is amazed at what I know how to do with software-defined radios because of your class. And so I was like, wow, I feel justified in what I'm doing, right? And this is really what I want to do. And I'm not done, right? We still have a lot of challenges to overcome, to include student laptops come in varying states of disrepair. Some of them have Windows and some of them have Windows that don't work. And we have a variety of different operating systems that we have to deal with. And so we're still working on a software baseline that makes sense. I think I still got some tweaking to do on the organization and how we order the classes. And of course, I need to make sure that I'm keeping ABET happy with some of the things that our first course provides, like applications of probability and statistics. So like making sure I really hit the noise and the random signals in enough detail to satisfy that requirement. Those are the things that I have to do. So thank you very much. I appreciate you sticking in with me. I think I got my 30 minutes in. And yeah, are there any questions?
Yeah. OFDM in your course?
Yeah, so usually that falls under the special topics, even though I know it's not a special topic. And sometimes we hit it with the HD radio because those sidebands have OFDM encoded data. So yeah, great question. And definitely something that they need to understand when we talk about next G systems, right? Yeah, Wi-Fi.
Wi-Fi, 4G, it's all OFDM.
Yeah, absolutely, yeah. And that's something I definitely try to, and there's, again, GNU Radio has a great tutorial on that, so very useful stuff. Thank you.
Any other questions? Oh, yes.
And while Marcus is hustling, I'll go ahead and say I am going to probably expound on this stuff a little bit more in my workshop on Thursday. So if you're interested in this, I'd love to have that conversation with you during that workshop.
Great talk. It's like music to my ear. My question is regarding your course material that you have prepared. When you actually go ahead and teach this in your class, are you teaching a theory first and then you are designing lab that goes with the theory, or the lab is the primary thing you want to teach and then your theory is sort of around that?
Yeah, so we start with the theory and we want the lab to back that up, right? So we started with the theory of AM, for example, and then we pull in the traditional lab, and then I pull in the GNU radio lab for them to be able to tie all three of those together. Yeah, so then we have theory, lab, and kind of simulation all working together.
Cool. I don't see any other questions, so please give a warm round of applause to Neil. Coming up next, we have Christopher Poore giving us an update on FISSURE.
Hi, I'm Chris Poore. I'm a senior reverse engineer at Assured Information Security, otherwise known as AIS. And in this talk, I'll be going over the recent remote sensor node updates to our open source framework called FISSURE. 1, 2. I'll start, for those that aren't familiar with FISSURE, I'll give you a basic overview. I'll try to explain why FISSURE is important, why it could be useful to you, and we'll go over the remote sensor node updates, and I'll spend most of this presentation walking through a video demonstration where I'll show you how to configure the sensor nodes. I'll show you some of the transmit and receive capabilities that FISSURE can do, and then I'll show you how to set up these auto-run playlists for the sensor nodes and set up different types of triggers to kick off different electromagnetic effects. A little bit about me. I'm a senior reverse engineer. I'm part of a team of security testers and other reverse engineers. So I'm coming at this from a cyber perspective, and as FISSURE does more of the RF things, as that gets filled out, it'll lean towards the cyber realm as we develop it some more. A little bit about my company, Assured Information Security. We're a cyber and information security company. We do all things cyber that you could think of. We have a couple hundred people. We're headquartered in Rome, New York. Check out our website, ainfosec.com, to view the different products and services that we offer. All right, so FISSURE is our open source framework. It's on GitHub right now. It's been out for a couple years. It was originally designed to help speed up the characterization of signals and the reverse engineering of RF protocols. It's kind of there to help solve this RF reverse engineering process, and it contains hooks for these different categories in that process, so for things like monitoring, collection, replay, and so on. And so as you go about your daily work and you have these tools and techniques and algorithms, FISSURE is a place where you can put them into software that can be shared by everyone. So it's a work in progress, and as we fill it out, it will be more automated and more complete, but as it is right now, it does a lot of things manually pretty well. It comes with a nice, easy, pain-free installer that installs hundreds of third-party tools. It's meant for beginners and experts. Beginners can learn about different topics. Experts can insert their cutting-edge code. It's written in Python. There's a nice GUI for it. And we're always looking for new contributors and lessons and things like that to add in the framework. So as you hear about FISSURE, think about ways that you could possibly contribute, and feel free to reach out to me. Why FISSURE? As I mentioned, you can stage your computer with hundreds of tools. You avoid starting from scratch. People you work with start from the same proven baseline. It's great for staging up computers from scratch. You can reuse your code, so as you do things in your daily work, it doesn't have to disappear when the project ends. You can contribute and put it inside of FISSURE, and you can access it later on, and you can share it with other people. If you want to learn about different technologies, FISSURE is great for browsing these topics and seeing things. It's very visual, and you can discover improvements for FISSURE, contribute. You can build something, you can advertise it online, you can get famous through it maybe, I don't know. And it's different than working on a project and not getting any recognition for it. I mean, you can help other people as you do this. So share your success, network with other people, help grow a community, and grow professionally. Put it on your resume saying you contributed to FISSURE. As we're at GRCon right now, here are some of the important GNU radio aspects. FISSURE is centered around GNU radio. It lets you install all the different out-of-tree modules with a single click. You can access the flow graphs and scripts that you like to use, change variables with a couple clicks. You can launch live inspection flow graphs against files or using radios. You can download collections of example signals from our online archive that we're building up. And you can view default variables and tables, build playlists, apply triggers, and we have it backwards compatible with a few GNU radio versions. So FISSURE is intended to solve that RF reverse engineering process. In particular, it has a bunch of tabs that do different things. I won't go into detail about all the tabs, but generally we start out capturing large streams of IQ data, and then we try to isolate those streams into individual files using signal conditioning techniques. And then from those individual files, we do feature extraction to get statistical values that'll help us with AI, ML models for classification of things like protocols and emitters. And that isolated data, those statistical features and those classification results can go to the next phase, which might be trying to obtain a bit stream. So you'll have an example IQ file, and you apply techniques to try to get those bits. And you try to get as much information as you can and add it to your library. And then we also have attack tabs for manual analysis. In the future, we'd like to automate all of this, have more vulnerability analysis, discover what something is, and then react to it and see if you've had an impact on the system. It does some preliminary fuzzing, but it's mostly manual analysis right now, and we're going to tie it all together. Here are more tabs, our online archive, the new edition, the sensor node tabs. We'll go through all this. View the library, add things to it, view the logs, access the menu items. All right, so what do I mean by remote sensor node? These are general purpose computers. They support any type of radio peripheral or sensor that you can plug into a computer typically. They run scripted playlists on startup, or they can be controlled through user interaction using the FISSURE dashboard GUI. They save data locally to the remote sensor node, and you can transfer it over the network. You can also transfer data to the sensor nodes. They maintain existing FISSURE capabilities, so whatever you used to do with FISSURE, you can still do with these sensor nodes. It runs a small subset of code, so if you're running it locally, it's the same code that you would run remotely. You just do it on a different machine. And you can communicate with these sensor nodes locally, like I said, over a local network, over the internet. So it's a great way to access different environments remotely. So here's kind of an example of what I'm talking about. You have a laptop that has the FISSURE dashboard GUI. It's connected to a Wi-Fi network. And then you have two sensor nodes. One might be a mini PC with a couple SDRs connected to it. Another might be a single board computer with another SDR connected to it. So this is what I'm talking about when I say remote sensor node. Some of the benefits to this approach: it's low cost, versatile hardware options. You can swap them out based on the mission need. There's flexible software that supports integration. We can use existing computers on your platform perhaps, or you can network to pieces of your software and just pass data back and forth. It's open source. It provides unique levels of access, so you and your partners, your collaborators can all share the software today. It doesn't take that much to get it set up. It's a great education and training tool. It provides remote access for RF testing. I do that a lot in my work, so if I work remotely, I can access devices back at the office, and this is a nice way to set that up. And it widens access to other RF environments, maybe places around the world, special test sites, laboratories. I'll talk about that a little bit more. We set up an IoT laboratory where this is a big part of it. And in FISSURE, and these updates also unlock a lot of geospatial scenarios for FISSURE, like direction finding, tracking, intrusion detection, mobile deployment, perimeter fence. These things aren't in place yet, but with these updates, we can start working towards those. So this IoT lab that I mentioned, a lot of the remote sensor node work that we did falls under this technology accelerator called Orion. It's spun up by the Air Force and a few other partners. AIS is one of them. And if you work in the IoT space or Internet of Military Things, and you need someone to help you accelerate some technology or something you're working on, I encourage you to check out orionassured.com and contact the people through there, and maybe you'll find something that'll help you out. All right, so now I'm going to start our walkthrough through FISSURE in the video. All right, so before I open FISSURE, I want to kind of show you the installer for it. You just run the install script, and it will open up a little GUI, choose, let you choose what operating system you're working on. It should detect it automatically. And from here you have different categories of tools that you can install. They're not all required. They're there if you want them. If you click on them, you'll see the code that gets run. And on the right side, you'll see a little verify section at the end. And if it passes the test after installation, the items will turn green. If it fails, it'll turn red. You really only need to do the minimum install, like the top 4 items, the hardware, the compile flow graphs, if you're setting up a new remote sensor node. Everything else is kind of just extra third-party tools that are optional, depending on your needs. But it's a great way to explore software, and you don't have to worry about installing it. If it doesn't work, I'd like to hear about it. The items that aren't checked by default, I don't know how to fix yet. So I could use some support with those. A lot of times they'll just fade away, and they change how they install things. All right, so if you want to open up FISSURE, you just type the FISSURE command from anywhere in your terminal. It'll open up this nice little GUI. And if you've never seen FISSURE before, there are different menu items on the top for standalone flow graphs, for tools for different categories of technologies. There's a lot of reference material, online calculators, websites, and most of them will just open up a terminal with an example command of how to use it. So it's a great way to explore things maybe you've never seen before. There are also lessons that I'm starting to add to FISSURE. The top ones are the ones that I've made. The ones in the bottom are just links to places that I thought were interesting. I'd love to hear about more of them. There's a user manual that you could access offline as well as online. And let's get into the new updates here. So on the top, there are new buttons. This says new sensor node. If you click it, you can launch a local or a remote sensor node. If you're launching a remote node, you just enter the IP address in the ports, and you connect to it, and you can recall different setups. You can ping it. So the remote sensor node right now is running on a different computer. It's running a small subset of code, and I'm using this GUI to detect what pieces of hardware are connected to the node. So you can check different radios, and the idea is to get unique identifiers. So if I run flow graphs, I know which ones I'm targeting. So if you have 2 hacker Fs, I need to know which serial number that you're using for it. So you probe it, you scan it, you can guess if you have multiple devices connected, and you're just adding it to the defaults for the different FISSURE tabs. I'll show you in a second what it's doing. So you click Add to All, and it goes to all the tabs. And throughout the tabs, there are these combo boxes for choosing the hardware that you just selected there. You'll see the name of the radio and the serial number or whatever identifier. And you can access them in different locations throughout FISSURE. So these are some of the places where they ask you to select the hardware. If you need to change between nodes, you just right-click the buttons on the top, and it will toggle back and forth between nodes, between active nodes. If you want to launch a local node, that's what I'm doing here. It runs the code locally on your computer. It takes a little bit for it to kick off, but it's the same procedure. You can check multiple radios at once and click that auto scan, and it will go through all of them and try to find the identifiers. And you can probe them. It'll spit out whatever custom function you want to use to probe. If there's nothing there, it'll probably be blank. All right, so let's go through some of the transmit and receive things you can do in FISSURE. So under the attacks, you can launch single stage attacks. These are just scripts. These are Python scripts, GNU radio flow graphs. You can view the default variables, change them before you run it and while it's running. So I have a lamp there on the right there that I just turned on. It's connected to an X10 switch, like an outlet switch, and it's got a Z-Wave light bulb inside of it. You can do multi-stage attacks where you run one attack followed by another attack. You can specify durations for each one. Here I'm turning the switch off, then on, and then I think I'm changing the colors. I'm changing the duration of each attack right here. So you can change the variables before you launch it, just like the single stage. And then click start, and it'll go. Lamp off. Lamp on. And random colors. Thank you. This is not live. All right. Next, there are different analysis capabilities in FISSURE. You can view IQ files. You can record within this tab. You can also play back signals. So here I'm going to test the recording. You can't really see what's happening live while it's doing it, but if I press a button on that remote that just popped up on the screen, I can capture a signal and it'll plot it as soon as it's done recording. You can change the sample rate, the number of samples. Pressing the button, and you get something like that. All right. I'm doing it again because the signal wasn't very good. There we go. I think next we'll test the playback. So this is a Z-Wave file, Z-Wave signal that will play back at 900 megahertz or so, and it changes the color of the light bulb to green. You can't really see the greenness of it, but it's there. There are also live inspection flow graphs that'll pop up a nice little GUI, so if you want to do a waterfall or something simple like that, that's a great place to add them. If you have your own flow graphs that you'd like to use, I'd like to hear about them. The problem with this on the remote nodes is that it's going to pop up the GUI on the remote node, so we still have to fix that. We have to work on passing the data over the network and prevent that from happening. So here we have our online signal archive with just examples of signals. I think I have like 15 devices or so right there right now. So if I want to look at a key fob, which I'm doing right here, I downloaded it from online, and I can do some initial analysis. I can plot different points in data. I can reuse existing tools. So if I have in Spectrum, I can load it up in Spectrum. This is good for the capture the flag. So you get the ones and zeros from that or someone else's tool. So if a tool has a command line option, I'd like to hear about it so I can just call their tool without having to reinvent the wheel. Otherwise, I'm going to develop solutions to get the bits from something like this. You could also use the buttons on the bottom to do things like a moving average filter, throw out every other sample, clean up the signal a little bit so it looks a little nicer. It applies to whatever's in the window. All right, so the online archive also lets you do simple replay of signals. So if you want to make a playlist of signals, you can just put the IQ files right there. It'll send it out on one radio. And okay, this is new. Our sensor nodes have the ability to build these auto-run playlists. They have the option of automatically starting when the sensor node starts. And the way you build them is through the single stage and multi-stage attacks. So you can also import and export them and copy them over if you want. So here I'm going to show you a single stage attack being added to the auto-run playlist. You just click the button Add to Auto Run on the bottom. And you can change the duration, the timeouts, delays for individual items. You can also change it for the playlist as a whole. So if you want the playlist to kick off at a certain date or time, you can do that. You can have it repeat at a regular interval. I often have this just changing the color of a light bulb when I go to an expo or something, every minute and a half or something like that. Each item in the playlist will run at the same time in different threads, essentially. So if you want to have two different radios do two things at once and you have enough processing going for your computer, you can do that. It's pretty flexible. If you want to have one thing run after the other, that's where you do the multi-stage. And that's a good solution. If you can't run two flow graphs on the same piece of hardware at the same time. It'll complain, it'll give you some errors likely. So a multi-stage attack is a way to get around that. And if you just want to start the attack right from this GUI, you can by clicking start and stop. All right. You can export, import, recall settings. It writes it to a nice little YAML file. You can also do file navigation to the remote nodes. So if you select an active node, you can view different folders on the sensor node. It's not full file navigation, but it's limited to different folders. You can download files. You can download folders. It'll zip them and transfer them over. And you could also transfer files to the sensor nodes and open them up and view them. And delete files on the nodes. All right, so that's a lot of the new stuff for the sensor nodes, but let's talk about the triggers for the different attacks. So the single stage, multi-stage, archive playlists, and the auto run playlists all have these little boxes above them that let you add triggers. And I have different categories like acoustic environment, file system, RF, time, and so on. And so here is a little sound threshold that uses my computer microphone for kicking off an attack. I think I'm just doing random colors. So I'll just yell something in my microphone, and it'll sit there saying waiting for triggers until whatever condition is satisfied. And you can set up multiple triggers, and whichever one is executed first successfully, you'll cancel out all the remaining triggers and go right into the playlist or the action you're trying to take. Let's go through a couple more of these. Yeah, this is just showing that if you want to add multiple triggers, you can just click add, it'll show up in that little table down there. And you can delete them through that. The environmental triggers require the internet right now. They use WTTR.in. So if you enter a city or an address, you can validate if you typed it in right by clicking the little validate button underneath it. It'll tell you, it'll give you an answer right away. So before you start the attack, you can make sure you got the right city. Sometimes you don't have to specify the state or the country. Like if you're doing Las Vegas, that's probably pretty good. But sometimes they're duplicate city names. All right, we have networking. We have these RF triggers are kind of interesting. Can't read the exact one that's going on. Okay, this is looking for an SSID, so it uses a Wi-Fi adapter. So you can use this for traditional cyber attacks. Like you listen for a router to show up, then maybe you throw an exploit at it. So this is what it's doing right now. It will it'll listen for that router that's sitting there on the table, then it will do a reboot attack to reboot it. All right. So other benefits to these RF attacks are that you can run GNU radio flow graphs, and you can listen for the standard out in the messages. So if you want to listen for a radio station to show up or a song title, you can do that. If you want to listen for like a button press, you can do that. You can listen for cellular towers. You can use GPS to know if you're within a range of a point or past the boundary. And you just set up your custom settings for whatever trigger you want to do, and it's pretty easy to add. We have instructions on how to do it in the user manual. I think I'm going to end the video right here. It's more the same. You can view the whole extended video online. There's a bigger video that goes along with this. But I want to wrap things up. So back to the slides here. I'll do this. So the outlook for our project, we're looking to complete the roadmap items that are listed on the GitHub page. We want to produce more capabilities and participate in RF simulation events, expand and coalesce the online archive of IQ files, test and improve the code through remote assessments, extend to academia, create some classroom exercises, support new GNU radio versions as they come out, and produce more videos for YouTube and Twitter, and experiment using the nodes in different operational scenarios and integrate more on more platforms. If you want to learn more, check out our GitHub page, go to our website, our company website, follow us on Twitter. I'll be posting videos, and that's all I have for now. If you have any questions, let me know. Thank you.
Thank you, good work. How large is your database of IQ files and RF signatures?
I'm sorry, the question was?
Oh, sorry. How large is the database that you've established for IQ?
So, it's pretty small. It's only 15 types of devices, really, but it's recorded at different sample rates. It's really just there to test FISSURE at the moment and do some initial AI, ML type testing. So it's not huge, but we're interested in adding more. I have lots of other types of data that I could add. We just have to get around to it.
Just one will follow up. So you say AI, what kind of thoughts do you have on that?
So throughout FISSURE, we can add AI, machine learning throughout different topics. Right now, we started with the upfront piece of protocol classification, emitter classification. There's a whole video on the TSI tabs for FISSURE, the target signal identification. So that's where we're starting, but as we fill it out, we'll add more to the different sections where we can.
Okay, thank you. As there's no more questions, have another round of applause, please. So, next up, it's awesome that Shammi Doly from ASU made it, and she will talk about real-time waveform optimization for radar applications. So, please welcome her.
Hello everyone, good afternoon. My name is Shammi Doly. I'm from Arizona State University, and I'm a PhD student, candidate actually, and I work in a research center named WISCA, and Dr. Daniel Bliss, yeah, he's my boss. I know it's been a long day, so I won't take much time, I promise. Yeah, I will keep my talk short. Okay, so this is the outlook. Okay, so based. So the first one is like the waveform selection. So yeah, like most of the radar system I think use the pulse radar because it's simple, and in pulse radar technique we send pulse in each PRI, and we transmit this pulse and we wait and we get the reflection back, and we kind of do radar signal processing and get the information of the environment. Then we have the continuous waveform radar where the transmission and receiving is like simultaneously happening, and because of some obvious reason, like we don't get any range in continuous waveform, so we can move into like frequency frequency modulated continuous waveform. And so yeah, so I don't know. Okay, so in FMCW radar, we sweep the fixed bandwidth in like in an instantaneous time, and so I tried two different sweeping methods. The first one is a sawtooth, and then we have like the triangular sweeping method. So for like sawtooth or triangular modulation, the bandwidth is fixed since we are not changing the bandwidth, so the range resolution we are not getting any benefit. But yeah, for triangular waveform we can get like a Doppler resolution, better Doppler resolution. And yeah, so like the basic FMCW radar waveform, like the trade-off, like I think it more depends on like what type of application we choose. So we have to go to like the range and the Doppler and the pulse compression techniques, where so like in Rayleigh bandwidth, if you consider like that bandwidth is the inverse of the duration of the pulse, so the time bandwidth product is 1. So if we keep increasing that duration of the chirp, we will get like more uniform shape. And yeah, we can keep increasing the duration of the chirp. So then the next part is the optimization. So why do we need optimizations? I think it's so far it's obviously clear. So many people have like so many researchers like trying to do research in this field, which is RF convergence. We are kind of running out of the spectral, so we have to think like how we can wisely use our spectrum, and we can share the spectrum with the other users. Like in my research, I'm doing the kind of investing how we can share the radar band with the communication user. So for that, I pose the waveform design problem in a decision theory problem and formulate the problem as a partially observable Markov decision problem. So which is like a mathematical framework to formulate the waveform design problem. And obviously when we pose the waveform design problem in a decision theory or AI-based theory, it will be like it will make our life more complex, like complicated. So to solve that complicated problem, we have to again come up with some kind of dynamic programming approach, where we call it like break the problem small pieces and then solve it. And to do that, I use two different types of dynamic programming. The first one is like the nominal belief state optimization, and then the random sampling multipath hypothesis. And so the intention is to reallocate the resource and to see like what's going to happen in the next step. So it's like it could be a communication optimized, or it could be a radar optimized. So if there is nothing in the environment, nothing interesting in the environment, then we don't need to continuously sending the radar waveform. We can obviously use it for the communication use. So that was the purpose of this joint radar communication research. And also like to shape the spectrum, like or optimize the waveform, we use like the Kramer-Rao bound. So which means like when we try to estimate the estimate the information of the environment, we need to know how accurate is our estimator is. And for that, we need to know some theoretical bound. And depending on that bound, we can tell how accurately our estimator is behaving. And the bound, the Kramer-Rao bound equation is like directly inversely related with the RMS bandwidth. So our target is to try different amplitude modulation technique, like concave up. We can see here like the concave up, concave down, and some flat modulation technique, and see how the RMS bandwidth change so that the estimation performance of the waveform change. So, and the last part is the receiving end, which is the test purpose. And for the test purpose, I use the stretch processing, which is a cheap trick. Like I think industry use this trick like to avoid the like a computationally expensive match filtering technique. And the trick is very simple, like we have our transmitter signal and we have the reflector signal, and then match two signals and get the like the overlapped portion and get a bit frequency. And the bit frequency, since it's like it acts like a tone, so we don't need that much sample, so the sample sizes really shrink down. So yeah, it's computationally really efficient. And so here's the GNU radio flow graph. So the first part is like using the chirp synthesizing, and I used a GNU radio block VCO complex to synthesize the chirp. And the next part is the optimizer, where I use like 3 different masking, as I mentioned earlier, and a feedback loop to select which mask we want to use at what time. And to do that feedback thing, one thing I want to make clear that it is still non-deterministic, because I don't know, so far my knowledge, I didn't find anything in GNU radio that I can feed back the information in really real-time kind of things, because it's kind of non-deterministic. So I'm like, the way I did it, like I choose like a like fixed number of samples. So for each CPI, I'm like, okay, after these samples, change the chirp, like a mask. So that's how I did the feedback. It's like a message passing block in GNU radio. I use that block. And then the stretch processing block to just compare like, okay, how my standard chirp and optimized chirp behave. And this is like the simple setup that I did. And so, yeah, so there are 2 types of modulation. The first one is the sawtooth, and then the triangular chirp, you can see. And there is like a GNU radio block latency, as you can see that the signal generator and the VCO output is not properly aligned. And I have no idea how to fix these things. Maybe, yeah, I have to think about it. So yeah, this is one challenge that I faced during the experiment. And also like for triangular chirp, like for stretch processing, I have to do it twice, because like for up chirp, I have to do one stretch processing, and down chirp, I have to do again another stretch processing. So yeah, like if we can see the concave up shape, where what we can call it like the COM optimal. The reason I'm calling it communication optimal, because see, I am only choosing the frequency with lower energy, which means like the it's kind of concaving up, so my spectral shape will be like act like I'm choosing the central frequency, and I'm like chopping down all the high frequency. So that's why it's like I'm calling communication optimal. And then we have this radar optimal, where it's concaving up, so I'm like not considering the central frequency, I'm considering all the edges frequency. And then we have this unweighted chirp, and we can see like nothing is happening here, like it's just same as the standard chirp. So yeah, this is like the last block where I did the stretch processing. So after the stretch processing, we can see like the the standard chirp and optimized chirp output, like at the receiver end. So here's a trade-off to make. I think like we can see here clearly that for standard chirp, it's like more narrower peak we can see, but the energy is like much more. For the optimized chirp, we can get much more energy, but the width is like more wider for the optimized chirp, and it's happening because it's a kind of concave down chirp. So I'm like picking the center frequency, not the edge frequency. So it's like happening when we call it the communication optimal, because for the communication user we need more energy. We don't consider like we are not detecting any target. So yeah, that case. So here is the trade-off we have to make, or decision we have to make, what type of application we choose. So this is the last slide, last experiment I did. So for the fixed delay, as we can see, the left plot where we can see the peak for both standard chirp and optimized chirp, that we can detect the peak. But for the when I increase the delay, I can see for the standard chirp there is nothing, there is no peak at the output of the stretch processing, because there is no overlap is happening because I increased the delay. However, for optimized chirp, I still can. It's not a perfect peak. It's like it's kind of something weird is happening there, but still I can see some peakish kind of thing there. So if we can tune our mask properly, we can get at least theory is telling us that we will get something better here. So yeah, that's all. This is the summary of my today's talk. I tried to make implement an NP-hard problem in GNU radio, which is insane. When I spoke with my professor that I'm gonna implement this NP-hard problem, and he's like, really? Okay, have fun. So yeah, I did it. It's kind of fun. It was a fun journey. I tried to design the chirp, optimize the chirp, and did the experiment and see okay, what's happening here. And the reason I did it because when I was doing my literature review, everyone is talking about waveform design and we're running out of spectrum, we should do something. And there are a lot of theoretical things is happening out there, but there is very less work where we can do something, we can see something experimentally. People are not touching the hardware. So that's the reason I thought I will do it. I will see how it actually works, how it works in theory versus in reality. So that's the inspiration behind this work. And challenges I already mentioned, this indeterministic feedback loop, and also GNU radio has there's some limitations, as we know. And so for next step, I'm still currently working on a project where I'm trying to design non-linear waveform design. So my next target is to, instead of using the LFM chirp, using the non-linear chirp and see how it works. And also instead of using GNU radio delay block, we'll use some real target and we'll do the experiment in our hallway. So that's the next big thing I think we will do. So yeah, that's it. Thank you very much. I can take the question.
So, where are the questions? Yes.
I'm always happy to see people doing radar stuff in GNU radio, so it's very nice. Did you use any out-of-tree? Use GNU radio, straight up GNU radio, basic blocks, and that was it?
Yeah, I just use the GNU radio. There is no MATLAB or nothing else, the GNU radio and the SDRs.
But you also didn't use any out-of-core GNU radio modules. You didn't install any additional GNU radio modules. You just used the basic building blocks from.
Oh no! I made some blocks, the embedded block, the Python block you're asking.
Mm-hmm.
Yeah, I made few blocks.
Cool, but you didn't import any additional. Okay, that's fine. Thank you very much.
Yeah. So yeah, the mass selection block and the mass generation block, those are those are the blocks that I used. And the algorithm behind those blocks was my research. The paper, so I just implement. That was in MATLAB, so I just converted it to Python and made a block. Yeah.
Okay, I see no other questions, so please give a closing round of applause to Shammi.
Thank you.
Thanks, Marcus. All right, so that concludes the first day of talks for GRCon. I have a couple announcements. For anyone who is giving a talk tomorrow, actually at all this week, please upload your slides. We'd really appreciate it. It helps us out a lot. Reminder, ham radio exams are tomorrow. The website has a lot of details, including there is a cost. It's, I think, $15 cash to take the exams. So you may want to study tonight, may not want to stay out too late. There's SETI, as you heard earlier, is hosting a small social, so it's a little bit limited in size, but I am told there is still space if you're interested. Can you please raise your hand? Go over there. Vishal is happy to give you the information so you can go. I encourage you to go and attend. I hear there's going to be food and food, everything covered. Okay, or something. I won't put them too much on a hook. All right, and then it sounds like there's going to be an informal group of people heading towards Kearns Hall around 6-ish. If anyone is interested in just getting dinner, it's low key. Like I said, it's not an official organized event. It's just if you want to hang out with some other people. It's a place to go, but just giving people a heads up. And then I have where we're at with Capture the Flag. So we actually, we have really close. So first is registration desk night shift. Second is not the FCC. So the last that I checked, it was a 7-point difference, so it's pretty close. Third is What the Freak. And there's 27 teams. Oh, thank you. There are 27 teams registered so far. So, it is no longer 7 points. It's now 18 points. All right, then. So if you're interested in doing Capture the Flag, I really encourage it. If you're looking for a team, I have my own team. Organizers are busy. I'm always taking people. I don't know if I'm allowed to do that, but I did. So anyways, thank you all for attending. Thanks very much to our speakers. Let's give it a round of applause once again for our speakers for today. All right, and we'll see you here again tomorrow. So thank you very much.